The universe began 13.787 billion years ago. Everything that exists now, every star, every rock, every drop of water, was squeezed into a space smaller than a single speck of dust. It was so hot and so tightly packed that nothing behaved the way it does today. Then, in a burst faster than anything that has ever happened since, that tiny speck stretched out in every direction at once, swelling from smaller than an atom to larger than a galaxy, in less time than it takes a thought to begin. Space itself was expanding, carrying everything with it. After that first burst, the newborn universe was a glowing fog, too hot for atoms to even form. It took a long stretch of time before it cooled enough for the first simple atoms to click together. And only after that did the fog finally clear, letting light travel freely for the first time. That ancient light still drifts through space today, like the last echo of a bell struck at the very beginning of everything. Here is where the puzzle begins. Asking what happened before this moment is a little like asking what is north of the northernmost point on a globe. Once you are standing at the top, there simply is no further north to walk toward. Some scientists think time itself might work the same way, fading into something else entirely as you get close enough to the beginning rather than hitting a solid wall. Other ideas picture the beginning differently. One pictures our universe as the rebound of an earlier universe that had been crushed down to nothing, bouncing back outward the way a ball springs back after hitting the floor. Another pictures endless bubbles constantly forming within some larger, ever-stretching foam, with our entire universe being just one single bubble among countless others, each one its own separate world. A third pictures time curling smoothly backward instead of stopping abruptly, the way the surface of a ball has no edge no matter how far you walk along it. None of these pictures has been confirmed. What is certain is that everything we can see, touch, and measure began from that same searing, tightly packed beginning and grew into the vast, star-filled sky above. Whatever came before it, if anything did at all, remains hidden behind the very first instant in a place our clocks and telescopes cannot reach. What caused the Big Bang? Picture a ball balanced right at the top of a smooth hill. It doesn't take much to send it rolling. Some scientists think the very early universe was balanced in a similarly delicate way, sitting in a strange high-energy state that could not last. Once it tipped over and began to roll, it released an enormous burst of energy, and that release is what became the fireball we call the beginning of everything. But this still leaves an old question hanging in the air. What tipped the ball in the first place? One idea suggests that nothing needed to. It points out that gravity itself behaves like a kind of debt. Every bit of matter pulls on every other bit, and this pulling force works almost like an opposite to the energy stored inside that matter. Add the two together across the whole universe, and they may cancel out to exactly nothing. If a bank account can sit at zero, while still holding both a large deposit and a large debt, perhaps the universe could spring into being while still totaling zero overall, needing no outside push at all. A second idea borrows from a strange but well-tested rule of very small particles, where things sometimes appear or change without any clear trigger, purely by chance. A single unstable atom deep in a lump of rock will eventually break apart, but nothing pushes it at the exact moment it happens. It simply happens following the rules of chance rather than a domino falling into another domino. Some scientists wonder whether the universe's beginning might have worked the same way, not caused by something before it, but arising the way any of these tiny chance events arise, following its own internal rules rather than being pushed into existence by an earlier event. There is also a deeper riddle sitting underneath all of this. Even if we fully explain the spark that started everything, we can still ask why the rules governing that spark exist at all, and why they take the particular shape they do rather than some other shape entirely. Every explanation in science eventually rests on some deeper rule being simply true, without a further reason offered underneath it. That may be the point where explanation itself runs out, at least for now, leaving one of the oldest questions still glowing quietly, unanswered above everything else. Why does anything exist at all? Every explanation for why something exists usually points back to something else that already existed. A chair exists because someone built it out of wood. The wood exists because a tree grew it. The tree exists because of soil, rain, and sunlight. Every one of these answers borrows existence from something else that came before it. But this trick cannot work for existence itself, since there is no earlier thing left to borrow from once you ask why anything exists in the first place. One old answer imagines that everything ordinary depends on some deeper thing that simply cannot fail to exist. The way a shadow depends on a lamp. Ordinary objects could have easily not existed at all, this idea says, but something underneath all of them could not possibly have failed to be there, and everything else rests on top of it. Another answer suggests that nothing is not actually as simple or stable as it sounds. Even the emptiest possible patch of space, once examined closely, is never fully still. It constantly flickers and stirs on its own. If total emptiness is naturally this restless, maybe it can never truly hold steady as nothing forever, and something is bound to stir loose from it eventually. The way a perfectly balanced coin standing on its edge will eventually topple over on its own. A third answer simply accepts that existence might not need a reason at all. It suggests that asking for a cause behind existence itself may be like asking what color a number is, a question that sounds meaningful but may not actually fit the thing it's being asked about. There is also a quieter observation worth sitting with. If nothing at all existed, there would be no one present anywhere to notice that absence or to ask why it was that way. Only in a universe that does exist could a question like this ever even be asked aloud. That doesn't explain why existence happened, but it does explain why anyone would ever be around to wonder about it. None of these answers has ever been proven. The question remains open, resting quietly underneath every single other question that has ever been asked, in science or anywhere else. What is dark matter? Picture a spinning pinwheel of stars, slowly turning in the dark. The stars near its center circle around quickly, exactly as expected, since they sit close to where most of the pulling force should be strongest. But the stars way out near the edges should be crawling along slowly, loosely held by a much weaker pull from so far away. When astronomers actually measured this, the outer stars were not crawling at all. They were racing around just as fast as the stars near the center, as if some invisible hand out at the edges were holding them in place. This pattern showed up again and again in one spinning cluster of stars after another. Whatever was gripping these outer stars could not be seen through any telescope. It gave off no glow, blocked no starlight, and left no shadow. Yet its pull was unmistakably there, wrapped like an invisible cocoon around every one of these star clusters, reaching out far beyond where the visible stars themselves came to an end. Further clues kept stacking up. Clusters of these star groups bend the light of even more distant galaxies behind them, the way a curved piece of glass bends light passing through it. Measuring exactly how much that light bends revealed far more hidden weight than the visible stars alone could ever account for. And when two enormous clusters of galaxies once collided head-on, their glowing gas clouds crashed together and slowed down, the way two clouds of smoke might collide and tangle. But whatever unseen material was gripping each cluster sailed straight through, barely slowing at all, as though it had passed right through the wreckage untouched. Scientists have spent years searching deep underground in tanks of quiet liquid shielded from every ordinary disturbance, hoping to catch one of these invisible particles brushing past an ordinary atom. So far, nothing has ever been caught red-handed. All that is known for certain is that this hidden material outweighs every star and every visible object in the universe combined, wrapped like scaffolding around galaxies everywhere, holding them together in a grip nobody has ever managed to actually see. What is dark energy? Space itself has been quietly stretching apart ever since the universe began, carrying galaxies farther and farther from one another, the way dots painted on a balloon spread apart as the balloon is blown up. For a long time, scientists assumed this stretching should be gradually slowing down, since every bit of matter in the universe pulls on every other bit, tugging everything back inward, like gravity always does. Then astronomers carefully measured a very specific kind of exploding star, one that always bursts with almost exactly the same brightness no matter where it appears. By comparing how bright these explosions should look against how bright they actually appeared, scientists could measure precisely how far away they truly were. The most distant ones came out dimmer and therefore farther away than a slowing stretch of space could explain. The stretching wasn't slowing down. It was speeding up. Something invisible appeared to be pushing space apart harder and harder over time, working directly against gravity's pull rather than adding to it. Scientists gave this invisible push a placeholder name, dark energy, and by their best measurements, it turned out to make up the single largest share of everything in the entire universe, more than every star, every planet, and every wisp of hidden gripping matter combined. One leading idea suggests that empty space itself is never truly empty, and instead carries some tiny built-in push all its own. As space stretches and makes more room, that push grows right along with it, feeding its own expansion in a runaway cycle. Another idea suggests this hidden push isn't fixed at all, but might be slowly changing in strength as time goes on, growing weaker or stronger depending on the era. Which of these pictures is correct will shape everything about how the universe eventually plays out. If the push stays steady forever, galaxies will keep drifting apart until the sky itself empties out. If it grows stronger, it could eventually pull apart galaxies, stars, and even atoms themselves. And if it is slowly fading, an entirely different and gentler future might be waiting instead. For now, the single largest force shaping the universe's future remains almost completely unexplained. Is the universe infinite? Light has only had a certain amount of time to travel since the universe began, which means there is a limit to how far out into space anyone could ever possibly see, no matter how powerful a telescope they built. Beyond that limit, there could be more galaxies, more stars, more empty stretches of space, or the whole universe could simply come to an end. Nobody standing anywhere within it could ever tell the difference just by looking. The same way a sailor surrounded by ocean in every direction cannot tell whether that ocean stretches on forever or simply ends somewhere over the horizon. To figure out the answer, scientists study the overall shape of space itself. If space curves back on itself like the surface of a giant ball, then traveling far enough in a straight line would eventually bring you right back to where you started, and the whole universe would be a finite, though endless feeling loop with no outer wall anywhere. If space instead lies perfectly flat, stretching evenly in every direction the way an endless sheet does, then it very likely goes on without any stopping point at all. Careful measurements of the oldest light in the sky, the same faint afterglow left over from the universe's fiery beginning, suggest that space is remarkably flat, about as close to perfectly flat as anyone has ever managed to measure. That leans strongly toward a universe stretching out endlessly in every direction, far beyond anything anyone could ever see. If that is true, something strange follows from it. In a universe stretching on forever, filled with roughly the same kind of scattering of stars and galaxies everywhere, every possible arrangement of matter that could exist would eventually have to repeat itself somewhere out in that endless stretch, simply because there are only so many ways matter can be arranged in any given patch of space, while the space itself never runs out. Far beyond anything any telescope could ever reach, there could be other patches of space arranged almost exactly like our own tiny corner of it. Whether the universe truly goes on forever or eventually comes to some hidden end remains unsettled. What is certain is that everything anyone has ever observed is only a small, glowing patch within something almost certainly far larger still. Does the universe have an edge? It feels natural to imagine the universe as a giant room with some kind of wall out at the very far edge of it. But that mental picture quietly assumes something that turns out not to be true. That space is an empty container that everything else simply sits inside of, the way toys sit inside an empty box. Space itself is not a container standing separately from everything else. It is a stretching, bending fabric that came into being together with everything inside it, and it has no outside surrounding it for a wall to separate it from. Picture the surface of a balloon with dots painted across it, representing galaxies. As the balloon is blown up, every dot drifts farther from every other dot. No single dot sits at the center of this spreading pattern, and there is no edge anywhere along the balloon's surface for an ant crawling across it to eventually bump into. The ant could crawl in a straight line forever and simply loop back around to where it started, without ever once hitting a wall. Our universe may work the very same way, only stretched across one extra dimension beyond what the balloon's flat surface shows. If space curves back on itself like that balloon's surface does, it has no edge anywhere, no matter how far anyone travels in any direction. And if space instead lies perfectly flat and simply goes on forever, as our best measurements suggest is close to the truth, then there is no edge for the same, simpler reason. It never runs out of room to keep going. This also clears up an old misunderstanding about the universe's beginning. It's tempting to picture that first fiery moment as an explosion happening at one single spot, with everything flying outward from that spot into some already existing empty space around it. But that beginning didn't happen at one spot inside space. It happened everywhere in space all at once, since space itself was smaller back then and has simply been stretching out ever since. There was never a single center it exploded from, and there is no outer edge it has been rushing toward. So the honest answer is that the universe has no edge, not because nobody has looked hard enough to find one, but because the very shape of space doesn't include the kind of boundary our imagination naturally expects. Will the universe end? Picture the night sky slowly dimming over an unimaginably long stretch of time. The stars burning brightest today will eventually run out of the fuel that lets them shine, one by one, and new stars will become harder and harder to form as the raw material needed to build them grows scarce. Small, dim, slow-burning stars will keep glowing long after brighter ones have gone dark. But eventually, even they will fade. What remains will be cold, burnt-out embers drifting silently through an ever-emptier sky. Even those embers won't last forever. Very slowly they may lose themselves entirely, dissolving into faint, drifting light over a stretch of time so long it makes the entire history of the universe so far look like a single passing moment. Whatever remains after that would be an unimaginably vast, cold, and almost perfectly still stretch of empty space, with nothing left anywhere to spark, burn, or change ever again. Scientists call this ending a slow fade into stillness, and based on current measurements of how fast space is stretching apart, this quiet fade looks like the most likely ending. A different possible ending flips this picture entirely. If the invisible push driving space apart ever reversed instead of continuing, gravity could eventually regain the upper hand, pulling everything back inward the way a ball thrown upward eventually falls back down. Galaxies would rush together instead of drifting apart, growing hotter and denser again, collapsing back down into something resembling the tightly packed beginning the universe first sprang from. Current measurements make this ending look far less likely than the slow fade, though not entirely impossible. A third more dramatic possible ending imagines the invisible push growing stronger and stronger over time, rather than staying steady or reversing. If it did, that growing push could eventually overpower every bond holding anything together, first tearing galaxies apart, then solar systems, then planets, and finally the very atoms making up everything that exists, ripping the universe apart at every scale all at once. Whichever ending eventually comes, if any truly does, it lies at a distance in time so enormous that it poses no real threat to anyone alive today, or to anyone's grandchildren's grandchildren 1,000 times over. It is simply a slow, quiet fact drifting somewhere far off in the deep future. Why is the universe so perfectly balanced? Certain deep rules of nature had to land in an extremely narrow range in order for stars, planets, or anything resembling life to ever exist at all. Nudge any one of these rules even slightly, and the entire universe could have turned out completely barren. Consider the invisible glue holding the core of every atom together. If that glue were even a little bit weaker, the simplest atomic building blocks could never lock together properly, and stars would have no way to shine. If that same glue were instead a little bit stronger, atoms would fuse together far too easily and far too quickly, and every star would have burned through its fuel in a flash rather than shining steadily for ages, leaving no time at all for anything to slowly grow and develop nearby. Consider gravity itself. the invisible pull pulling everything toward everything else. It happens to be almost unbelievably weak compared to the other forces at work in nature. If gravity were only a little stronger, stars would form quickly, burn fiercely, and collapse into darkness almost as soon as they lit up, leaving no time for anything nearby to slowly grow. If gravity were instead weaker still, matter might never have clumped together at all, leaving the universe a thin, structureless mist with no stars and no planets anywhere. Even the invisible push driving space apart, discussed earlier, had to land in an extraordinarily narrow range. Push any harder, and matter would have been swept apart before it ever had a chance to clump into stars and galaxies in the first place, leaving space forever empty and smooth. Nobody currently knows why these rules landed exactly where they needed to for stars, planets, and living things to become possible at all. One idea suggests that countless other regions of space, or perhaps countless other universes entirely, might exist with completely different rules, most of them far too harsh for anything interesting to ever take shape. And that anyone able to ask this question in the first place could only ever find themselves in one of the rare places where the rules happen to line up just right. Another idea suggests a deeper explanation is still waiting to be discovered, one that will eventually reveal these rules were never really a coincidence at all. For now, the balance itself remains a striking and unexplained fact, sitting quietly underneath everything else in existence. Is there a multiverse? Picture space stretching out endlessly in every direction, filled everywhere with roughly the same scattering of stars and galaxies. As discussed earlier, in a universe this vast, every possible arrangement of matter would eventually have to repeat itself somewhere out in that endless stretch, simply because space never runs out while the number of ways matter can arrange itself in any one patch does. Somewhere impossibly far beyond anything any telescope could reach, there could be another patch of space arranged almost exactly like our own tiny corner of it. This is the simplest and least exotic version of the idea that other universe-like regions might exist. A second picture comes from the very early universe's first burst of expansion. Some scientists think this burst may not have switched off evenly everywhere at once. Instead, it may have kept swelling forever in most places, while switching off only in scattered little pockets here and there, with each pocket becoming its own separate, fully formed universe, possibly with entirely different underlying rules from our own. Under this picture, our whole observable universe would be just one bubble drifting within an endlessly bubbling, ever-expanding foam. A third picture comes from the strange behavior of very small particles. Instead of a coin toss settling into either heads or tails the instant someone looks at it, this picture imagines that both outcomes actually happen, each one branching off into its own separate, fully real world that can never again touch or influence the other. Under this view, every single coin toss, every choice, and every random flicker of any tiny particle anywhere might be quietly splitting reality into ever more branching copies, all happening alongside one another without ever crossing paths again. None of these pictures can currently be tested directly, since by their very nature, any other bubble, branch, or distant repeating patch of space would lie completely beyond anything anyone could ever reach or observe. Because of this, some scientists remain cautious about how seriously to take these ideas, even while others consider them a natural and expected consequence of theories that have already been tested successfully in other ways. Whether any of them are true remains entirely unknown, making the multiverse one of the most genuinely open and hotly discussed questions at the very edge of everything we understand about the universe. Part 2. The Mysteries of Space. What is inside a black hole? When a giant star finally runs out of fuel, it can no longer hold itself up against its own weight, and it begins to collapse inward. If the star was massive enough, this collapse never stops. The star keeps folding in on itself, crushing down smaller and smaller, until it disappears behind an invisible boundary in space. Past that boundary, gravity grows so strong that nothing, not even light, can ever climb back out. That boundary is the edge of a black hole, and everything past it is cut off from the rest of the universe forever. Nobody can see what actually happens deep inside, since no light ever escapes from there to show us. The equations that describe gravity everywhere else in the universe seem to break down completely at the very center, predicting a point where everything gets crushed down into an impossibly tiny space. Most scientists think this is a sign that the equations themselves are missing something, rather than a sign that reality genuinely becomes infinite and impossible right at that spot. Some scientists picture the crushing coming to a halt just before it reaches that impossible point, cushioned by some deeper, tinier structure of space itself that nobody has ever directly measured, similar to how packed sand eventually resists being squeezed any tighter. Under this picture, the crushed material might not vanish into nothingness at all, but instead bounce, or spring back outward somewhere else entirely. A different picture imagines that there is no single crushed point at all, and that the entire inside of the black hole is instead filled with an impossibly tangled, tightly wound structure, all the way out to the boundary itself, with no truly empty space anywhere inside. What can actually be observed from the outside has grown remarkably detailed in recent years. Telescopes working together have captured a direct picture of the glowing ring of matter swirling just outside one of these boundaries, with a dark shadow sitting right where the black hole itself begins. Ripples passing through space, set loose whenever two of these objects finally collide and merge, have also been caught rippling past our own planet, confirming many of gravity's stranger predictions in the most extreme conditions ever tested. Still, what waits at the very center remains completely hidden. Whether it is a truly bottomless crush, a hidden bounce, or a tangled knot nobody has ever pictured correctly, remains one of the deepest open questions standing right at the edge of everything we understand about gravity. Where does information go inside a black hole? A black hole isn't perfectly black after all. Very slowly it leaks a faint trickle of glow out into space, drawn from the strange, restless flickering that happens naturally at the very edge of its boundary. Over an unimaginably long stretch of time, this slow leak can drain a black hole of everything it once held until eventually it fades away completely, leaving nothing behind. This creates an uncomfortable puzzle. One of the deepest rules in physics says that nothing about an object's history should ever be able to vanish completely from the universe, even if it becomes scrambled beyond recognition. In principle, if you knew everything about how something ended up, you could always trace it backward to figure out how it began. But the faint glow leaking out of a black hole appears to carry no trace at all of whatever originally fell inside, meaning that once the black hole finally fades away entirely, whatever fell in seems to have vanished from the universe without a trace, breaking that deep rule completely. One promising idea suggests that everything that ever falls into a black hole gets stamped, in some deeply scrambled form, directly onto the black hole's own boundary, the way a complete picture can sometimes be encoded onto a flat surface, rather than needing to fill an entire space. If that's true, the faint leaking glow might carry the scrambled imprint of everything that ever fell in after all, just in a form far too tangled for anyone to easily untangle and read. Careful recent calculations have begun to support this picture, showing that the total scrambled information carried by the leaking glow follows a pattern more consistent with everything eventually being recoverable, rather than truly and permanently lost forever. This is now considered one of the most important recent results in the ongoing effort to understand black holes properly, even though nobody has a complete picture yet of exactly how the recovery would actually work if you were the one falling in. Whether it will one day be possible to genuinely piece back together everything that ever disappeared into a black hole, or whether some of it truly is gone forever, remains a live and actively debated question, sitting right at the meeting point between gravity's rules and the deeper rules governing tiny particles. Why are black holes so massive so early? The largest black holes, the kind sitting at the very center of entire galaxies, are thought to grow slowly over time by swallowing surrounding gas and by merging with other black holes, gradually packing on more and more weight across billions of years. There is even a natural speed limit to how fast this feeding can happen, since matter falling in too quickly heats up and glows so fiercely that it pushes back against anything trying to fall in any faster, like a crowd getting jammed trying to squeeze through a doorway too quickly. The puzzle is that some of the very earliest galaxies ever spotted, dating back to a time when the universe itself was still remarkably young, already contain black holes so enormous that this slow, steady feeding process shouldn't have had nearly enough time to build them up yet. It's a bit like finding a fully grown oak tree in a forest that, by every other measure, should have only just finished sprouting its very first seedlings. One idea suggests that these early black holes may not have started out as the crushed remains of a single dying star at all, the more typical starting point, but instead formed directly from an enormous, pristine cloud of gas collapsing all at once, skipping the usual slow build-up entirely and starting out already enormous from the very beginning. Another idea suggests that under just the right conditions, especially when a black hole sits inside an unusually dense, gas-rich pocket of the early universe, it may occasionally be able to feed faster than the usual speed limit normally allows, letting it fatten up considerably quicker than the standard slow and steady picture would predict. A third, more speculative idea suggests some of these black holes might have formed almost instantly, from extreme clumps forming in the very first flicker of the universe's existence, long before any stars had even begun to shine, giving them an enormous head start over every other black hole that came afterward. Recent observations have also found some of these early black holes looking unusually heavy compared to the surrounding galaxy they sit inside, hinting that black holes in the early universe might have outpaced the galaxies growing up around them, rather than growing steadily alongside them the way they seem to today. Exactly how these earliest giants managed to grow up so quickly remains an open and actively investigated puzzle. What are white holes? Flip a black hole's rules completely backward, and you get something strange. Instead of a region that nothing can ever escape from, you get a region that nothing can ever enter. Anything trying to approach it would simply be pushed away, while whatever sits inside continuously streams outward. This mirror image object is called a white hole, and it comes directly from the very same equations that describe black holes, almost as if it were their long-lost twin. Despite fitting neatly into the math, almost no scientist believes a white hole could actually form and survive out in the real universe. A real black hole forms through the ordinary and violent collapse of a dying star, a process that naturally produces the swallowing kind of object rather than its gushing opposite. The gushing version only shows up in a much more idealized, perfectly balanced version of the equations, one that doesn't match how anything actually collapses in the messy real world. There's also a serious problem with keeping a white hole stable even if one somehow appeared. The moment even a tiny amount of stray matter or drifting light approached it from outside, which seems almost impossible to avoid in any real universe, that white hole would likely be forced to collapse almost instantly into an ordinary black hole instead, snapping shut before it ever had a real chance to exist. Even so, white holes keep showing up in serious scientific discussions, mostly because of an intriguing possible connection to a black hole's own hidden interior. Some pictures of what might happen deep inside a black hole suggest that whatever gets crushed down at the center doesn't actually vanish, but instead bounces back outward, potentially emerging somewhere else entirely as a gushing white hole on the far side, almost like a tunnel connecting one to the other. Because of the extreme stretching and slowing of time near a black hole, this entire bounce could take an unimaginably long stretch of time to complete. From the perspective of anyone watching from a safe distance outside, no white hole has ever actually been spotted anywhere in the sky, and nothing currently observed requires one to explain it. For now, they remain a fascinating and mathematically valid idea with no confirmed real-world counterpart anywhere in the universe. What happens inside a wormhole? Picture folding a sheet of paper so that two far-apart points touch each other directly, letting something travel between them almost instantly, instead of crawling the long way across the unfolded sheet. A wormhole is the space version of that fold, a hypothetical tunnel connecting two distant points in space, or perhaps even two entirely separate universes, letting something pass between them far more quickly than crossing the ordinary distance ever could. The very first version of this idea, to come directly out of gravity's own equations, turned out to be far too fragile to actually use. It pinches itself shut so quickly that not even a beam of light could make it all the way through before the passage sealed closed behind it, snapping shut faster than anything could ever cross. Keeping a wormhole open long enough for something to actually pass through would require an unusual kind of material, one that pushes space apart instead of pulling it together, the way ordinary matter always does. Nothing like this has ever been found in large, stable amounts anywhere in nature. Tiny, extremely brief flickers of something resembling it have been measured in careful laboratory experiments, but the amount needed to hold open a tunnel large enough to actually travel through appears to be far beyond anything that could ever realistically be gathered or sustained. There's also a fascinating and much stranger idea connecting wormholes to something else entirely. The strange, invisible link that can form between two separate particles no matter how far apart they later travel, where measuring one instantly seems to affect the other. Some physicists suspect that this strange invisible linking in the folded tunnel of a wormhole might actually be two completely different ways of describing the very same underlying connection, just seen from two very different angles. No wormhole of any kind has ever been detected anywhere in space, and nothing currently observed requires one to explain it. If they exist at all beyond the equations describing them, they are most likely to be unimaginably tiny and fantastically unstable, requiring an amount of unusual material and precise engineering far beyond anything achievable with any technology currently imaginable. What are fast radio bursts? Every so often, a radio telescope catches an incredibly brief flash of energy arriving from somewhere impossibly far out in space, lasting only the tiniest fraction of a second, yet carrying more energy in that instant than an entire star produces over several days. These flashes come from galaxies so distant that their light has been traveling toward us for longer than most stars have existed, and for years after they were first noticed, nobody could explain what could possibly produce a flash this brief and this powerful. For a while, some researchers even wondered whether these flashes might simply be a glitch in the equipment rather than a real signal from space, especially after an embarrassing false alarm turned out to be caused by nothing more than a nearby microwave oven being opened partway through its cooking cycle. That particular mystery was eventually cleared up, and the genuine flashes were confirmed to be arriving from far beyond our own galaxy. A major clue arrived once researchers noticed that one particular source kept flashing again and again from the exact same spot in the sky, rather than flashing only once and going silent forever. That single detail ruled out any idea requiring the source to be destroyed the moment it flashed, since something that keeps flashing has to still be there afterward. The leading suspect today is an unusually extreme kind of collapsed star, one wrapped in a magnetic grip far more powerful than anything else known to exist, capable of occasionally releasing a sudden, violent burst of energy through sudden shifts and cracks in its own crust, not unlike how a sudden shift deep underground can trigger an earthquake. This suspicion was strongly reinforced after a burst of this exact kind was caught coming from a known example of this type of collapsed star, sitting right within our own galaxy for the very first time. Even so, not every flash appears to behave the same way, and some researchers suspect there may be more than one kind of source producing them. A dedicated radio telescope built specifically to catch these events has already gathered a huge and steadily growing catalog of flashes, revealing a genuinely varied and only partly understood family of signals, still being pieced together year by year. Why do pulsars spin so fast? When a massive star finally collapses at the end of its life, what's left behind can be an object barely wider than a city, yet packed with as much weight as an entire sun squeezed down into that tiny space. As that collapse happens, whatever spin the star originally had gets concentrated down into a much smaller ball, and the spin speeds up dramatically as a result, the same way a spinning skater whips around faster the moment she pulls her arms in tight against her body. The result is an object spinning around many times every single second, sweeping a tight, narrow beam of energy out across space as it turns, not unlike a lighthouse beam sweeping across the dark. Whenever that narrow beam happens to sweep directly across our own planet, it registers as a steady, rhythmic pulse, ticking away with a regularity so precise that some of these spinning objects rival the best clocks ever built by any engineer. Some of these objects spin remarkably fast right from the moment they form. Others spin fast for a very different reason entirely. They sit closely paired with a neighboring star, slowly pulling material away from that neighbor over a very long stretch of time. As that stolen material spirals inward, it carries momentum along with it, gradually speeding up the spin, the same way water spiraling down a drain speeds up as it gets closer to the center. Over enough time, this slow theft can spin an old, previously slowed down collapsed star back up to blistering speed all over again. These steady, clockwork pulses have proven remarkably useful for entirely different purposes. The very first confirmed planets ever found orbiting a star other than our own Sun were actually discovered by noticing the extremely subtle wobble their gravity caused in one of these ticking beacons rather than by seeing the planets directly at all. Networks of these same ticking objects spread out across the sky and tracked for years have also been used together as an enormous natural detector, picking up the faintest of ripples passing through space itself. The basic reason behind their blistering spin is well understood. What remains more mysterious is the finer detail of what's actually happening deep inside them, including occasional small, sudden speed-ups that still puzzle researchers trying to understand exactly what kind of material makes up their crushed interior. Why are quasars so bright? Some of the most brilliant single points of light ever spotted in the sky turned out, once carefully studied, to sit at truly staggering distances, so far away that their light has been traveling toward us since a time when the universe itself was still remarkably young. Yet despite that enormous distance, they still managed to appear astonishingly bright from here, meaning that whatever was producing that light had to be almost unbelievably powerful, brighter than an entire ordinary galaxy crammed into a space no larger than a solar system. The engine behind this brilliance turns out to be a colossal black hole sitting at a galaxy's center, actively feeding on a swirling disk of gas and dust spiraling slowly inward toward it. As that material spirals closer and closer, friction and churning forces heat it to almost unimaginable temperatures, causing it to blaze with light long before it ever actually crosses into the black hole itself. Turning falling matter into light this way is a remarkably efficient process, far more efficient at releasing energy than even the fiery furnace burning at the heart of an ordinary star. This kind of blazing activity isn't a permanent feature of every giant black hole. It only flares up while there's a steady, generous supply of gas nearby to keep feeding it, and such generous supplies were far more common back when galaxies were still young and full of raw material, colliding and merging with one another much more often than they do today. That's exactly why these blazing beacons tend to be found only at the very greatest distances, corresponding to a much younger and more chaotic era of the universe's history. Our own galaxy's own giant black hole, sitting quietly at its center, is comparatively dim and calm today, simply because it currently lacks a large, steady supply of nearby material to feed on, showing that this fierce blazing behavior is a temporary phase tied to available fuel rather than a permanent property belonging to every giant black hole equally. One remaining puzzle involves just how forcefully this blazing activity can blast gas clear out of its home galaxy entirely, potentially shutting down the galaxy's own ability to form new stars for a very long time afterward. Exactly how strongly and how often this actually happens across different kinds of galaxies remains an active area of ongoing study. What is the great attractor? Our own galaxy, along with an enormous surrounding region of space around it, is quietly gliding through the universe at a startling speed, far faster than the ordinary stretching of space alone could ever explain. Something massive, sitting somewhere out in a particular direction, appeared to be tugging on everything, pulling our galaxy and its neighbors steadily toward it. Tracing exactly where this pull was coming from turned out to be unusually difficult, for an almost comically simple reason. Whatever was doing the pulling happened to sit almost directly behind the thick, dusty disk of our own galaxy, as seen from here, a stretch of sky so cluttered with our galaxy's own stars and dust that it has long been informally nicknamed the zone hidden from ordinary view. Scientists had to rely on other kinds of light that can pass more easily through that dusty haze in order to slowly map out whatever lay hidden behind it. What they eventually found wasn't some single, unusually heavy object at all, but an enormous, previously hidden gathering of galaxies, clustered together behind our own galaxy's obscuring dust, and simply overlooked until observers found the right kind of light to see through the haze. Researchers named this hidden gathering the Great Attractor. Even after finally mapping it out, the pull from this hidden gathering alone still wasn't quite enough to fully account for our galaxy's entire measured speed through space. Continued mapping eventually revealed something even larger lurking farther out behind it, a truly enormous gathering of galaxies that our own galaxy turned out to be only a small part of, with the Great Attractor itself sitting as just one especially dense knot within this much larger structure, rather than being the single final source of the pull all on its own. Even this bigger picture may not be the complete answer. Some of our galaxy's motion may still be nudged along by yet another enormous, even more distant gathering of galaxies sitting even farther away still. Untangling exactly how much of our galaxy's total motion comes from each of these overlapping tugging structures remains a genuinely difficult ongoing puzzle, complicated by that same stubborn curtain of dust still blocking a clear direct view. Why is there a huge cold spot in space? Scattered faintly across the whole sky is the very oldest light in the universe, an ancient afterglow left over from a time not long after everything began, back when the universe first became clear enough for light to travel freely. Across the sky, this ancient light is almost perfectly even in temperature everywhere, but not quite, showing tiny, expected ripples here and there. In one particular patch of sky, though, researchers found something considerably colder and larger than any of the ordinary expected ripples ought to be. An unusually deep and unusually wide dip sitting all on its own. Follow-up observations using more advanced instruments confirmed that this cold patch was real and genuinely unusual, rather than simply being a glitch in the original measurement. One promising explanation points to an enormous, unusually empty stretch of space sitting along that same direction, containing noticeably fewer galaxies than the surrounding regions around it. Ancient light passing through a stretch of space this empty loses a tiny bit of extra energy on its way through, cooling it down very slightly by the time it reaches us, in a way that wouldn't happen quite the same way if space weren't gently stretching apart the whole time that same light was passing through. Researchers did, in fact, find an unusually large, empty stretch sitting roughly in that same direction. Even so, careful calculation suggests that this particular empty stretch, while genuinely real, doesn't appear to be quite big or quite empty enough on its own to fully explain just how deep and how wide the cold patch actually turned out to be, leaving only a partial explanation rather than a complete one. A more cautious explanation suggests the cold patch might simply be an unusually large but ultimately ordinary random fluctuation, the kind of statistical fluke that becomes more likely to turn up somewhere once you search across the entire sky rather than checking just one small area you picked out in advance. A few more unusual and far more speculative explanations have also been proposed, including the idea that the patch might be a leftover scar from an ancient collision with another separate bubble of space entirely, though this idea hasn't gathered much support. For now, most researchers lean toward some mixture of the empty stretch explanation and ordinary statistical chance, though a fully complete and satisfying explanation still hasn't been settled on. Part 3. The Mysteries of Our Solar System. What lies beneath Europa's ice? One of the icy moons circling Jupiter from a distance looks like a smooth, cracked eggshell drifting through space, its surface crisscrossed with long reddish streaks running in every direction. Beneath that frozen shell, scientists believe an entire ocean of liquid water is quietly sloshing around, sealed away from the freezing vacuum above by a thick lid of ice. What keeps that hidden ocean from freezing solid, despite sitting so far from the sun's warmth, is the moon's own uneasy orbit. As it circles its giant host planet, the pull of gravity from that planet and its other neighboring moons squeezes and flexes the little moon over and over, warming its insides through friction. The same way repeatedly bending a piece of metal back and forth will eventually make it warm to the touch. That constant flexing may be enough to keep an ocean liquid beneath the ice indefinitely. The reddish streaks crisscrossing the icy surface hint that this hidden ocean isn't entirely cut off from the surface above it. Whatever material colors those streaks likely rose up from below through cracks in the ice, suggesting some slow exchange happening between the deep hidden ocean and the frozen world above it, and by extension, the empty space beyond that. One especially exciting possibility is that the ocean floor itself might host warm, mineral-rich vents, not unlike the ones found deep in Earth's own oceans, where entire communities of strange creatures thrive without ever needing sunlight, living instead off the heat and chemistry bubbling up from below. If a moon this far from the sun has something similar happening at its own ocean floor, it would mean warmth, liquid water, and useful chemistry might all be present together in one place, 3 of the basic ingredients life is thought to need. Occasional narrow plumes of water vapor have also been spotted shooting up from cracks in the ice, though these sightings have proven difficult to confirm with full certainty. A dedicated spacecraft is now on its way specifically to study this icy moon up close, aiming to measure exactly how thick its icy shell really is, how deep and salty its hidden ocean might be, and whether those narrow plumes are truly real. Whether anything is actually alive down there remains completely unknown, and answering that question will likely take missions built specifically to look for it, once the groundwork has finally been laid. Does Enceladus hide an ocean of life? A tiny, icy moon circling Saturn, small enough that it could comfortably fit inside a mid-sized country, turned out to be one of the most surprisingly active places ever found anywhere in the solar system. Long, cracked stripes near its southern end were found spraying jets of water vapor and ice crystals directly out into space, some of it escaping the moon's weak gravity entirely and drifting off to join one of Saturn's own faint outer rings. A passing spacecraft flew directly through these icy plumes several times, allowing its instruments to taste the spray up close. What it found was salty water, simple chemical building blocks similar to what makes up living things, and, notably, a gas that on Earth is strongly linked to warm, mineral-rich vents bubbling up from an ocean floor. That last discovery hinted strongly that this little moon's rocky core might be undergoing the same kind of warm chemical activity found at the floor of Earth's own deep oceans, providing both heat and useful chemistry to whatever ocean sits above it. Later, even closer analysis of that same spray turned up phosphorus, an element every living thing on Earth absolutely requires, rounding out nearly every basic ingredient scientists generally consider necessary for life as we understand it. This little moon manages to stay warm enough to keep its hidden ocean liquid for the very same reason its icy neighbor does. It gets repeatedly flexed and squeezed by the pull of a nearby moon as it circles Saturn, generating heat through friction deep inside despite its small size, which would otherwise have long since cooled down and gone completely still. Taken together, this makes for a genuinely striking case. Salty water, the right basic chemical ingredients, warm, vent-like activity, and a key nutrient every living thing needs, all found together in the spray from one small, easily overlooked moon, arguably making it one of the most promising places in the entire solar system to search for life, quite possibly rivaling far larger and more famous candidates. What hasn't been found yet is any direct sign of anything actually alive down there. The spacecraft that first tasted the spray wasn't built to search for that kind of evidence specifically, and no follow-up mission built for exactly that purpose has been sent yet, leaving this moon's hidden ocean as a richly promising, but still entirely unconfirmed possibility. Why is Venus so different from Earth? Venus and Earth started out so alike in size and makeup that they're sometimes called twin planets. Yet today, Venus is the hottest planet anywhere in the solar system. Hot enough to melt metal on its surface, wrapped in a crushingly thick blanket of air and topped with clouds made of stinging acid. Something clearly sent these two twins down wildly different paths. The leading explanation points to a runaway heating effect. Both planets likely started out with a fair amount of water and a thicker surrounding blanket of gas, trapping heat close to the surface. Earth, sitting at just the right distance from the Sun, managed to keep its water liquid, letting oceans form. Those oceans slowly soaked up much of the heat-trapping gas surrounding the planet, locking it safely away in rock and keeping the overall warming effect mild and steady for billions of years. Venus, sitting closer to the Sun and soaking up more heat, may never have managed to hold on to stable oceans for very long. Without liquid water around to soak up and lock away that heat-trapping gas, it simply kept piling up in the surrounding air instead, wrapping the whole planet in an ever-thickening blanket that eventually cooked away whatever water might have been there in the first place and cranked the surface temperature up to where it sits today. Venus is also missing something else Earth has, a cracked, shifting outer shell made of separate moving pieces that slowly grind past, crash into, and slide beneath one another over unimaginably long stretches of time. Venus's outer shell instead appears to be one single unbroken layer, with its whole surface looking roughly the same age everywhere, hinting that the entire planet may occasionally resurface itself all at once in a single dramatic event, rather than constantly renewing itself piece by piece the way Earth does. Venus also spins unusually slowly, and in the opposite direction from most other planets, meaning a single sunrise to sunrise day there drags on longer than its entire year. Nobody is certain why. One idea points to an ancient, powerful collision early in the planet's history that could have knocked its spin into reverse. Another suggests its thick blanket of surrounding gas may have gradually dragged and slowed the spin down over a very long stretch of time, all on its own. Where is Planet 9? Way out past the last known planets in our solar system, a handful of small, icy worlds have been found drifting along unusually similar tilted paths, all leaning in roughly the same direction as though something out there were gently herding them into line. That pattern seemed too consistent to be pure coincidence, and it led some astronomers to propose that a large, undiscovered planet might be lurking out in that same distant darkness, its gravity quietly nudging these smaller, icy worlds into their oddly matching paths over a very long stretch of time. If a planet like this really exists, it would circle the Sun on an enormous looping path, taking far longer to complete a single orbit than anyone alive today could ever witness from beginning to end. It would also sit so far away and reflect so little sunlight back toward us that spotting it directly would be extraordinarily difficult, even for the most powerful telescopes currently available. Dedicated searches scanning the skies where this hidden planet ought to be lurking haven't turned up anything conclusive yet, though they have managed to rule out large stretches of sky where it clearly isn't hiding, gradually narrowing down where it could still plausibly be found if it truly exists. Not every astronomer is convinced a single hidden planet is really the right explanation. Some suggest the strange matching tilt might instead come from a broad, disc-shaped scattering of many smaller, icy chunks out there, spread out widely enough that their combined pull could nudge things into line without needing one single large planet responsible for it all. Others have raised a more mundane possibility. Since only a small handful of these distant icy worlds have been found and carefully tracked so far, the apparent pattern in their tilted paths might simply be a trick of which ones happen to be spotted first, rather than reflecting a genuine underlying pattern at all. A newly built telescope, designed specifically to repeatedly scan the entire night sky in extraordinary detail, should turn up a great many more of these distant icy worlds in the coming years, offering a much stronger data set for finally settling whether the tilted pattern is real and giving the search a real shot at spotting this hidden planet directly if it truly is out there waiting to be found. Why does Uranus rotate sideways? Nearly every planet in the solar system spins on a gently tilted axis, similar to how Earth leans just enough to give us changing seasons throughout the year. One planet breaks that pattern dramatically, spinning almost completely on its side, as though it had been knocked clean over and left to keep spinning that way ever since. Its poles end up pointing almost directly toward and away from the Sun at different points along its long, slow orbit, rather than up and down the way most other planets' poles do. This sideways tilt creates a genuinely bizarre pattern of seasons. One pole ends up facing the Sun continuously for an extraordinarily long stretch of time, bathed in unbroken daylight the entire while the opposite pole sits plunged in continuous darkness for that same long stretch, before the whole arrangement slowly swaps around again as the planet continues creeping along its very long orbit. The leading explanation for this dramatic tilt points to an ancient, violent collision, likely occurring very early in the solar system's history, back when many more large, half-formed planets were still drifting around and crashing into one another before eventually settling down into the handful of planets we know today. A single, glancing blow from another sizable world could plausibly have knocked this planet's spin over onto its side without shattering it apart entirely, especially since a planet built mostly of gas and ice, rather than solid rock, can often absorb this kind of violent jolt more gently than a purely rocky world could. Some researchers suspect this same ancient collision might also help explain a few of the planet's other unusual quirks, including why it puts out noticeably less of its own internal heat than its neighboring giant planets do, and why its rings and moons circle it in that same tilted sideways orientation rather than lining up with the rest of the solar system the way most other moons and rings typically do. This distant, sideways spinning planet has only ever been visited up close once, very briefly, by a single passing spacecraft decades ago, meaning almost everything known about it comes from that one brief flyby. Scientists have specifically called for a dedicated new mission to return and study it properly, hoping to finally settle exactly what happened to knock it over so dramatically, though any such mission would take many years just to arrive. What created Saturn's hexagon? Sitting right at the top of Saturn, wrapped around its north pole, is an enormous, strikingly six-sided pattern woven directly into the planet's swirling clouds, wide enough that several planets the size of Earth could comfortably fit inside it. Unlike the more chaotic, constantly shifting weather patterns swirling around most other planets, this six-sided shape has stayed remarkably steady and sharply defined for as long as anyone has been watching it, rotating in place almost as if it were locked directly onto the planet's own spin, rather than drifting independently the way ordinary clouds usually do. Scientists managed to recreate a strikingly similar six-sided pattern inside a simple spinning tank of fluid, right in an ordinary laboratory. When a fast-moving ring of fluid flows around a more slowly turning pool sitting inside it, the boundary between the two can naturally break apart into a series of large, evenly spaced, swirling pockets, arranged all the way around the ring and under just the right spinning conditions. This naturally settles into a six-sided pattern rather than some other number of sides. This suggests Saturn's giant hexagon isn't some strange, one-of-a-kind mystery unique to that one planet, but instead a fairly ordinary and expected result of fast-moving fluid flowing around a more slowly spinning pool, once the exact right conditions line up. Saturn's opposite pole, curiously, shows nothing like this at all, instead swirling into a single, simple, roughly circular storm with a well-defined calm center, much like a hurricane. Exactly why one pole settles into sharp, six-sided order while the other simply swirls into a plain circular storm instead remains only partly understood. A passing spacecraft that studied Saturn closely for many years found that this six-sided pattern reaches surprisingly deep down into the planet's swirling clouds, rather than sitting only right at the very surface, and it even watched the pattern's overall color shift gradually from a cooler blue tone to a warmer golden-brown one as that pole slowly turned from winter into summer over the course of the mission, caused by a gradually thickening haze forming as that pole caught more direct sunlight. Why this pattern has proven so remarkably stable and long-lasting, and exactly how deep down into the planet it truly extends, remain open questions still being pieced together. How did the Moon form? Earth's moon is unusually large compared to the planet it circles, far larger, relative to its host, than almost any other moon found anywhere else in the solar system. That size difference has made explaining exactly how it formed a genuinely tricky puzzle, since most other moons appear to have formed through much gentler, more ordinary processes that don't easily produce a moon quite this large. The leading explanation pictures a dramatic ancient collision. Early in Earth's history, not long after our planet had mostly finished forming, a smaller, roughly Mars-sized world is thought to have slammed into it at a glancing angle. That impact would have blasted an enormous amount of molten and vaporized rock, torn from both Earth's own outer layers and from the crashing world itself, out into orbit around our planet. That scattered debris likely swirled together and clumped up remarkably quickly, cooling and solidifying into the moon we see hanging in our sky today. Rock samples carried back from the moon's surface show a striking chemical resemblance to Earth's own outer layers, closer than a simple even blend of both worlds' material would normally be expected to produce, which puzzled scientists for a long time. More recent, more detailed models suggest the original collision may have been even more violent than first assumed, vaporizing so much material from both worlds at once that it briefly formed an enormous, blisteringly hot, spinning cloud of vaporized rock surrounding Earth entirely, allowing material from both worlds to mix together far more thoroughly before finally cooling down, with the moon condensing out of the cooler outer portion of that mixed cloud and Earth reforming out of what settled back down at the center. This dramatic origin left a lasting mark on Earth itself. Our moon's steady gravity is thought to help keep Earth's tilt gently steady over very long stretches of time, rather than wobbling unpredictably the way a planet without a large moon might. A steadier tilt likely helped keep Earth's climate more stable over the vast stretches of time life needed to slowly develop and diversify, though exactly how essential a large, steadying moon really is for a planet to support life remains an open question still being studied. Why is Mercury so dense? The smallest planet closest to the Sun turns out to be unusually heavy for its size, once you account for how tightly its own gravity naturally squeezes it together. That extra weight points to something surprising hidden underneath its surface. An enormous metallic core taking up far more of the planet's total size than the core of any other rocky planet in the solar system, wrapped in only a thin outer shell of ordinary rock, almost like an oversized metal ball, barely dusted with a light coating of stone. A few different explanations have been proposed for how this little planet ended up so lopsided in its makeup, and figuring out which one is correct has proven surprisingly difficult. One idea suggests the planet originally formed with a much more ordinary mix of rock and metal, similar to its rocky neighbors, but that an early violent collision with another passing world stripped away much of its outer rocky shell, leaving the dense metal core behind as a far larger share of what remained. A second idea suggests that the intense heat and fierce outpouring of energy from the young, much more active sun nearby may have slowly boiled away and blown off much of the planet's lighter rocky material directly, without needing any violent collision at all, simply by sitting so close to a much fiercer young sun for a very long stretch of time. A third idea suggests the planet may simply have formed in a patch of the swirling material surrounding the young sun that happened to be especially rich in metal to begin with, needing no dramatic later stripping event of any kind to explain its unusual makeup. A spacecraft that spent several years circling this little planet found that its surface still holds on to certain delicate elements that should have easily boiled away if either the violent collision or the fierce sunlight explanation were fully correct, complicating both of those ideas somewhat, and lending a bit more support to the simple idea that the planet was just born unusually metal-rich to begin with. A newer mission, still years away from arrival, is expected to gather far more detailed evidence and finally help settle which explanation, or which mix of explanations, is truly correct. Could Mars have once supported civilization? Long ago, Mars looked far different than the cold, dusty, and dry world it is today. Dried-out river channels, ancient lake beds, and what appears to be the remains of a large, long-vanished ocean have all been spotted carved into its surface, and rolling robotic explorers sent to examine its rocks up close have found minerals that, here on Earth, only ever form after long, sustained exposure to flowing or standing liquid water. This wetter, warmer chapter of Mars's history unfolded early on, not too terribly long, in cosmic terms, after the planet itself first formed, and it may have offered conditions loosely comparable, in some ways, to the young Earth around the same time life is believed to have first taken hold here. That resemblance is exactly why Mars is considered one of the most promising places to search for traces of very simple, ancient microscopic life, and why recent rolling explorers have been carefully collecting rock samples, specifically meant to be brought back to Earth someday for far more thorough laboratory study than can ever be done directly on the Martian surface itself. It's worth being clear about exactly what this evidence does and doesn't suggest. Nothing found so far hints at any advanced civilization, any technology, or any complex, many-celled form of life ever having existed there. The scientific interest lies specifically in the possibility of very simple, single-celled life, since Mars's brief wet chapter likely wasn't long enough, or stable enough, to allow anything resembling complex technological life to develop, based on how long that kind of complexity took to develop here on Earth, even under far steadier conditions. The reason Mars lost its early warmth while Earth kept its own climate mild and steady comes down largely to size. Mars is considerably smaller than Earth, and a smaller world cools down and loses its protective inner heat much faster. Evidence suggests Mars once had a protective magnetic shield surrounding it, much like Earth's own, but that shield shut off early on as its smaller core cooled and hardened. Without that shield, the endless stream of energy flowing outward from the Sun gradually stripped away Mars's once thicker blanket of surrounding air, leaving behind the thin, cold, and dry world we see today. Why are there so many asteroids? Scattered across a wide, donut-shaped band of space between two of the solar system's larger planets sits an enormous swarm of rocky and metallic chunks, ranging from tiny pebbles to a handful of much larger bodies, together making up the largest collection of leftover rubble anywhere in the inner solar system. Despite how crowded this band sounds, if every single piece of it were gathered together and weighed, the whole collection would still add up to only a small fraction of the weight of our own moon, with most of that weight concentrated in just a few of the largest chunks. For a long time, a popular but ultimately mistaken idea suggested this rubble might be the shattered remains of an entire planet that once existed there and was somehow destroyed. That picture doesn't hold up, since the whole collection is simply far too light to have ever been a proper planet in the first place, and the many different chunks show far too much variety in their makeup to have all come from a single shattered world. The explanation that fits the evidence far better is that this rubble represents leftover building material from the solar system's earliest days, material that never managed to properly clump together into a full planet in the first place. The overwhelming gravity of the enormous planet sitting just beyond this band appears to be responsible for constantly stirring things up, speeding up collisions between the smaller chunks enough that they tended to shatter each other apart about as often as they managed to stick together, unlike material elsewhere in the young solar system that was left calm enough to steadily clump together into full planets over time. That same giant planet's gravity has also been quietly sweeping certain chunks out of specific orbits ever since, either flinging them out of the band entirely or sending them tumbling inward toward the Sun. Spacecraft that have visited these rocky chunks up close have found a genuinely varied bunch, ranging from ancient, mostly unchanged chunks that have barely been altered since the solar system's very earliest days, to larger bodies that managed to partly melt and separate into a metal center and rocky outer layer before their development was interrupted early on. One of the largest of these chunks has even shown surprising hints of leftover salty liquid still lurking somewhere beneath its surface today. Part 4. The Mystery of Life. How did life begin? Somewhere in Earth's early history, ordinary chemistry crossed a line and became something else entirely. A system that could copy itself and pass its own instructions along. Nobody witnessed this happen, but scientists have spent decades trying to piece together how simple, lifeless ingredients might have arranged themselves into something capable of living and reproducing on its own. One classic experiment sealed a mix of simple gases believed to resemble Earth's early air inside a glass container and repeatedly sparked it with the electricity to mimic lightning. Within just a week, some of the basic building blocks used in every living thing had formed on their own, showing that the raw ingredients of life could arise from ordinary chemistry without any living thing needing to make them first. One leading idea for where the first true spark of life might have actually happened points to warm, mineral-rich vents bubbling up from the ocean floor. Tiny, naturally occurring pockets within the rock at these vents create small chemical and electrical differences across their thin walls, strikingly similar to the tiny electrical differences every living cell today maintains across its own outer wall in order to stay alive, almost like nature had already built the scaffolding needed for the very first step before life itself ever had to build that scaffolding on its own. A different idea points instead to shallow puddles sitting out in open sunlight on land, repeatedly drying out and refilling with rain. That steady cycle of wetting, drying, and sunlight exposure has been shown, in careful laboratory experiments, to stitch together several of the same basic building blocks life still relies on today, in a way that proved surprisingly difficult to reproduce, using only the underwater vent setting instead. Central to many of these ideas is the belief that a single flexible molecule, capable of both storing simple instructions and doing useful chemical work all on its own, came before the more specialized system of instructions and workers that every living cell relies on today, with that older, more flexible molecule eventually handing off each of its two jobs to its own, more specialized successor once life had gotten properly underway. Exactly how that first flexible molecule managed to assemble itself from simple raw ingredients in the first place remains the biggest missing piece of the whole puzzle, and one of the most actively studied questions in all of science. What was the first cell? Every living thing alive today, from the smallest microbe to the largest whale, traces its family tree back to one shared ancestor sitting far back in the deep, distant past. This shared ancestor wasn't the very first living thing to ever exist, since even simpler forms almost certainly appeared before it and then vanished without leaving any descendants behind. Instead, it's simply the most recent point where every surviving branch of life on Earth today can be traced back to meeting up in one single place. Careful comparison of genes shared across the very oldest and simplest branches of life has revealed that this shared ancestor was already a fairly capable little organism, equipped with working tools for harnessing energy from simple gases, an early system for building up more complex chemicals, and machinery for reading instructions and building proteins strikingly similar to the machinery every living cell still relies on today. In other words, this ancestor was already carrying most of life's essential toolkit, even if a simpler version of it, rather than being some barely formed, half-finished scrap of chemistry. Clues buried within those same shared genes also hint that this ancestor likely lived somewhere warm, closely matching the kind of environment found around deep, mineral-rich ocean vents, lending some further support to the vent-based origin story discussed in the previous topic. One especially interesting open question is whether this ancestor already had a proper outer wall sealing it off from the world, the way every living cell does today, or whether it was instead a looser, less clearly bounded pocket of chemistry, tucked safely inside naturally occurring mineral pores, rather than wrapped in its own self-made covering. If life's very earliest chemistry got its start tucked safely inside these ready-made mineral pockets, it would neatly explain how something as complicated as a working cell wall could eventually develop, without needing a fully working cell wall to already exist beforehand just to get that development started in the first place. No direct physical trace of this ancestor has ever been found, or is ever likely to be found, since anything that old would have been ground up and recycled by Earth's own restless geology many times over by now. Almost everything known about it comes not from digging up fossils, but from carefully comparing the shared genetic fingerprints still carried by every living thing alive today. Why did DNA form the way it did? Every living thing carries its instructions written along a long twisted ladder made of two intertwined strands, with each rung along that ladder built from one of 4 different chemical letters, always pairing up with its exact matching partner across from it. This elegant twisted design turns out to be extremely well suited to the specific job it needs to do. Because the ladder is built from 2 matching strands rather than just one, each strand can act as a template for rebuilding its exact missing partner whenever the 2 need to be copied, meaning the very shape of the molecule already carries a natural, built-in method for duplicating itself accurately, almost like a zipper that can be pulled apart, and then rebuilt piece by matching piece along either half. The particular building material chosen for the ladder's backbone also happens to matter a great deal. A slightly different, closely related building material, missing one small piece present in this version, turns out to be noticeably more fragile and prone to falling apart, making it far better suited for carrying short-term, disposable instructions rather than serving as a stable, long-lasting archive. The sturdier version used for permanent storage benefits directly from lacking that same fragile piece, letting it hold on to its instructions reliably for a very long time. It's also worth noting that using exactly 4 different chemical letters isn't some unavoidable law of chemistry. Scientists have successfully built working artificial versions using additional letters beyond the usual 4, even coaxing living microbes to copy and pass along this expanded alphabet across generations, showing that 4 letters is simply how life happened to settle early on, rather than the only workable option chemistry could have ever produced. The reason the 4 familiar letters always pair up the exact same specific way with one another comes down to their particular shapes, fitting together snugly and consistently, keeping the width of the twisted ladder perfectly even no matter which pair happens to sit at any given rung, a consistency that matters enormously for keeping the whole structure stable and easy for a cell's machinery to read, copy, and repair reliably. This whole elegant design likely arrived somewhat late in life's early history, built as a sturdier, more specialized upgrade once life had already been running for a good while on a simpler, more flexible molecule instead. Why is water essential for life? Every single living thing ever discovered depends completely on liquid water, and this isn't simply a leftover habit from early evolutionary history. Water carries a genuinely unusual set of properties that make it remarkably well suited for hosting life's chemistry. Because each tiny water molecule carries a slight pull on one end and a slight push on the other, it's remarkably good at surrounding and pulling apart all sorts of other substances, letting a huge variety of different ingredients dissolve and mix freely together, and allowing chemical reactions between them to happen efficiently in a shared liquid soup, rather than requiring solid substances to somehow react directly with one another the slow and clumsy way. Water also does something genuinely strange compared to almost every other common substance. It becomes lighter, not heavier, the moment it freezes solid, which is why ice floats on top of liquid water instead of sinking to the bottom. This matters enormously for anything living in a lake or ocean that freezes over during a cold spell, since a floating layer of ice on top acts like an insulating lid, letting liquid water and whatever lives within it keep going safely underneath, rather than the whole body of water freezing solid from the bottom up and destroying everything living inside it. Water can also soak up or release a fairly large amount of heat while barely changing its own temperature at all, giving anything built mostly from water, oceans, and living cells alike a kind of natural cushion against sudden damaging swings in temperature. The same molecular quirk responsible for ice floating also gives liquid water an unusually strong tendency to cling to itself and to other surfaces, a property plants directly rely on to draw water upward from their roots all the way to their highest leaves, fighting against gravity the whole way, purely through water's own natural tendency to cling tightly together and to the narrow channels it's traveling through. Because water's suitability for hosting life's chemistry is so well understood, the search for life beyond Earth leans very heavily on simply following wherever liquid water might be found. Some researchers have wondered whether an entirely different liquid, such as the strange extremely cold liquid found pooling on the surface of one of Saturn's moons, might support some completely different kind of chemistry capable of supporting life, though this remains a purely theoretical idea with no confirmed example anywhere, leaving water as the only liquid ever actually confirmed to host real living things. Why is life carbon-based? Every living thing is built around a single element serving as its basic structural backbone. And that element's real superpower lies in how many stable connections it can form at once, including long chains, branching structures, and rings, both with other atoms and with more of its own kind, giving rise to an enormous variety of possible shapes and structures unmatched by almost any other element. A close chemical neighbor, sitting just below this one on the periodic table and sharing a similar ability to form four connections, is often suggested as a possible alternative building block for some other kind of life. But this neighboring element's connections, especially chains built entirely from more of itself, tend to be considerably less sturdy and less varied under the kinds of everyday conditions found on a planet's surface. The most common naturally occurring version of this alternative, found abundantly in ordinary sand, is a hard, chemically stubborn solid. Quite unlike the airy, easily available gas its carbon equivalent forms instead, a gas plants happily breathe in and use directly to build themselves. There's also a practical plumbing problem facing any hypothetical life built from this alternative element. Its typical waste product would come out as a solid rather than a gas, leaving any such creature with the awkward and seemingly unsolvable challenge of somehow needing to expel solid mineral waste from its body, rather than simply breathing it out effortlessly as carbon-based life does. Carbon also happens to be forged in enormous quantities inside stars, making it one of the most naturally abundant elements scattered throughout the entire universe, meaning any planet built from a fairly typical mix of cosmic ingredients should have plenty of it readily available to work with. Even with all these clear practical advantages, scientists studying the possibility of life elsewhere remain appropriately cautious about assuming carbon is the only element capable of building something alive, given that everything currently known about life comes from studying exactly one confirmed example. It remains at least conceivable that under conditions dramatically different from anything found in our own solar system, some other kind of chemistry not yet seriously considered could support its own kind of living complexity, though nothing proposed so far comes close to matching carbon's proven versatility, sturdiness, and sheer natural abundance. Did life begin more than once? Every living thing studied so far, from the tiniest microbe to the largest whale, shares the same underlying chemical blueprint, the same basic set of instructions, the same small library of building blocks, and the same overall method for turning instructions into working parts. This deep shared similarity is the strongest evidence that everything alive today descends from one single shared ancestor. But sharing one common ancestor today doesn't necessarily mean life could only have ever sparked into being exactly once. It remains entirely possible that life sparked into being independently more than once on the early Earth, through the same kind of chemistry happening in different places or at different times, but that only one of these separate sparks ever managed to survive, spread, and thrive long enough to leave any descendants still around today, quietly outcompeting or simply outlasting any other separate spark that may have fizzled out and vanished without a trace, especially since Earth's surface has been so thoroughly reshaped and recycled since those earliest days that almost no direct evidence from that period survives regardless. This raises an intriguing possibility. If life really did spark into being more than once, could some entirely separate, independently arisen form of microscopic life still be quietly surviving somewhere today, right alongside all the familiar life we already know, simply going unnoticed because the tools scientists normally use to search for and grow living things are specifically built around detecting familiar life's own particular chemistry, and might easily overlook something built along fundamentally different chemical lines. Some researchers have specifically searched unusual, extreme environments for exactly this kind of hidden, independently arisen life, reasoning that such places might be more likely to have sheltered a separate lineage that never had to directly compete with familiar life for the same resources. Nothing of the sort has been confirmed so far, though the search itself remains a genuinely difficult one. A related and equally curious puzzle involves handedness. Nearly every building block used inside living things consistently favors one particular mirror image version over its opposite twin, even though ordinary non-living chemistry usually produces an even 50-50 mix of both versions when left to its own devices. This consistent handedness across all known life is generally thought to reflect a chance early decision made once, long ago, by whatever system first managed to start copying itself successfully, which then carried that same one-sided preference forward into everything descended from it ever since. Could life exist without DNA? As discussed in an earlier topic, most researchers already believe life very likely got its start using a simpler, more flexible molecule long before the familiar twisted double ladder came along later as a sturdier upgrade. That alone strongly suggests life without today's familiar genetic material isn't just a hypothetical curiosity, but very probably an actual, real chapter that every living thing alive today has already passed through in its own deep history. Chemists have gone even further, successfully building several entirely artificial genetic materials from scratch in the laboratory, using different backbone chemistry than either of life's two familiar molecules, while still managing to encode instructions through matching pairs and getting copied under careful laboratory conditions. This shows that today's familiar genetic material isn't the only possible chemical solution capable of reliably storing and passing along instructions. Some careful laboratory work has even suggested that certain of these alternative backbone chemistries might actually have been easier to stumble upon through simple early chemistry than the more familiar, flexible molecule researchers usually assume came first, raising the intriguing possibility that life's very earliest history might include not just one simpler chapter before today's familiar genetic material, but possibly an even earlier chapter still, using something entirely different again. A few researchers have gone even further still, wondering whether instructions might once have been carried by something completely outside the realm of familiar chemistry altogether, such as tiny mineral crystals capable of replicating their own particular pattern of imperfections as they slowly grow and occasionally break apart into new seed crystals, potentially even providing the very first scaffolding that early, more familiar genetic chemistry eventually assembled itself upon. This remains a much more speculative idea, without the same kind of laboratory support as the alternative genetic materials described above. Taken together, this body of work suggests that if life exists somewhere else entirely, having started under very different conditions than early Earth, it could plausibly be built around an entirely different genetic material altogether, so long as it manages to reliably store instructions and pass them along with reasonable accuracy across generations. So far, though, every confirmed example of real, living, evolving life still relies on one of life's two familiar genetic molecules, leaving every other possibility as an interesting but so far entirely unconfirmed idea. Why did complex life suddenly explode? For an enormous stretch of time after life first appeared on Earth, nearly everything alive remained simple and single-celled, with nothing resembling an animal, plant, or any other complicated many-celled creature anywhere to be found. Then, eventually, complexity took off dramatically, with a huge burst of elaborate new life forms appearing in a comparatively short stretch of time. Before that dramatic burst could even begin, though, an earlier and arguably even more important step had to happen first: the appearance of a more sophisticated kind of cell, one built with a distinct control center and other internal working parts, rather than the simpler, more bare-bones design used by earlier life. Every complicated living thing today, from the smallest mushroom to the largest whale, descends from this more sophisticated kind of cell, rather than from its simpler ancestors directly. The leading explanation for how this more sophisticated cell came about involves one simple cell swallowing up a separate, smaller one instead of digesting it, with the swallowed cell surviving inside its new host and eventually settling into a permanent, mutually beneficial partnership. becoming a small, specialized power-generating structure tucked inside its host from then on. Strong hints supporting this story include the fact that these tiny, power-generating structures still carry their own small, separate loop of instructions, distinct from the rest of the cell's main library and structurally resembling the instructions found in simpler, independent cells rather than the host cell's own more elaborate library. This new, more sophisticated cell design turned out to be a crucial stepping stone toward complex life, largely because it unlocked a dramatically larger energy supply than a simpler cell could ever manage alone. A cell packed full of its own small internal power generators can scale up its total energy output as it grows larger. In a way, a simpler cell relying only on its own outer edge for energy production simply cannot match, providing exactly the kind of energy budget that larger, more complicated and more specialized living structures eventually came to depend on. Notably, this crucial upgrade appeared long before the later dramatic burst of complex life took off, showing that having the right cellular upgrade wasn't enough on its own to immediately trigger an explosion of complexity, and that several further ingredients, discussed in the next topic, were still needed before that explosion of complex life could finally get properly underway. What caused the Cambrian explosion? At a certain point deep in Earth's ancient past, following an almost impossibly long stretch of time in which life remained mostly simple, a burst of dazzling variety suddenly appeared in the fossil record, with something resembling nearly every major modern animal body type showing up within a comparatively short stretch of geological time. An especially well-preserved fossil site, tucked away in a remote mountain range, later gave scientists an unusually clear window into just how strange and varied this early explosion of animal life truly was, including several bizarre body shapes with no obvious modern equivalent. No single explanation fully accounts for why this burst happened when it did, and most researchers now suspect several separate factors lined up together around the same stretch of time. One major factor involves a meaningful rise in the amount of breathable oxygen filling the air and oceans right before this burst took off, since active, complicated animal life demands considerably more oxygen to fuel itself than simpler, earlier life forms ever needed. And this rising oxygen supply may have finally lifted a long-standing barrier that had been holding animal complexity back until then. A second major factor points to the sudden arrival of proper eyesight. Once the very first animals evolved sharp, image-forming eyes, active hunting became possible for the very first time, kicking off an evolutionary arms race between hunters and their prey, with prey species rapidly evolving defenses like tough shells and quick escapes, while hunters kept pace by evolving sharper senses and better ways to catch them, together driving a rapid burst of new body shapes and abilities on both sides of this brand-new predator and prey relationship. A third factor involves a shift in the underlying genetic toolkit controlling how a developing embryo builds its own overall body plan, with small tweaks to this shared toolkit capable of producing large coordinated changes to an animal's overall shape, potentially opening the door to a much wider range of workable new body designs once this flexible toolkit first evolved. A fourth factor involves the appearance of hard shells and skeletons across many separate animal lineages around this same time, likely driven partly by changing ocean chemistry and partly by that same predator pressure, with the added side effect of dramatically improving how well these creatures happen to fossilize compared to the soft-bodied life that came just before them. Why did evolution produce consciousness? There's a meaningful difference between an animal simply reacting cleverly to its surroundings and an animal actually experiencing anything at all while it does so, having some kind of genuine inner feeling accompanying its behavior rather than just carrying it out automatically. Explaining why evolution would bother producing that inner feeling on top of whatever clever behavior already gets the practical job done turns out to be a much trickier puzzle than simply explaining clever behavior on its own. Evolution generally only keeps traits around if they provide some kind of real advantage, whether directly or as an unavoidable side effect of some other advantage. That raises an awkward question for inner experience specifically. What practical advantage does the actual felt quality of an experience provide, above and beyond whatever advantage the underlying clever behavior it accompanies was already providing on its own. One leading idea suggests that having some sort of inner experience helps an animal bring together information streaming in from many different senses and thought processes into one single unified picture of what's happening around it right now, allowing far more flexible and well-informed decisions than if each sense and thought process worked away separately without ever properly talking to one another. A closely related idea pictures conscious experience as something like a shared stage or broadcast system inside the brain, making certain pieces of information broadly available to many different specialized mental processes all at once, rather than keeping that information locked away and useful to only one narrow process at a time, potentially allowing far more flexible responses to brand new situations that don't neatly match any single one of the brain's pre-built automatic routines. A separate and especially thorny puzzle asks why any of this information processing should feel like anything at all from the inside, rather than simply happening in the dark, with all the same clever behavior playing out exactly the same way, but with absolutely no accompanying inner experience whatsoever. Some researchers consider this deeper puzzle a genuine and possibly permanent mystery, standing apart from ordinary scientific explanation. Others argue that once every underlying mental process is fully mapped out and understood in complete detail, this seemingly separate mystery will simply dissolve away on its own, with nothing further left over still needing to be explained. This basic disagreement remains entirely unresolved and sits right at the very center of the whole ongoing effort to understand consciousness scientifically. Why do we dream? Somewhere in the depths of sleep, the eyes begin darting rapidly back and forth beneath closed lids, and the brain lights up almost as busily as it does while wide awake, even though the body itself lies almost completely still, its muscles gently locked in place. This is the stage of sleep where dreaming runs at its most vivid, growing longer and stranger as the night wears on. Nobody has settled on a single, complete explanation for why dreaming happens at all, though several thoughtful ideas have gathered real supporting evidence. One idea suggests dreams are simply what happens when the thinking part of the brain tries to make sense of a jumble of essentially random signals firing away deeper down, weaving those stray sparks into something resembling a story, the same way it naturally weaves a story out of real sensory information during ordinary waking life. A second idea suggests dreaming lets the brain safely rehearse how to handle danger, tucked away inside an imagined scenario rather than a real one, which would help explain why dreams, and especially nightmares, so often involve threatening or unsettling situations far more often than an ordinary, comparatively safe waking life actually involves. A third idea ties dreaming closely to memory. This stage of sleep appears to help settle and strengthen freshly learned information, weaving new experiences together with older ones already tucked away, and people who get proper sleep, especially this particular dreaming stage, tend to perform noticeably better afterward on tasks involving memory and creative problem-solving compared to people who were kept awake instead. A related idea points to the body's own stillness during this stage as a clue. The same brain circuits that keep muscles locked in place during vivid dreaming may exist specifically to let the brain safely rehearse and strengthen movement-related pathways without the body actually moving along with them, a hypothesis supported by a rare condition in which that stillness fails, causing people to physically act out whatever they happen to be dreaming, sometimes quite energetically. Most researchers now suspect dreaming probably serves several of these purposes all at once, rather than any single one alone fully explaining it, weaving together memory, emotion, and rehearsal every single night in ways still being carefully studied and pieced together. Why do we sleep? Nearly every creature with any kind of proper nervous system spends some regular stretch of its life in a deep, restful state, even though that stretch leaves it far less aware of danger and unable to hunt or gather food the whole while. Something about sleep must be valuable enough to be worth that very real risk, and researchers have found several genuinely convincing reasons why. One major reason involves cleaning house. While the body rests, a quiet drainage system tucked around the brain becomes noticeably more active, flushing away waste products that build up during a busy day of thinking, including certain waste linked to serious problems later in life if it's ever allowed to pile up unchecked. The brain appears to need this restful downtime specifically to keep its own housekeeping running properly. A second major reason ties directly back to memory, as discussed in the previous topic. Getting proper rest, especially the deeper resting stages, helps settle freshly learned information into more lasting storage, with well-rested people consistently performing better on memory and learning tasks than people who were kept awake instead. A third reason involves simple energy savings. Body temperature and overall energy use both drop noticeably during rest, which may have mattered a great deal to smaller, faster-burning ancestors living in times when a reliable meal wasn't always guaranteed, even if the energy savings themselves seem fairly modest for us today. A fourth reason involves the body's own defenses. Going without proper rest has been shown to noticeably weaken the body's ability to fight off illness and respond properly to vaccines, suggesting that rest plays some direct supporting role in keeping the body's natural defenses working properly. Just how essential rest truly is becomes starkly clear in a rare and tragic condition where a person gradually loses the ability to sleep at all due to specific damage deep within the brain. Without any restful sleep left at all, the body's health steadily breaks down across every system at once, and the condition proves fatal within a fairly short span of time, offering the clearest possible evidence that rest isn't simply a pleasant habit, but something the body cannot survive very long without. Why do we yawn? A yawn, that deep, jaw-stretching breath followed by a slower exhale, shows up not just in people, but across an enormous range of animals, including birds, reptiles, and even fish, suggesting it's an old, deeply rooted behavior, rather than something unique to any one kind of creature. Even so, figuring out exactly why it happens has proven surprisingly tricky. An old and once widely believed idea suggested yawning helps pull in extra oxygen or push out stale air, based on the simple observation that people often yawn when they seem tired or worn out. Careful testing has directly challenged this idea, though, since deliberately changing someone's oxygen or stale air levels through controlled breathing doesn't actually change how often they yawn at all, undercutting the whole idea fairly directly. A better supported idea suggests yawning helps cool the brain down. Taking in a big gulp of outside air, combined with the stretching and extra blood flow that happens across the face and neck during a yawn, may help draw heat away from the brain. Supporting this, yawning tends to happen more often when the brain or body runs a bit warm, and pressing something cool against the forehead has been shown to noticeably cut down on yawning, while something warm tends to bring on more of it. There's also the strange and very familiar habit of catching a yawn just from watching, hearing, or even simply reading about someone else yawning nearby, a pattern seen not only in people but also in some animals that live in close social groups. This kind of contagious yawning appears closely tied to social bonding, since people tend to catch yawns far more easily from close family and friends than from complete strangers, and people who generally struggle to read others' feelings tend to catch yawns less easily as well. Notably, young children don't usually start catching yawns from others until they're old enough to properly understand that other people have their own separate thoughts and feelings, a milestone that tends to arrive around the same age in most children. Children who experience more difficulty with that particular kind of social understanding also tend to catch yawns less often, offering a further hint tying contagious yawning closely to our broader social wiring. Why do we age? Aging is the slow, steady wearing down of the body's own inner workings over the course of a lifetime, and rather than having one single cause, it seems to arise from several separate processes all quietly chipping away at the body together, each one contributing its own piece to the overall picture. One major process involves the protective caps sitting at the very ends of the body's long, coiled instruction strands, which grow slightly shorter every single time a cell divides and copies itself, since the copying process can never quite reach all the way to the very tip. Once these caps wear down past a certain point, the cell generally stops dividing altogether, or in some cases shuts itself down entirely, rather than continuing to divide with worn-down, less reliable instructions. A second major process involves cells that have stopped dividing but haven't shut down completely, lingering around instead and actively releasing chemical signals that stir up low-level irritation in the surrounding tissue, and can even nudge nearby healthy cells into the same worn-down, lingering state. Rather than being harmless leftovers, these lingering cells appear to actively speed up aging in the tissue surrounding them. A third major process involves ordinary wear and tear from the body's own everyday energy production, which naturally throws off a steady trickle of reactive byproducts capable of gradually damaging nearby proteins and other important cell parts faster than the body's own repair systems can always keep up with. A fourth major process involves subtle chemical tags attached to the body's long coiled instruction strands, controlling which particular instructions get used at any given time without changing the underlying instructions themselves. These tags shift in a strikingly reliable, clock-like pattern as the years go by, precise enough that a lab can estimate someone's biological age fairly accurately just from studying this pattern alone. And experiments resetting these same tags in aging animals have managed to visibly reverse several signs of aging and modestly extend how long those animals lived afterward. None of these four processes acts entirely alone. Aging appears to emerge from all of them compounding together over time, and much of today's research focuses on whether directly targeting one or more of these underlying processes, rather than simply treating age-related illness after it appears, could meaningfully slow the whole process down. Why can't humans regrow limbs? Certain animals can regrow an entire missing body part almost as good as new, including a small water-dwelling salamander often studied specifically for this remarkable talent, capable of regrowing a fully working leg, complete with bone, muscle, and skin, correctly shaped and properly connected, within just a matter of weeks. This little salamander's regrowth begins with cells right around the wound quietly stepping backward in their own development, temporarily forgetting their specialized job and reverting to a much more flexible, blank slate state, not unlike the very earliest cells found in a developing embryo. This flexible clump of cells then multiplies and gradually respecializes back into every different tissue type needed to properly rebuild the missing limb, following many of the same instructions originally used to build that same limb the first time around, back when the animal was still developing inside its egg. People, and mammals more broadly, keep only a much more limited trace of this same regrowing talent. Young children can sometimes partly regrow the very tip of a lost fingertip, and the liver can regenerate a fair amount of lost tissue after injury, though through a somewhat different process, and without regrowing its original overall shape, simply restoring working tissue in a rougher form instead. The leading explanation for why mammals lost this remarkable talent points to an uncomfortable trade-off. The very same flexible, backward-stepping cell behavior that lets a salamander regrow a limb closely resembles the kind of runaway, unchecked cell growth seen in cancerous tumors. Mammals, being generally larger, warmer, and longer-lived than a small salamander, likely face a much higher lifetime risk from cancer and may have evolved much stricter internal safeguards specifically against this kind of flexible cell behavior as a result, with losing the ability to regrow limbs being an unfortunate side effect of gaining those stronger safeguards. Mammals also tend to seal wounds quickly using tough fibrous scar tissue rather than this slower, carefully rebuilt regrowth, trading a properly rebuilt limb for a faster, safer seal against infection and blood loss instead. Very young mammals show a bit more of the older regrowing talent than adults do, hinting that some of the underlying instructions may still be tucked away quietly rather than being gone completely. An insight now driving hopeful early research into someday safely coaxing at least some of that old talent back out. Why does placebo work? Give someone a treatment that has no active medicine in it whatsoever, and tell them it should help. And remarkably often, They genuinely do feel better afterward, sometimes even showing real, measurable changes inside the body, purely from expecting the treatment to work. This effect shows up so reliably that any new medicine being tested has to prove it works noticeably better than this expectation-driven improvement before it can be considered genuinely effective at all. The clearest picture of how this works comes from studying pain relief specifically. Believing a treatment will ease pain appears to trigger the body's own natural pain relief chemistry, the very same system targeted by real pain medication, and blocking that natural system with a separate drug has been shown to wipe out much of the relief people would otherwise feel from a fake treatment, offering strong evidence that this isn't just wishful thinking, but a real, measurable chemical response happening inside the body. Brain scans back this up further, showing that a fake treatment given for pain relief measurably calms down activity in the very same brain regions that process pain signals, in a pattern closely resembling what a real pain medication produces, rather than the person simply describing their pain differently afterward without anything actually changing underneath. The specific ritual surrounding how a treatment gets given also seems to genuinely matter. Larger fake pills tend to work better than smaller ones. Fake injections tend to work better than fake pills, and treatments that seem more expensive or come packaged more elaborately tend to work noticeably better still, all suggesting that a person's expectations, shaped heavily by these small surrounding details, play a very real and direct role in how strongly their body actually responds. Perhaps the most surprising finding of all comes from cases where people are told, honestly and directly, that the pill they're being given contains absolutely nothing at all, and still, a good number of them go on to feel noticeably better afterward anyway. This suggests the effect doesn't strictly require anyone to be fooled, and may instead depend more on the broader sense of care and attention surrounding the whole treatment process itself, rather than purely on believing a real medicine is involved. Why does pain exist? Pain serves a clear and vital job. It grabs attention immediately and forcefully, pushing a person to pull away from whatever is causing harm, and to avoid similar harm afterward, protecting the body both in that very moment and through everything learned from the experience going forward. The clearest proof of just how essential pain really is comes from a rare condition in which someone is born completely unable to feel any physical pain at all, due to a specific inherited difference affecting how pain signals travel along the body's nerves. Rather than living free of suffering, people with this condition tend to suffer tremendously over their lifetimes, since they lack the warning signal that would otherwise prompt them to notice and treat injuries before they turn serious, often going through repeated, undetected fractures, untreated burns, and unnoticed internal injuries, without the constant careful watching most people never have to think twice about. Pain signals start at specialized nerve endings tuned to detect potentially harmful pressure, heat, or chemical irritation, traveling first to the spinal cord and then onward to the brain, where separate regions handle different jobs, one pinpointing exactly where and how strong the pain feels, another handling the unpleasant, distressing emotional weight of it. This split becomes especially clear in rare medical cases where damage to that second, more emotional region leaves someone still able to notice and pinpoint a painful poke exactly where it happened, while reporting that it no longer actually bothers them the way it once did. Pain also isn't a simple, fixed readout of physical damage. It can shift considerably depending on the surrounding situation, as shown by wartime medical records finding that badly wounded soldiers often needed far less pain relief than civilians with comparably serious injuries, likely tied to the wounded soldier's relief at having survived and been pulled safely away from danger, compared to a civilian for whom the very same injury carried no such silver lining at all. The body even carries its own natural pain-easing chemistry, released during intense exercise, sudden danger, or injury, letting it temporarily dial pain down when pushing through it, at least for a while, might matter more than the pain's usual warning value. Why do memories fade? Memory doesn't come in just one single form. A brief flicker holds raw sensory detail for only a heartbeat. A slightly longer stretch keeps a small amount of information actively in mind without needing to write it down. and a much longer-lasting form can hold on to information for years or even an entire lifetime. Forgetting works somewhat differently depending on which of these different forms is involved. One of the earliest careful studies of forgetting found that freshly learned information tends to slip away fastest right after it's first learned. Then the pace of forgetting gradually levels off, with whatever manages to survive that first steep drop tending to stick around far more reliably afterward, a basic pattern later research has repeatedly confirmed across all kinds of different material. Down at the level of individual brain cells, memories appear to take shape through the strengthening of specific connections between cells that happen to fire together repeatedly and closely in time, gradually making those particular connections more efficient at passing along a signal the more often they're used together. Forgetting, at this very basic level, appears to reflect these same specific connections gradually weakening again, whenever they go too long without being refreshed through further use or recall. A separate and increasingly well-supported idea suggests that at least some apparent forgetting isn't really about a memory being erased at all, but instead about briefly losing the ability to properly retrieve something that's actually still tucked away safely somewhere, a pattern familiar to anyone who has ever failed to recall something in one moment, only to have it pop back into mind effortlessly a little while later, without learning anything new in between. Sleep plays a clear and active role in deciding which fresh memories end up sticking around for good. The brain appears to selectively replay and reinforce certain recent memories during deep, restful sleep, and memories replayed this way tend to stick around noticeably better than similar memories that don't get this same treatment, suggesting sleep actively sorts and strengthens what's worth keeping. Interestingly, some forgetting may actually be helpful rather than simply being a flaw. Holding on to every single tiny detail from every single day without ever letting anything fade could make it much harder to spot useful general patterns buried within all that overwhelming clutter, suggesting a healthy amount of forgetting may be a feature rather than a failure. Why do we forget childhood memories? Most adults can't recall any specific, clear memories from their very earliest years. A strange and remarkably consistent gap in memory found across virtually every culture ever studied. Several different explanations have been proposed, and the true picture likely involves a bit of each working together at once. One major piece of the explanation involves the part of the brain responsible for properly filing away new long-term memories, which is still busy finishing its own construction throughout early childhood, and simply isn't fully ready yet to reliably store the kind of clear, detailed memories older children and adults can easily form later on. A second major piece ties directly to language. How well a young child can later describe a past event in words appears to depend heavily on what words and concepts that child had actually learned by the time the event originally happened, rather than on what words they've since picked up by the time they're later asked to recall it, hinting that very young children may be storing their earliest experiences in a form that doesn't translate cleanly into the words-based memories adults typically rely on afterward. A third major piece involves a child's still developing sense of having their own personal, ongoing life story, a sense that tends to take real shape only gradually across the toddler and early school years. Children whose parents talk with them often and in rich detail about shared past experiences during these early years tend to grow up with noticeably more detailed and longer-lasting memories from that same period, suggesting the surrounding conversations a young child has about their own experiences help shape which of those experiences ever turn into lasting, tellable memories at all. It's worth noting that very young children and even infants clearly can learn and remember plenty of things well before this age, including learned physical skills and simple emotional associations. What seems to specifically go missing is the kind of clear, personal, story-like memory adults rely on to recall their own particular past experiences, rather than any general inability to learn or be shaped by experience during those earliest years at all. Why do some people never need much sleep? Most adults function best on a solid, generous stretch of rest each night, and both getting noticeably less than that and, somewhat surprisingly, getting noticeably more than that have both been linked to worse health outcomes over time. Yet a very small number of people seem to function perfectly well on a good deal less rest than everyone else, without showing any of the usual downsides that ordinarily come from cutting sleep short. The clearest explanation traces back to specific inherited quirks passed down within certain families. Researchers first identified this in a mother and daughter who both slept noticeably less than the rest of their family while still functioning perfectly well. And when the very same inherited quirk was bred into laboratory mice, those mice likewise needed less sleep than ordinary mice while showing no obvious harm to their memory, learning, or general health, offering strong direct evidence that this really is a genuine biological difference, rather than simply a bad habit some people have gotten unusually used to. Since then, researchers have identified several additional different inherited quirks, found in separate families, all producing this same basic short-sleeping pattern, suggesting there's more than one biological path leading to naturally needing less rest. It's worth being careful here, since people confirmed through careful testing to have this genuine trait are considerably rarer than the far larger number of people who simply believe they personally do fine on very little sleep. Careful testing has repeatedly shown that most people who regularly cut their sleep short, without carrying one of these rare inherited quirks, do show real, measurable dips in attention and memory on careful testing, even when they themselves don't feel especially impaired at all, a striking mismatch between how sharp someone feels and how sharp they actually turn out to be once properly tested. People confirmed to genuinely be natural short sleepers also tend to share a few other traits beyond simply needing less rest, including reports of generally higher energy, a sunnier outlook, and a noticeably higher tolerance for pain in some cases, though these additional traits have been studied in far fewer people than the core sleep finding itself, leaving the fuller picture still not completely understood. Part 6. The Human Mind. What is consciousness? There is something it feels like to be you right now, some inner glow of experience running quietly behind everything you notice, and as ordinary as that feeling is, it has proven remarkably hard to fully explain in scientific terms. Researchers studying the mind have found it useful to split this puzzle into two very different kinds of questions. The easier set of questions asks how the brain manages specific jobs like focusing attention, combining information from different senses, or describing its own inner states out loud. These are genuinely difficult technical puzzles, but they fit comfortably within ordinary scientific methods, which explain behavior by tracing it back to underlying physical processes. The much harder question asks why any of that busy physical activity should be accompanied by actual felt experience at all, rather than simply happening quietly in the dark, with all the same clever behavior playing out exactly the same way, but nobody actually experiencing any of it from the inside. Even a full and complete map of every single thing happening physically inside a brain wouldn't by itself obviously explain why any of it feels like something rather than nothing. Some researchers have proposed detailed mathematical frameworks attempting to measure exactly how much a given system's parts are woven together into a single unified whole, treating that measurement as a stand-in for how much genuine experience that system carries. Others picture experience arising once information gets broadcast widely enough across many different parts of the brain at once, becoming available everywhere, rather than staying locked away in one narrow corner. Careful study of brain injuries has shown that losing an enormous section of the brain, packed with the most individual cells, can still leave someone's ordinary conscious experience completely intact, while damage to a much smaller, more specific region, tucked deep inside the brain, can wipe out consciousness entirely, suggesting that where and how connections are arranged matters far more than sheer size or cell count alone. Careful study of medically induced unconsciousness has likewise shown a consistent breakdown in long-distance communication between separate brain regions right at the exact moment awareness disappears. Despite this growing pile of clues, no single explanation has yet earned full agreement on what consciousness truly is at its very core, leaving it one of the most actively studied and least completely settled puzzles in the whole of science. Where does the mind exist? The overwhelming majority of researchers studying the brain today work from the position that the mind is produced entirely by the brain's own physical activity, rather than existing as some separate, independent thing merely loosely connected to it. Thoughts, feelings, and every flicker of experience are understood to arise directly from physical activity happening inside a living physical brain. This stands in contrast to an older idea picturing the mind and body as two entirely separate kinds of things, interacting somehow, despite being fundamentally different in nature. That older picture doesn't sit comfortably alongside the huge and steadily growing pile of evidence showing that damaging or directly stimulating a specific part of the brain produces highly specific, predictable, and repeatable changes to someone's thinking, personality, perception, or behavior. One especially famous historical case involved a man who survived a severe injury to a specific front portion of his brain, followed by dramatic and lasting changes to his personality and self-control, offering an early and striking clue tying personality closely to physical brain structure. Later careful study of patients who had the connection between their brain's two halves surgically separated found that each half could sometimes process information and even make small decisions somewhat independently of the other, offering further direct evidence of just how closely the mind depends on specific brain structure and connectivity. An important refinement to this picture argues that the mind shouldn't be thought of as sitting only inside the brain, sealed off from everything else, but rather as something that emerges from constant, active back and forth between the brain, the rest of the body, and the surrounding world, with certain thinking processes genuinely shaped by physical bodily states and by how a person actively interacts with tools and objects around them, rather than occurring purely as an isolated internal simulation. A more provocative version of this same idea suggests that under the right conditions, an external tool a person reliably and habitually depends on to store and later recall important information could reasonably be considered a genuine extension of that person's own mind and memory, rather than merely an outside aid used by an entirely separate, brain-bound mind. Just how literally to take this particular claim remains debated, but it has reshaped how many researchers think about where, exactly, the boundary of an individual mind should be drawn. Why are we self-aware? Self-awareness is the ability to recognize yourself as a distinct individual, separate from your surroundings and from everyone else, and to reflect on your own inner state. One clever way researchers test for this in animals involves placing a small mark somewhere on an animal's body it can't see directly without a mirror, then watching whether the animal, upon later spotting itself in a mirror, reaches up to touch or investigate that mark on its own body, rather than reacting as though it were looking at a completely different animal. A fairly short list of animals reliably pass this kind of test, including several great apes, dolphins, orcas, elephants, and one particular species of bird, hinting that this ability to recognize oneself has evolved independently more than once across quite different branches of the animal family tree, rather than depending on one single inherited brain structure shared by all of them. Human babies generally don't pass this same kind of test until they're a little older, and that milestone tends to arrive around the same general time as a few other important developments, including early complex language and the very first stirrings of a personal, ongoing sense of one's own life story, suggesting self-recognition is one visible marker within a broader, more gradual unfolding of self-awareness overall, rather than switching on suddenly and completely on its own. One influential idea suggests self-awareness evolved largely as a useful side effect of the demands of complicated social living, since accurately understanding your own mind may have been an efficient shortcut for guessing what other members of your group were likely thinking, feeling, and planning to do next, given that everyone else shares a broadly similar underlying kind of mind to work from as a starting template. Supporting this idea, animals that live in larger, more socially complicated groups tend, on average, to show stronger evidence of self-awareness and of understanding others' minds than more solitary animals do. Brain scans have identified a specific network of regions that light up noticeably more whenever someone is thinking specifically about themselves, their own personality, or their own past and future, compared to when they're thinking about someone else entirely, offering a specific physical location tied closely to self-focused thought, even if researchers are still working out exactly how that activity relates to the full, rich feeling of being aware of oneself. Do we truly have free will? Free will, in its strongest sense, means being able to have genuinely chosen differently in a given moment, rather than every choice being fully locked in ahead of time by everything that came before it. This question moved from pure philosophy into direct scientific testing, once researchers began measuring brain activity in the moments leading up to a simple, freely chosen action. In an early and widely discussed version of this kind of experiment, people were asked to flick their wrist whenever they personally felt like it, while watching a clock closely enough to note the exact moment they became consciously aware of having decided to act. A steady buildup of brain activity turned out to begin noticeably before people reported becoming consciously aware of their own decision, a finding many took to suggest the brain quietly settles on an action before conscious awareness of that choice ever catches up to it. This original finding and its dramatic interpretation have faced serious pushback since then, pinning down the exact subjective moment someone becomes aware of a decision through their own self-report is genuinely tricky, and more recent, more careful versions of this same experiment have suggested that the early buildup of brain activity may not reflect a specific decision being quietly made at all, but might instead just be ordinary background noise the brain is always producing, with a conscious decision simply occurring, almost arbitrarily, whenever that background noise happens to nudge past a certain threshold, a far less dramatic explanation than the original one. Philosophers have long sorted their views on this question into a few broad camps. One camp holds that since every event, including every human decision, is fully determined by what came before it, genuine free will in the strongest sense simply doesn't exist. A second camp insists genuine free will does exist, though defending this view convincingly usually requires leaning on some kind of built-in randomness somewhere in nature, even though pure random chance doesn't obviously feel any more like genuine freedom than strict predetermination does. A third, and currently quite popular camp, argues that free will is entirely compatible with everything being determined in advance, so long as free is understood to mean acting according to your own genuine reasoning and values without outside coercion, rather than meaning you could have somehow chosen differently, given the exact same prior circumstances. This remains a genuinely open and actively debated question, with no single view having won over everyone. Where do thoughts come from? A single thought doesn't come from one single, dedicated thought-making spot tucked away somewhere inside the brain. Instead, thoughts emerge from the shifting interplay between several distinct networks of brain regions, each one handling a somewhat different kind of mental job, working together in different combinations, depending on exactly what kind of thinking is happening. A large share of everyday, unprompted thought, including daydreaming and quiet reflection on your own past and future, is tied closely to a particular network that, somewhat surprisingly, becomes more active, not less, whenever someone is given nothing specific to focus on and simply left to rest quietly, suggesting that unstructured, self-directed thought is an active and energetically busy default state for a resting mind, rather than simply representing an empty lull between more meaningful, purposeful tasks. By contrast, focused, effortful thinking, the kind involved in solving a hard problem or carefully planning something, draws instead on a different network centered more toward the front and top of the brain, one that tends to quiet down during the same restful moments the daydreaming network lights up, with the two networks generally trading off with one another depending on whether attention is turned inward or outward at any given moment. A third network appears to act as a kind of switchboard, constantly monitoring incoming information for anything personally relevant or suddenly urgent, and shifting the brain's overall attention between inward daydreaming and outward-focused thinking, depending on which one seems more useful in the moment. Zooming in closer, certain specific kinds of thought, including thinking in words, picturing something visually, or imagining a particular physical movement, each draw heavily on the very same brain regions used for the real version of that same experience. Picturing a movement lights up much of the same motor control region used to actually carry it out, and silently imagining spoken words draws on much of the same region used to actually hear real speech. Interestingly, careful sampling of people's inner thoughts throughout an ordinary day has found real variation in how much any one person's thinking actually runs in clear inner words, compared to wordless imagery, pure emotion, or a kind of thinking that never seems to involve language at all, suggesting the felt experience of where thoughts come from may differ noticeably from person to person, rather than following one single universal pattern. Why do we experience déjà vu? Déjà vu is that oddly specific feeling that something happening right now has somehow already happened before, even while you're fully aware at the very same moment that this simply can't be true. Most people report experiencing this feeling at least occasionally at some point in life, most often during the teenage and young adult years, with the feeling tending to show up less often as people get older. The clearest clues about where this feeling comes from trace back to a particular region deep inside the brain closely tied to recognizing familiarity, part of the brain's broader memory system. In careful research involving patients undergoing brain monitoring for an unrelated medical reason, directly and gently stimulating this exact region reliably triggered a genuine reported feeling of déjà vu, even without anything actually new or unusual happening around the patient at that moment, offering unusually direct evidence that this specific feeling can be switched on by activity in one particular brain region alone, entirely separate from any real memory or genuine repeated experience. This supports a broader idea that déjà vu arises from a kind of misfire in the brain's ordinary familiarity detecting system. Normally, that system lights up specifically when a current experience genuinely matches something stored away from the past. Déjà vu may happen when this same system fires off by mistake or gets triggered by some real but easily overlooked partial resemblance to an actual past experience, producing a strong, convincing sense of familiarity without any specific memory anyone can actually point to as the source. A related and well-supported idea suggests déjà vu can be triggered specifically when a new scene shares the same overall spatial layout as somewhere visited before, even if every individual object and detail within that scene looks completely different, and even if nobody consciously notices any resemblance at all. Specially designed virtual environments sharing an identical layout but completely different surface details have reliably triggered noticeably higher rates of déjà vu in careful laboratory testing, supporting the idea that shared layout, more than obvious surface similarity, may be a key trigger behind many everyday cases. Déjà vu also shows up noticeably more often in people with a particular kind of seizure disorder tied to this same brain region, sometimes serving as an early warning sign just before a seizure begins, further reinforcing the tight link between this specific feeling and this specific part of the brain. Why do we hallucinate? A hallucination is a sight, sound, or other sensation that feels completely real and vivid to the person experiencing it, despite nothing actually being there to cause it. Hallucinations can arise from a surprisingly wide range of very different underlying causes, including certain eye or brain conditions, extreme isolation from ordinary sensation, and certain mind-altering substances. One especially telling example involves people who have lost a significant amount of their eyesight but have no other underlying mental health condition, and who nonetheless begin seeing vivid, detailed visual scenes that they know, with full clarity, are not actually there. The leading explanation suggests that the part of the brain responsible for vision, suddenly starved of its usual steady stream of real visual input, becomes unusually active and starts generating vivid images entirely on its own, essentially filling the sudden silence left behind once its normal input disappears. A closely related principle applies to certain cases of hearing voices that aren't really there, a specific experience tied to a breakdown in an internal system that normally helps the brain tell apart its own self-generated inner speech from real speech arriving from outside. When that internal labeling system falters, ordinary inner thought can end up mistakenly experienced as though it were a real external voice speaking from somewhere outside. Complete sensory isolation, even in perfectly healthy people with no underlying condition at all, has been shown to reliably bring on genuine hallucinations after just a few hours, further supporting the general idea that the brain's various sensing systems tend to actively generate their own content once deprived of their usual expected stream of real outside information to work with instead. Certain mind-altering substances reliably produce vivid hallucinations by disrupting the brain's usual, tightly organized way of filtering incoming sensory information through built-in expectations, loosening the normally tight grip those expectations hold over raw sensory input and letting far more unfiltered, unusual sensory activity bubble up into conscious awareness than usual. Across every one of these very different causes, a shared underlying idea emerges. Ordinary, accurate perception is itself already an active, constructive process, with the brain constantly generating its own predictions and checking them against real incoming information, rather than passively recording the world exactly as it is. Hallucinations happen when those internal predictions are given too much weight compared to what's actually out there. What causes intelligence? Intelligence, broadly meaning the ability to reason, learn, solve problems, and adapt to brand new situations, arises from a genuinely tangled mix of inherited traits, life experience, and specific measurable features of brain structure, rather than being fully explained by any single one of these on its own. Careful studies comparing identical twins who share essentially all of their inherited traits against fraternal twins and other siblings who share only about half have consistently found that inherited traits account for a substantial share of the differences in measured intelligence within a given group of people. Though this doesn't mean any one single person's intelligence is simply locked in by their genes alone, since the same studies also show a real and meaningful role for upbringing and experience. Rather than resting on any single gene, intelligence appears to be shaped by an enormous number of small genetic differences scattered across a person's entire genetic makeup, each contributing only a tiny individual effect, a pattern similar to how many other complex human traits tend to work. Beyond inherited traits, several specific early life factors have repeatedly been tied to differences in measured intelligence, including good nutrition, reduced early exposure to environmental toxins, and a rich, stimulating environment full of language and conversation during early childhood. A particularly striking piece of evidence for how much environment matters comes from the steady, well-documented rise in average measured intelligence scores across successive generations throughout much of the past century in country after country, a shift far too fast to be explained by any change in genetics, and instead pointing squarely toward broad improvements in nutrition, education, and general living conditions. At the level of brain structure itself, overall brain size shows only a fairly weak connection to measured intelligence. A much stronger connection shows up in how efficiently different brain regions, especially toward the front and sides of the brain, are able to communicate with one another along their long-distance connecting pathways, suggesting that how well connected and efficiently wired a brain happens to be may matter more than its sheer overall size. Exactly how inherited traits, upbringing, and brain wiring all combine together to produce any one particular person's specific level of intelligence remains a genuinely complicated and still actively studied question, resisting any simple, tidy division between purely inherited and purely environmental causes. Why does music affect emotions? Music reliably stirs up strong feelings across virtually every culture ever studied, despite carrying no obvious direct survival value in the way a genuine threat or the smell of good food does, which has long made it a genuinely interesting puzzle for researchers studying emotion and evolution. A large body of brain research ties music's emotional pull directly to the brain's own natural reward system, the very same system responsible for the pleasure of food and close social connection. Brain scans have shown that listening to a piece of music someone genuinely loves triggers a measurable release of the brain's own pleasure chemistry, and this release tends to peak especially strongly right in the moments leading up to a musically anticipated high point, rather than only during that high point itself, suggesting music's emotional pull comes substantially from setting up and then satisfying, or sometimes cleverly delaying, a listener's own musical expectations. This expectation-based idea has deep roots in music theory itself, which has long argued that a skilled composer's careful, deliberate playing with a listener's ongoing expectations, delaying an anticipated note, or surprising the ear with something unexpected, is a major source of music's emotional power, with the specific size of the gap between what a listener expects and what actually happens shaping how strongly they feel tension and eventual release. One evolutionary idea suggests music's power to stir feeling and connection may trace back to the earliest patterns of soothing, sing-song speech used between a parent and infant, a pattern found across many different cultures, with music more broadly acting as an extension of that same early bonding instinct out toward wider groups of people through shared singing, dancing, and communal ritual. A specific and especially strong reaction some people feel to music, a pleasurable shiver or wave of chills running down the spine at a particularly moving musical moment, has been tied to noticeably stronger physical connections between the brain's sound processing regions and its emotional reward regions in people who reliably feel this reaction compared to people who don't, hinting that at least some of this variation between people traces back to real, measurable differences in brain wiring. No single explanation fully accounts for music's emotional pull on its own, and most researchers now see it as a blend of reward chemistry, expectation, deep evolutionary roots, and individual brain wiring, all working together at once. Can memories be perfectly stored? It's tempting to picture memory working like a video recording, capturing and storing an exact, unchanging copy of the past for perfect playback later. Decades of careful research have shown this picture is simply wrong. Every single act of remembering actively rebuilds a memory from scratch, weaving it together from stored fragments and whatever else happens to be on a person's mind at that moment, rather than neatly replaying an untouched, complete original. An early and now classic study had people read an unfamiliar story from a very different culture and then recall its details after various delays. Retellings consistently shifted in the exact same directions over time, with unfamiliar details quietly and unconsciously smoothed over or reshaped to better fit each person's own existing assumptions and expectations, offering an early, clear demonstration that remembering actively reshapes the past, rather than simply replaying it untouched. Later research went even further, showing that gently feeding someone subtly misleading information after they witnessed a real event, through carefully worded questions asked sometime afterward, could reliably shift their own later memory of specific details from that event, with people often reporting, quite sincerely and confidently, having witnessed things that never actually happened, purely because a later question had planted the idea. Even more strikingly, researchers have shown it's possible to plant an entirely fabricated childhood memory using the right kind of suggestive, repeated questioning, with a meaningful number of people going on to sincerely and vividly recall a detailed childhood event, such as getting lost in a public place that had never actually happened to them at all, showing that memory doesn't just occasionally drop small details, but can, under the right conditions, construct entirely new false ones from nothing. Down at the level of individual brain cells, the very act of recalling an existing memory appears to briefly loosen that memory's own underlying storage, leaving it open to subtle change for a short while before it settles firmly back into place again, meaning each and every time a memory gets recalled, it isn't simply read off a shelf untouched, but is instead quietly nudged and updated all over again. Given all of this, memory is now understood to be a living, constantly reshaped process, continuously shaped by existing beliefs, later information, and the very act of remembering itself, rather than ever being stored as a perfect, permanently fixed recording. Part 7. The Quantum World. Why does quantum physics seem so strange? Down at the scale of atoms and the tiny particles that make them up, matter and energy follow a set of rules that has been tested more thoroughly and confirmed more precisely than any other set of rules in all of science, and yet those same rules describe behavior that clashes head-on with everything ordinary experience has ever taught us to expect. A single tiny particle, before anyone measures it, doesn't have to settle on one single state at all. It can behave as though it's holding on to several different possibilities all at once, only settling into one definite outcome the instant a measurement actually happens. Two particles can also become linked in a way that makes them behave as a connected pair no matter how far apart they later travel, in a manner no simple, everyday explanation can fully capture. And the very same tiny particle can behave like a solid little object in one kind of experiment and like a spread-out ripple in another, depending entirely on how it's being observed. One of the most accomplished physicists of the last century once bluntly admitted that nobody truly understands this set of rules, not because the mathematics ever fails to predict the right answer, since it predicts outcomes with staggering precision every single time, but because nobody has ever managed to fully explain what is actually happening underneath those equations, or why nature would behave this particular strange way in the first place. Much of the strangeness seems to come from a basic mismatch. The mathematics used to describe this tiny scale world doesn't map neatly onto any familiar everyday picture at all. The core mathematical object used to describe a tiny particle doesn't represent a physical wave rippling through ordinary space the way a wave in water does, except in the very simplest cases. And for anything involving more than one particle, it exists instead in a far more abstract mathematical space that resists being pictured in any simple, everyday way. Several competing pictures have been proposed over the past century, attempting to explain what these strange rules truly mean underneath the surface, ranging from the idea that a measurement simply and mysteriously forces a single outcome to occur, to the idea that every single possible outcome actually happens, each one branching off into its own separate, fully real version of events. Strikingly, every single one of these competing pictures currently makes exactly the same testable predictions, meaning choosing between them today comes down to taste and philosophy rather than any experiment able to settle the matter outright. What causes wave function collapse? Left alone and unmeasured, a tiny particle's mathematical description evolves smoothly and predictably over time, quietly holding open several different possible outcomes at once. Then, the instant a measurement actually happens, this same description appears to snap suddenly into just one single definite outcome, chosen only according to the odds rather than being fixed in advance. This abrupt snap creates a genuinely puzzling gap sitting right at the center of the whole theory. There's smooth, gentle, predictable change the whole time nobody is measuring anything, and then there's this sudden, seemingly different kind of snap the moment somebody actually does measure something, and the standard version of the theory never fully pins down exactly what physically counts as a measurement, substantial enough to trigger that snap in the first place. One long-favored explanation simply treats this snap as a basic, unexplained feature of nature without asking for any deeper story behind it, drawing a rough dividing line between the strange, tiny-scale world being measured and the ordinary-scale equipment doing the measuring, though critics have long pointed out that nobody has ever clearly specified exactly where that dividing line is actually supposed to sit. A more modern and increasingly well-supported explanation suggests that this apparent snap doesn't actually require any special new process at all. It happens simply because the tiny particle being measured rapidly becomes hopelessly tangled up with the enormous number of surrounding particles nearby, including stray light and air, the moment any real-world measurement takes place. Once tangled up this thoroughly with its surroundings, the particle's ability to show off its stranger, many outcomes at once behavior becomes practically impossible to detect ever again, making it look exactly as though a single, definite outcome had occurred, even though in the larger picture that includes the particle together with everything it got tangled up with, nothing ever technically and fully snapped shut at all. This tangling up explanation has been directly confirmed in careful laboratory experiments precisely tracking, in real time, exactly how quickly a delicate many outcomes at once state falls apart the moment it's allowed to interact with more and more surrounding particles. It explains beautifully why this strange behavior vanishes from view so quickly and so reliably in the real world. But most physicists agree it doesn't, by itself, fully settle the deeper question of why any single one specific outcome actually ends up being experienced at all, rather than every possible outcome simply continuing to quietly coexist forever unseen by one another. Why does observation matter? A popular but misleading claim about the tiny-scale world suggests that a person's own conscious act of looking at something is what physically causes it to settle into one definite outcome, a claim that badly overstates what real experiments actually show, and one that the overwhelming majority of physicists studying this world directly reject as an accurate description of what's really happening. What real experiments do clearly show is that any physical process capable of recording, even in principle, which specific path or outcome a tiny particle actually took is enough, all on its own, to destroy the delicate, many paths at once behavior tied to the other unrecorded possibilities. This has been directly confirmed using entirely automatic detection equipment, with no person needing to be consciously aware of, or even present to see, the actual result at all, which rules out any need for a conscious mind to be directly involved. This shows up most clearly in a classic setup where a stream of tiny particles is fired one at a time toward a barrier containing two narrow slits set close together. With nothing recording which slit each particle passes through, the particles build up a telltale rippled pattern on a screen behind the barrier, strongly suggesting each individual particle somehow passed through both slits at once as a spread-out possibility rather than a single solid object. The moment any detector is placed at the slits specifically to record which one each particle actually passed through, that rippled pattern vanishes completely, and the particles instead pile up in a much simpler pattern, exactly as ordinary solid little objects would. What flips the outcome here isn't whether a person ever consciously learns which path was taken. It's simply whether that path information gets physically recorded anywhere at all in the surrounding world, in a way that could, in principle, later be checked, even if nobody ever actually goes and checks it. Clever experiments have confirmed this directly by recording which path information with automatic equipment and then deliberately erasing that same recorded information again before anyone ever looks at it, and the telltale rippled pattern reliably reappears once the information has been properly erased, regardless of whether any conscious observer was ever involved at any point in the whole process. So, observation, in the specific sense that actually matters here, really means any physical process capable of recording distinguishing information, not a conscious mind paying attention. The idea that consciousness itself holds some special power to directly affect the tiny-scale world isn't supported by the evidence at all, despite remaining a popular misconception. Is Schrödinger's cat real? A famous thought experiment imagines a cat sealed inside a closed box together with a tiny radioactive source that has an exact, even chance of triggering a hidden mechanism at some point, one that would release a poison and kill the cat if it goes off. This thought experiment was never meant seriously, as an actual description of what would really happen to a real cat. It was deliberately designed to sound absurd, specifically to highlight a genuine and troubling problem with how the tiny-scale rules of physics were being interpreted at the time. Since the radioactive source, left unmeasured, can be described as holding open both "it triggered" and "it didn't trigger" as simultaneous possibilities, applying that very same idea consistently all the way up to the cat itself would seem to suggest the cat must also count as being simultaneously alive and dead at once, right up until the box is finally opened and someone actually looks inside. The whole point of the thought experiment was to argue that taking this consequence completely, literally, treating an ordinary cat as genuinely and physically both alive and dead at once, was deeply troubling and needed a better explanation. A very well-supported modern explanation shows exactly why a real cat would never actually be caught behaving this strange way. A cat is an enormously complicated object built from a staggering number of individual atoms, constantly and unavoidably interacting with everything around it, including the surrounding air and light, at an extremely fast rate. This overwhelming amount of constant interaction causes any delicate, both-at-once possibility to fall apart and become impossible to detect again in an almost unimaginably tiny fraction of a moment, far too quickly for anyone to ever catch a real cat sitting in that strange in-between state, even if it briefly and technically began to form in the very first place. Researchers have actually managed to create and directly observe this delicate both-at-once behavior in specially built objects considerably larger than a single tiny particle, including tiny engineered circuits large enough to see with the naked eye, though only by keeping them extremely cold and carefully shielded from any ordinary outside interaction. Conditions nothing like the messy, warm, constantly disturbed environment a real living cat actually experiences every moment of its life. So, the thought experiment was never meant to describe what would truly happen to an actual cat. It was a deliberately provocative way of exposing a genuine puzzle in how the tiny-scale rules of physics should properly be understood, a puzzle later explanations have gone a long way toward clearing up. Can particles exist in two places? Before being measured, a tiny particle can behave as though it occupies several different positions at once, rather than sitting still in one single, definite spot the way an everyday object always seems to. This isn't just a gap in our knowledge about some hidden, single true position the particle secretly has all along. Careful experiments have shown it's a genuine feature of how these tiny particles actually behave. The clearest evidence for this comes from firing particles one at a time toward a barrier with two narrow slits, and watching a telltale rippled pattern slowly build up on a screen behind it, a pattern that only makes proper sense if each individual particle really did pass through both slits at once as a spread-out possibility, rather than sailing cleanly through just one slit or the other the way a normal little object would. An especially striking example of this same many places at once behavior shows up in a phenomenon where a tiny particle manages to pass straight through a solid barrier it shouldn't have had nearly enough energy to get past at all, according to ordinary everyday physics. This happens because the particle's spread-out possibility naturally leaks a little bit into and through the barrier itself, giving it a small but genuine chance of turning up on the other side despite lacking the energy to have gone over or through in any ordinary sense. This isn't just some obscure laboratory curiosity either. It plays an essential role in letting heavy atoms occasionally break apart on their own, and it's exactly what allows the sun and other ordinary stars to keep shining as steadily as they do, since normal everyday physics alone would make that process far too slow to sustain a star's fire at all. Careful, well-controlled experiments have completely ruled out the tempting alternative explanation that a particle secretly holds one single true position all along, with its many places at once description merely reflecting our own incomplete knowledge of that hidden true position. The way not knowing which pocket someone hid a coin in doesn't mean the coin was really smeared across every pocket at once. Researchers have also managed to keep pushing the size of objects that can show this many places at once behavior larger and larger, successfully demonstrating it in fairly large, complex molecules under carefully controlled laboratory conditions. There's no known sharp size limit above which this strange behavior simply and suddenly stops working entirely. Only a steadily growing practical difficulty in shielding larger and more complicated objects from their surroundings long enough to actually catch them doing it. Why are particles entangled? Two tiny particles can become linked together in a peculiar way, such that measuring a particular property of one of them instantly reveals precise information about the matching property of the other, no matter how far apart the two particles have since traveled. This strange linking cannot be fully explained by imagining that each particle simply carried its own fixed, hidden property all along, quietly waiting to be revealed the moment somebody finally checked. This strange linking troubled some of the earliest physicists working on these tiny-scale rules, who argued that it must mean the theory was missing some deeper, hidden piece of the puzzle, one that would restore a more comfortable, ordinary picture of reality if only it could be found, rather than accepting what one of them memorably and dismissively called spooky influence, reaching across any distance at all. This debate eventually turned from pure philosophy into something that could actually be tested directly in a laboratory. A clever mathematical test was developed showing that any theory in which each particle secretly carries its own fixed, hidden property all along would have to produce results falling below a certain specific limit, while the standard tiny-scale rules predicted results that would clearly exceed that same limit under the right conditions. Careful experiments, refined and tightened over several decades to rule out every remaining loophole, have repeatedly confirmed the tiny-scale rule's own prediction, clearly and decisively ruling out the entire class of simpler, more comfortable explanations that early skeptics had hoped might restore an ordinary picture of hidden fixed properties. It's worth being precise about what this strange linking does and doesn't actually allow. It cannot be used to send an actual message faster than light, since the specific outcome at either single location remains completely random on its own, and the meaningful connection between the two separate results can only be confirmed afterward by comparing notes through an entirely ordinary, properly speed-limited channel. This strange linking isn't just an abstract curiosity confined to physics laboratories either. It has already become the essential working foundation behind real, practical modern technology, including methods of secure communication that can reliably detect any outside eavesdropper, and machines built to perform certain kinds of calculation far more efficiently than any ordinary computer ever could. Can information travel faster than light? One of the most thoroughly tested rules in all of physics holds that light's own speed marks an absolute, unbreakable limit on how quickly any real message or influence can travel from one place to another, a rule confirmed through more than a century of careful testing across many completely different areas of physics, without a single confirmed exception ever turning up. As discussed in the previous topic, the strange, seemingly instant linking between two separated tiny particles doesn't break this speed limit at all, since the specific outcome measured at either single location remains completely random all on its own, with no way to extract or send any actual usable message from either measurement alone. The meaningful connection between the two only becomes clear once the results are compared afterward, using an entirely ordinary and properly speed-limited method. A separate and sometimes misunderstood example involves certain very unusual light experiments in which the overall shape of a light pulse passing through a specially engineered material can be measured moving faster than light's ordinary speed. Careful, detailed analysis has shown this happens because the specially engineered material subtly reshapes and distorts the pulse's overall envelope as it passes through. And crucially, the genuinely new part of the pulse actually carrying any new information never exceeds light's ordinary speed at all, once the situation is properly and fully worked out. A further commonly cited example involves the stretching of space itself. Because space has been gently and continuously stretching apart ever since the universe began, the distance between two sufficiently far apart galaxies can grow faster than light's ordinary speed would normally allow. This doesn't break the rule either, since no actual object or signal is ever locally moving faster than light through the space immediately around it. It's the space itself expanding uniformly everywhere at once that produces this large-scale separation over vast distances, a genuinely different situation from something physically racing past its own immediate surroundings faster than light. After more than a century of extraordinarily careful and continued testing across every corner of physics, this speed limit remains one of the most solidly confirmed rules ever established, and every single proposed shortcut or apparent exception ever seriously examined has, upon careful analysis, turned out to fully respect it after all. Why is quantum randomness truly random? Physicists widely believe that certain outcomes in the tiny-scale world, such as which of two paths a tiny particle takes at a specific junction, or the exact moment a particular radioactive atom happens to break apart, aren't simply unpredictable, because we lack enough information to calculate them in advance. The way we can't easily predict exactly how a tumbling coin will land, even though its landing is, in principle, fully determined by ordinary physics. Instead, these tiny-scale outcomes are believed to be genuinely and fundamentally random at the deepest possible level, with no hidden, more complete explanation waiting to be discovered underneath. The strongest evidence for this comes from the same careful experiments discussed earlier regarding strangely linked particles, which ruled out the entire class of simpler explanations that would have restored a comfortable picture of particles secretly carrying fixed hidden properties all along, properties that, once fully accounted for, would have made everything fully predictable in principle after all. It's worth being precise here, though, since those experiments specifically ruled out explanations relying only on ordinary nearby influences, while leaving open, at least in principle, a very different and more unusual kind of explanation involving influences that reach across any distance instantly, so long as no actual usable message could ever be sent that way, in keeping with the speed limit discussed in the previous topic. One seriously developed alternative theory along these lines proposes that tiny particles do, in fact, have a completely definite position and path at every single moment, even when unmeasured, quietly guided along by an accompanying wave that isn't directly observed. Remarkably, this alternative theory reproduces every single one of the standard tiny-scale rule's own well-tested predictions exactly, without needing any fundamental randomness built into its own picture of reality at all. Because this alternative theory currently makes exactly the same testable predictions as the standard picture for every experiment ever performed, the deep question of whether tiny-scale randomness is genuinely fundamental, as most physicists currently assume, or whether it merely reflects our own incomplete knowledge of some deeper, fully determined hidden mechanism, cannot currently be settled by any experiment at all, and remains, for now, a matter of interpretation rather than settled fact. Machines that generate genuinely random numbers by directly exploiting this tiny-scale randomness are already in real practical use today, particularly for serious security purposes, precisely because this kind of randomness is currently considered far more reliably unpredictable than anything an ordinary computer program could ever produce on its own. Is reality fundamentally quantum? The modern theory that successfully blends the tiny-scale rules of physics together with the rules of fast relative motion currently provides the most complete and most thoroughly tested description of physical reality that exists anywhere in science, correctly and precisely describing 3 of the 4 known fundamental forces of nature, with its predictions confirmed to an extraordinary degree of precision across many decades of careful testing. Within this framework, what we ordinarily think of as solid, separate little particles, including the tiny building blocks of light and matter, are better understood not as small solid objects in any everyday sense, but as small, localized ripples rising up from underlying fields that fill the whole of space and time completely, with the fields themselves considered the truly fundamental layer of reality, and the particles we notice simply being specific, distinct ripples within them. Given how well this picture has held up, many researchers studying the deepest foundations of physics argue that reality is, in a very real sense, built from these tiny-scale rules all the way down, with the familiar, solid-feeling, everyday world we actually experience emerging only as an extremely accurate practical approximation, one that becomes reliable specifically because the delicate, many outcomes at once behavior discussed in earlier topics gets rapidly and thoroughly washed out once enough surrounding particles get involved, rather than the everyday world being some entirely separate and equally fundamental layer of reality in its own right. This raises a further and still unresolved question. Is this current framework itself truly the final, deepest layer of reality? Or could it, too, eventually turn out to rest on something even more fundamental, still waiting to be discovered underneath it? This question becomes especially sharp once gravity, the one major force this framework still hasn't been successfully folded into, is brought into the picture, since gravity has so far stubbornly resisted every serious attempt to fit it comfortably alongside the other 3 forces within this same successful framework. Some researchers have gone even further still, proposing that gravity itself, and even the basic fabric of space and time, might not be truly fundamental at all, but could instead emerge from some deeper, more basic pattern of tiny-scale connections between far more fundamental underlying pieces in a manner loosely similar to how something like temperature emerges from the collective jostling of countless individual atoms, rather than being a separately fundamental quantity all its own. This remains a genuinely open and actively pursued idea, showing that even physics's most successful framework yet may not be the final word on what reality is truly built from underneath everything else. Could quantum mechanics be incomplete? Despite being tested and confirmed more precisely than perhaps any other set of rules in the whole of science, several serious and specific reasons lead a meaningful number of physicists to suspect that the tiny-scale rules of physics, in their current standard form, may not represent the absolute final and complete word on how reality actually works at every possible scale and under every possible condition. The single biggest reason involves the long, stubborn difficulty in successfully combining these tiny-scale rules with the separate and equally well-tested rules describing gravity and the large-scale shape of space and time, discussed in earlier topics regarding the true nature of black holes and the earliest moments of the universe. Since both sets of rules have each been extremely well confirmed within their own separate domains, this ongoing difficulty in fully unifying them strongly suggests that at least one of them, or perhaps some subtler piece of both together, will eventually need some further adjustment once a complete and unified theory finally comes together. A second reason involves the unusual and uncomfortable situation where several genuinely different, mutually incompatible explanations for what these rules actually mean underneath the surface, discussed at various points throughout this part of the series, all currently make exactly the same testable predictions. A situation some physicists take as a hint that the current standard mathematics may be an extremely accurate and useful calculating tool, without yet fully capturing the true underlying picture of reality that a more complete future theory might eventually make clear beyond any doubt. A third reason traces back to an old and still unresolved question about whether the randomness built into these rules is a genuine, permanent feature of reality, as most physicists currently assume, or whether it instead reflects our own current, incomplete understanding of some deeper, fully determined mechanism still waiting to be uncovered, an issue directly connected to the alternative explanation discussed in an earlier topic that reproduces every standard prediction without needing any fundamental randomness at all. A fourth and increasingly active area of research involves careful experiments specifically designed to test whether these tiny-scale rules truly continue working without any limit as objects get larger and more complicated, or whether some yet undiscovered mechanism might cause this strange behavior to quietly fade away once a system grows large enough, with a few specific proposals suggesting gravity itself might be the true underlying cause of that fading, rather than merely getting tangled up with the surroundings. Whether these tiny-scale rules represent nature's truly final and complete word or an extremely accurate stepping stone toward something deeper still remains a genuinely open question today. Part 8. The Mysteries of Physics. Why is gravity so weak? Of the four basic forces shaping everything in the universe, gravity is astonishingly and almost embarrassingly weak compared to the others. A small ordinary magnet can easily lift a metal pin right off a table, its modest pull overpowering the combined gravitational tug of the entire planet beneath it. Physicists call this puzzling gap between gravity's weakness and the other force's relative strength one of the deepest open questions in all of fundamental physics. This puzzle becomes especially sharp when physicists try to calculate the expected properties of a particular important particle discovered a little over a decade ago, one closely tied to how much mass other particles carry. When all the surrounding influences on this particle are properly added up, the natural expected result comes out vastly larger than what's actually measured, unless some remarkably precise and seemingly coincidental cancellation happens to occur behind the scenes. A coincidence many physicists find deeply unsatisfying and are eager to find a better explanation for. One serious proposed explanation suggests gravity might not actually be weak at its deepest level at all, but instead only appears weak because it alone is able to leak out into extra hidden dimensions of space beyond the familiar three we move through every day, with the other three forces remaining fully confined within our own familiar dimensions. Under this picture, gravity's pull would seem diluted specifically because it's spreading its influence out across these extra hidden dimensions, rather than being fully concentrated within our own, in the same way a fixed amount of light spreads out and grows dimmer as it radiates outward across an ever larger sphere. This idea makes a testable prediction. If these extra hidden dimensions are large enough, gravity's ordinary pulling pattern should start to noticeably shift once distances get small enough to directly probe those extra dimensions. Extremely precise laboratory tests of gravity at very short distances have so far found no sign of any such shift, ruling out a fair range of possible sizes for these extra dimensions, without fully ruling out the whole idea, since any hidden extra dimensions could simply be smaller still than anything tested so far. A separate, more mathematical idea suggests gravity's weakness might instead be an unavoidable requirement built into any fully self-consistent way of combining gravity with the tiny-scale rules of physics, a serious and actively studied idea, though not yet fully proven. Either way, gravity's dramatic weakness compared to the other forces remains one of the most significant unexplained numbers in all of physics. Why can't gravity fit quantum theory? Modern physics rests on two enormously successful pillars, each extensively tested and confirmed within its own particular domain. One pillar precisely describes how tiny particles behave, and the other precisely describes gravity as the bending and curving of space and time itself, confirmed at the scale of planets, stars, and entire galaxies. Despite each pillar's remarkable individual success, physicists have struggled for decades to combine the two into one single, unified picture. The trouble shows up clearly the moment physicists try to treat gravity using the very same mathematical toolbox that works so well for the other three basic forces. Applying that same toolbox to gravity produces a flood of impossible, infinitely large results the moment calculations are pushed to very high energies, a breakdown that simply doesn't happen with the other three forces when treated the exact same way. This breakdown becomes especially serious at an almost unimaginably tiny scale, one so small that both gravity's effects and the tiny scale rules of physics become equally important at exactly the same time, rather than one completely overshadowing the other the way they normally do at the much larger, everyday scales we're familiar with. Several serious approaches have been proposed to try to resolve this clash and build a single, complete theory, successfully combining gravity with the tiny scale rules, though none has yet been confirmed by any experiment. One approach proposes that the truly fundamental building blocks of everything aren't tiny points at all, but instead extremely small, thin, vibrating loops, with a given loop's particular vibration determining exactly which kind of particle it appears to be from a distance, including a specific particle believed to be responsible for carrying gravity itself, arising naturally rather than needing to be specially inserted. This approach generally requires several additional hidden dimensions of space beyond the ones we notice and hasn't yet led to any prediction testable with current technology. A completely different approach skips particles altogether and instead treats the very fabric of space as being built from tiny, discrete building blocks, somewhat like a photograph that looks perfectly smooth from a distance but turns out to be made of individual dots once you zoom in close enough. This approach has struggled to fully and smoothly reproduce ordinary large-scale gravity the way we actually observe it, and likewise hasn't yet produced a prediction that could clearly set it apart from its rivals. Given how impossibly tiny the scale involved actually is, no current technology comes anywhere close to directly testing either approach, leaving the true path toward successfully combining gravity with the tiny scale rules of physics as one of the biggest open problems standing at the very frontier of physics today. Why is time one direction? There's a genuinely strange mismatch sitting at the heart of physics. Almost every basic rule governing how individual particles interact works exactly the same whether run forward or backward, producing an equally valid result either way, yet everyday experience clearly runs in only one direction. Eggs shatter but never spontaneously reassemble, and people grow older but never younger. This mismatch is usually explained not through any deep asymmetry in the basic rules themselves, but through a different quantity entirely, one that measures how mixed up or spread out a system's arrangement has become. A basic and thoroughly tested law of nature holds that this measure of mixed upness, for anything left alone, will almost always increase over time, or at the very least, never spontaneously decrease on its own. This law turns out to be fundamentally about likelihood and probability rather than being an absolute, unbreakable command. Any given large, everyday arrangement of matter almost always has vastly, overwhelmingly more possible mixed-up ways of being arranged than possible neat, orderly ways, so a system left alone naturally tends to drift toward whichever overall arrangement has the largest number of ways to achieve it, simply as an unavoidable consequence of basic probability, rather than because some deeper law directly forbids the reverse. This is exactly why a shattered egg never spontaneously reassembles itself. There are an almost unimaginably larger number of ways for its pieces to sit scattered and broken than there are ways for them to happen to reassemble into one single intact egg again, making the reverse so overwhelmingly unlikely that it might as well be considered impossible for all practical purposes, even though nothing in the basic underlying rules technically forbids it outright. This raises a deeper and genuinely puzzling further question. If mixed-upness naturally tends to increase as time goes forward, then it must have been considerably lower in the past, and tracing this reasoning all the way back to the very beginning implies the universe itself must have started out in an extraordinarily neat, orderly, and highly specific state right at the very start, a state so specific and so unlikely to have simply occurred by pure chance that it demands some further explanation all its own. Nobody currently has a fully settled answer for why the universe's very beginning happened to be arranged so neatly and so improbably in the first place. And this single unanswered question sits directly underneath the entire everyday experience of time only ever seeming to move in one single direction. What is time made of? The modern understanding of gravity doesn't treat time as some separate river flowing at exactly the same steady pace for absolutely everyone everywhere in the universe, the way older, more old-fashioned physics once assumed. Instead, time gets woven together tightly with ordinary space into one single, unified, and remarkably flexible fabric, one whose exact shape is directly molded by whatever matter and energy happen to be sitting nearby. This flexible picture has been thoroughly and repeatedly confirmed through direct measurement. Clocks genuinely tick at slightly different rates depending on how fast they're moving and how strong the nearby pull of gravity happens to be. Clocks aboard orbiting satellites, for instance, genuinely run at a very slightly different pace than identical clocks sitting still down on the ground. A small but very real and precisely measured mismatch that has to be carefully corrected for constantly, or else satellite navigation systems used every day would quickly drift wildly inaccurate. Despite confirming that time bends and flexes this way, this same successful picture of gravity doesn't actually explain what time fundamentally is at some even deeper level, the way water can be explained as being built from smaller underlying pieces. This deeper question becomes especially pressing whenever physicists try to combine gravity with the tiny-scale rules of physics discussed in the previous topic, since some of the most serious proposed approaches toward that unification make startling and very different claims about what time truly is underneath everything else. One particularly striking proposal describes the entire universe using a single overarching mathematical description that, remarkably, contains no explicit sense of time passing at all, hinting that time, at this deepest possible level, may not be a truly fundamental ingredient of reality in its own right, but might instead be a kind of higher-level bookkeeping trick, one that only becomes meaningful once you start comparing how different parts of a larger system change and relate to one another, rather than time itself being some separate, ever-flowing background quantity running independently underneath everything else. A closely related idea suggests that time might instead emerge from the shifting relationships between the tiniest possible building blocks of space itself, rather than flowing along as some separate background all its own. Some researchers studying this question have even suggested that our strong, deeply familiar sense of time steadily and smoothly flowing forward might say more about the particular way human minds are built to experience the world than it reveals about time's own truly fundamental underlying nature. Whether time is truly fundamental, or something deeper and stranger still waiting underneath it, remains one of the most genuinely open puzzles in all of physics. Why is the speed of light constant? Light travels through empty space at one single, fixed, and completely unchanging speed, and remarkably, every single observer measures that exact same speed for it, no matter how fast they themselves happen to be moving relative to the light's original source or to one another. A deeply strange fact that flatly contradicts the more familiar everyday rule that speeds simply add together depending on how fast you yourself happen to be moving. This strange constancy was first uncovered by an experiment specifically designed to detect Earth's own motion through space by carefully measuring tiny expected differences in light speed depending on which direction it happened to be traveling. That experiment repeatedly turned up no difference at all, a puzzling and unexpected result that took years to properly explain, until a young physicist proposed that light speed truly is fixed and constant for absolutely everyone, entirely independent of how anyone happens to be moving, rather than assuming some invisible, unmoving medium must be quietly hiding the expected difference. The real insight buried in this discovery was recognizing that if light's speed truly stays constant, no matter how anyone is moving, then something else entirely, namely the ordinarily assumed fixed universal nature of both space and time themselves, must instead be the more flexible quantities, shifting in a very specific and precisely calculable way between different moving observers. Specifically, in order to keep light's own measured speed locked in place as an absolute constant for every single one of them. This single insight directly leads to clocks running at different rates and to objects appearing to shrink slightly along their direction of motion when measured by someone watching them speed past. Beyond its role in these strange effects, light's fixed speed carries a much deeper significance still. It represents the single fastest speed at which any cause can ever produce an effect anywhere in the universe, a fundamental structural feature woven directly into the very geometry of space and time itself, rather than merely being some incidental property that happens to belong to light alone. Light itself simply happens to travel at exactly this universal top speed, because the particles making it up carry no mass whatsoever, and any massless particle, as a direct mathematical consequence of these same rules, is always forced to travel at precisely this same fundamental top speed, no matter who happens to be watching. Careful astronomical observations stretching across vast distances and enormous spans of time have found no hint of this fundamental speed ever varying even slightly, making it one of the most solidly and repeatedly confirmed constants in the whole of physics. What is empty space? Modern physics has completely upended the old, comfortable idea of empty space as a simple, silent void containing absolutely nothing at all. Even a region of space with every last scrap of matter and energy carefully removed still isn't truly empty in that older, simpler sense. It remains quietly filled everywhere with restless, ever-fluctuating activity that can never be fully switched off, a basic and unavoidable consequence of some of the deepest rules governing the tiny-scale world. These constant, unavoidable flickers give rise to fleeting little bursts of matched pairs, popping briefly into existence directly out of seemingly empty space before instantly disappearing again, all within an incredibly short window of time. Though these fleeting bursts can never be caught and observed directly all on their own, their combined effect has been measured clearly and repeatedly in more than one completely independent way. The clearest and most direct confirmation of this comes from a delicate experiment involving two flat, uncharged metal plates placed extremely close together in a vacuum. A small but perfectly real and precisely measurable force gently pushes those two plates together, arising because the narrow gap squeezed between them restricts which kinds of these restless fluctuations are able to properly fit inside it, compared to the much wider range able to freely exist in the open space surrounding the outside of the plates. This subtle mismatch produces a small but genuine and repeatedly measured pull, drawing the two plates steadily together. A second and completely separate confirmation comes from a very small but precisely predictable mismatch between a simple atom's expected energy levels calculated using an earlier and simpler version of the theory, and that same atom's actual, carefully measured energy levels in the real world. A mismatch that only gets properly and fully explained once these same restless background fluctuations are properly folded into the calculation. This same restless underlying energy filling empty space is also believed to be closely connected to the mysterious force driving the universe's ever-accelerating expansion. Discussed in an earlier part of this series, though the actual measured strength of that expanding force turns out to be dramatically and puzzlingly smaller than what a straightforward calculation of this restless background energy would naturally predict, a serious and stubbornly unresolved mismatch that remains one of the most significant unsolved puzzles in all of modern physics. Empty space, then, turns out to be far from truly empty at all, but is instead a constantly active, restlessly fluctuating medium, whose measurable effects have been confirmed in more than one completely independent way, even while its full and complete underlying nature remains only partly understood. Why do physical constants never change? Certain fixed numbers appear again and again throughout physics, including light's own fixed speed and the specific strength governing how strongly electrically charged particles interact with one another, and every measurement ever taken, anywhere and at any time, has found these numbers holding perfectly steady, never wavering even slightly. This steadiness quietly underlies essentially the whole of modern physics, and yet it isn't something automatically guaranteed by any deeper rule we currently understand, which is exactly why scientists keep testing it as carefully and as often as they can. The most demanding tests come from studying extremely distant and extremely ancient light, arriving here after traveling for an almost unimaginably long stretch of time, offering a direct window into what these same fixed numbers looked like far back in the universe's past. One early study suggested a tiny possible shift in one particular constant over that enormous stretch of time, a genuinely exciting hint at the time, though later studies using different telescopes and different data haven't consistently managed to confirm the very same result, leaving most researchers currently doubtful that any real shift actually occurred, and suspecting instead some subtle, still unidentified measurement quirk was likely responsible. A separate and remarkably clever natural test comes from a genuinely unique ancient site where a naturally occurring uranium deposit is believed to have spontaneously sustained its own natural nuclear reaction for a very long stretch of time, occurring entirely on its own, without a trace of human involvement, deep in Earth's ancient past. Because the fine details of that ancient natural reaction depend very sensitively on the exact strength of a particular basic force, carefully studying the leftover chemical traces from that reaction lets scientists check just how much, if at all, that particular force could have shifted since then. That check has found no evidence of any meaningful shift at all, placing an extremely tight limit on how stable this particular force has truly remained across an enormous stretch of Earth's deep past. Some genuinely serious theoretical proposals do suggest that certain of these fixed numbers could, in principle, shift very slightly across sufficiently long stretches of cosmic time, tied to the behavior of some deeper, currently unknown underlying field. This keeps motivating scientists to keep testing for it, even though no confirmed shift has ever actually turned up. The deeper question of why these particular fixed numbers should hold so remarkably steady at all remains for now simply an observed fact rather than something derived from any known deeper principle. Why is matter more common than antimatter? Every basic kind of particle has a mirror image opposite counterpart, matching it in every way except carrying an opposite electric charge, and whenever a particle meets its exact opposite counterpart face to face, the two completely destroy one another, converting their entire combined substance directly into a burst of pure energy. The universe's fiery beginning, discussed earlier in this series, is believed to have produced almost exactly equal amounts of ordinary matter and its mirror image opposite in its earliest, hottest moments. Since the basic process responsible for creating particles directly out of pure energy back then would, under the simplest expectation, have created matching amounts of both at once. Yet the universe we actually observe today is overwhelmingly made of ordinary matter, with only the barest trace of its mirror image opposite ever found anywhere, and only when deliberately produced through violent high-energy collisions. If matter and its opposite had truly stayed perfectly balanced the whole way through, the two should have almost completely wiped each other out early on, leaving behind a bare, radiation-filled universe with hardly any leftover matter at all, rather than the rich, structured universe of stars and galaxies actually observed today. The tiny surviving imbalance needed to explain everything we see today turns out to be remarkably small. For roughly every billion matched pairs that met and destroyed one another in the fiery early universe, just one single extra particle of ordinary matter is thought to have been left over without a partner to meet and vanish alongside. That tiny leftover surplus eventually grew into every star, every planet, and every living thing that exists today. A physicist studying this puzzle laid out 3 specific conditions that would all need to be satisfied for any natural process to produce this kind of tiny leftover imbalance in the first place. Some process capable of tipping the overall balance toward ordinary matter, some breaking of a deep underlying mirror symmetry that would otherwise force matter and its opposite to behave in perfectly matched ways, and all of this happening while the early universe was still churning too chaotically to have settled into a perfectly even balance. That particular mirror symmetry breaking has, in fact, already been directly confirmed through careful experiments studying a certain unusual particle's decay, but the amount of breaking confirmed so far turns out to be far, far too small to fully explain the whole observed imbalance on its own, strongly suggesting some additional, still undiscovered source of this same mirror symmetry breaking must still be waiting out there to be found. Can negative mass exist? Negative mass describes a purely hypothetical kind of matter that would respond backward to any pushing force, accelerating directly toward a push rather than away from it. And that would actually push other nearby matter away through gravity, instead of pulling it inward, the way every single known form of ordinary matter always does. No confirmed naturally occurring particle of this kind has ever actually been found anywhere, and most physicists consider it unlikely that anything like it exists freely out in nature as a stable substance. A closely related but importantly different idea, a patch of space carrying less than the ordinary baseline amount of energy, has, notably, already been confirmed to exist under very specific and carefully controlled conditions, seen clearly in the small but genuine pull drawing 2 closely spaced metal plates together in a vacuum, discussed in an earlier topic regarding the true nature of empty space. The tiny scale rules of physics do allow small, brief, and tightly localized patches of this reduced energy to exist under just the right conditions, but they place a strict limit on how much can exist, and for how long, making it appear extremely difficult, and possibly outright impossible, to gather and sustain nearly enough of it to be useful for anything on a larger practical scale. This strict limit directly and seriously constrains a few genuinely exotic ideas that would otherwise require large, stable amounts of this reduced energy material to actually work, including a hypothetical shortcut tunnel through space discussed in an earlier topic and a hypothetical way of folding space to travel effectively faster than light without technically breaking any speed limit. A genuinely fascinating recent laboratory result did manage to create something behaving remarkably like negative mass, using a carefully cooled cloud of atoms chilled down to an extraordinarily low temperature. Under those very specific and carefully engineered conditions, the atoms accelerated toward an applied push rather than away from it, exactly matching how true negative mass would be expected to behave. It's important to be clear that this doesn't represent the discovery of any genuinely new, negative mass particle out in nature. It's a specifically engineered effect arising from how the atoms interact with each other and with the surrounding equipment holding them in place, a bit like how electrons moving through certain materials can sometimes usefully be described as behaving with an altered mass, without their true, fundamental mass ever actually changing at all. Given these strict limits on gathering and sustaining reduced energy material at any meaningful scale, most physicists consider genuine negative mass unlikely to exist as a stable, large-scale, or practically usable substance, even while its stranger properties can be cleverly recreated in miniature under very carefully controlled laboratory conditions. Is space-time actually real? The modern understanding of gravity describes it not as an ordinary, invisible force reaching directly and instantly between separate objects, but as the actual curving and bending of a single, unified fabric woven together from space and time, with massive objects simply following the straightest possible path they can through that same curved fabric, famously summarized by one physicist's memorable phrase describing how this fabric guides matter's motion, while matter, in turn, shapes the fabric's own curve. This picture has been confirmed through a whole series of completely independent tests, including a small, previously unexplained wobble in a nearby planet's orbit, that this picture accounted for immediately and precisely, the visible bending of distant starlight as it grazes past the sun, and, more recently, the direct detection of ripples passing through the fabric of space itself, set loose by the collision of two extremely dense collapsed objects far off in deep space. Given this repeated and remarkably precise confirmation, few physicists seriously question that space and time really do behave this way as an extremely accurate practical description of gravity. A much deeper and more philosophical question remains open, though. Is this curved fabric truly one of the most basic, fundamental building blocks of reality itself? Or could it instead be something that emerges from an even deeper, more basic underlying structure, one that doesn't look anything like ordinary space and time at first glance? This question has become an increasingly active and serious area of research, tied closely to the broader effort to successfully combine gravity with the tiny-scale rules of physics. One particularly influential line of research has uncovered a striking mathematical connection showing that a complete theory of gravity operating within a curved region of space is exactly equivalent to a separate theory containing no gravity at all, operating only on that region's own outer boundary surface. Since gravity and curved space don't appear anywhere in this alternative boundary-based description, many researchers argue space and its curvature may not be truly fundamental, but might instead emerge from more basic underlying connections, resembling the strange linking discussed in an earlier topic regarding tiny paired particles, with the very connectedness of space itself perhaps being built out of something deeper and stranger still. Whether space and time are truly fundamental, or a construction resting on something else entirely, remains one of the most active open questions at the very edge of physics today. Part 9. The Earth's Mysteries. How did Earth's water arrive? Earth formed close enough to the Sun that the raw building blocks gathering together to form it were likely far too warm for ice to have simply stuck around and been baked directly into the young planet in any large amount. And yet today, oceans spread across most of the planet's surface, with even more water tucked away deep inside its rocky interior. Figuring out exactly how all of that water first arrived remains a genuinely interesting puzzle. For a long time, the leading idea suggested water arrived afterward, carried in by a steady rain of icy comets and water-rich rocky debris crashing down onto the young planet during its earliest and most chaotic era. Comets seem like an obvious candidate at first, since they're icy through and through, but careful chemical analysis of a comet's actual ice, carried out by a spacecraft that flew alongside one, turned out to look noticeably different in composition from the water actually found in Earth's oceans, casting real doubt on comets being the main source after all. A particular category of especially old, unaltered rocky rubble left over from the solar system's earliest days has since emerged as a much stronger candidate, since its water more closely matches the chemical fingerprint of Earth's own oceans. Material carried directly back to Earth by two separate space missions, each one collecting a sample from this same kind of ancient rubble, has confirmed water-bearing minerals with a fingerprint lining up impressively well with our oceans, lending solid support to this rubble as a major original source. A separate and increasingly serious idea suggests a meaningful share of Earth's water may never have needed to be delivered afterward at all, and might instead have been locked directly into water-rich minerals that were already part of the raw rocky material that built Earth in the first place, rather than existing as loose ice that would have simply evaporated away in the heat so close to the young sun. Careful study of a class of meteorites believed to closely resemble Earth's original raw building material has found they carry enough trapped water to account for several times over what fills our oceans today, suggesting this built-in water may have contributed considerably more than once assumed. Most researchers today suspect Earth's water came from a mix of both sources working together, built in from the start and delivered afterward by incoming debris, rather than either story alone fully explaining where all our water ultimately came from. Why does Earth's magnetic field flip? Earth's magnetic field, generated by churning molten metal deep within the planet, occasionally and unpredictably flips its polarity entirely, with north and south magnetic poles swapping places over a stretch of time considerably longer than a human lifetime, but still remarkably brief on the grand scale of Earth's own history. Evidence for these past flips comes from rock that continuously forms along cracks on the ocean floor, cooling and hardening in place while permanently recording the exact direction of the magnetic field at that very moment, preserving a detailed magnetic diary stretching back tens of millions of years. This magnetic field arises from swirling currents of molten metal deep inside the planet, combined with Earth's own steady spin, generating electrical currents that in turn produce the overall magnetic field through a self-sustaining process, not unlike an ordinary electrical generator. Because this churning motion is naturally chaotic and unpredictable, small shifts deep within that churning flow can, given enough time, disrupt the field badly enough to flip it entirely. Behavior scientists have even managed to recreate convincingly inside detailed computer simulations built purely from the underlying physical rules governing that churning flow. These flips happen irregularly rather than on any fixed, predictable schedule, sometimes occurring fairly close together in time, and at other points in Earth's past, going an extraordinarily long stretch without any flip happening at all, showing that the underlying churning process driving these flips doesn't follow any tidy, predictable rhythm at all. The most recent full flip happened long enough ago that some researchers consider Earth somewhat due for another one, based purely on how often flips have happened on average throughout the more recent stretch of Earth's history, though this kind of simple averaging doesn't actually let anyone reliably predict when the next flip will truly happen, given how irregular the pattern has always been. Earth's magnetic field has also been measurably weakening over the past couple of centuries, a trend some see as a possible early sign that another flip may be approaching, though similar temporary weakening has happened before without leading to any actual flip, making it hard to read too much into this trend alone. Based on the historical record, an actual flip wouldn't be expected to pose any direct danger to living things, since past flips don't line up clearly with any past mass extinction. The main practical concern would involve a temporary weakening of the overall shield during the long transition itself, potentially exposing modern technology, including satellites and power grids, to more disruption than any living creature would likely ever notice. What lies at Earth's core? Deep beneath our feet, past a thick shell of solid rock, Earth hides a core made mostly of iron and nickel, itself split into two very different layers. An outer layer that stays fully liquid, and sitting at the very center, a solid inner ball, discovered through careful study of how earthquake tremors bend and bounce as they pass through the planet's hidden depths. That solid inner ball manages to stay solid despite being blisteringly hot, roughly as hot as the sun's own visible surface, purely because of the almost unimaginable weight of rock pressing down on it from every direction, which raises the melting point of iron enough to keep it locked solid despite the extreme heat surrounding it. This solid inner ball isn't just sitting still either. It appears to be very slowly growing larger over time, as the surrounding liquid layer gradually cools and solidifies onto its outer surface, releasing both extra heat and certain lighter leftover material that doesn't fit neatly into the newly solidifying iron. That released material rises upward through the surrounding liquid layer, helping to drive the very churning motion responsible for generating Earth's protective magnetic field, discussed in the previous topic, tying the slow growth of this inner ball directly to keeping that protective shield running. A genuinely active and still unresolved puzzle involves how this solid inner ball behaves internally. Careful study of earthquake tremors passing through it has suggested it might spin at a very slightly different pace than the rest of the planet around it, and more recent research has suggested this slight difference in spin may have recently paused, or perhaps even briefly reversed, based on subtle shifts noticed in how tremors from repeated earthquakes travel through it over the years. This particular interpretation remains actively debated, with different research teams studying very similar data, sometimes reaching different conclusions about what's truly happening down there. The core's exact makeup also isn't fully settled. Careful measurements have long shown that the core is slightly less dense than pure iron, and nickel alone would be expected to weigh, hinting that some lighter additional ingredient must be mixed in as well, with several different lightweight candidates still being seriously considered and studied using a combination of earthquake data, high-pressure laboratory experiments, and careful chemical modeling, without a single fully agreed-upon answer yet. Why do supervolcanoes exist? A supervolcano describes a volcanic system capable of unleashing an eruption on a scale dramatically larger than anything witnessed directly within recorded human history, ejecting an almost unimaginable volume of material all at once, dwarfing even the largest eruptions anyone alive today has ever actually seen or recorded. Unlike an ordinary volcano, which slowly builds up a tall, cone-shaped mountain through repeated smaller eruptions, most supervolcanoes don't form a visible mountain at all. Instead, they sit above an enormous underground chamber of molten rock that, once it finally erupts catastrophically, empties out fast enough that the ground above collapses downward into the space left behind, forming a wide sunken bowl in the landscape rather than a rising peak. One famous example in the western United States sits inside a bowl so enormous that it wasn't even properly recognized as a single volcanic feature until aerial photography finally revealed its true overall shape. The underlying cause behind this same volcanic system is generally traced to an unusually persistent and long-lived source of heat rising steadily from deep within the planet, staying in roughly the same underlying spot for an extremely long stretch of time, while the solid ground above it slowly drifts across it, leaving behind a trail of progressively younger volcanic bowls stretching across the landscape, with the currently active bowl simply marking wherever that same deep, persistent heat source currently happens to sit beneath the slowly drifting ground above it. This particular volcanic system has erupted catastrophically a small handful of times throughout its history, and careful study of the molten chamber sitting beneath its current bowl has found that only a fairly modest share of that chamber is actually molten at any given time, with the bulk of it instead being solid, if still very hot, rock, a composition researchers consider inconsistent with the system being anywhere near ready to erupt catastrophically again anytime soon. Exactly what specific conditions ultimately trigger a supervolcano to erupt at one particular moment, rather than continuing quietly for a much longer stretch of time, isn't fully understood, complicated considerably by the simple fact that nobody has ever directly witnessed and carefully measured one of these truly massive eruptions happening in real time, leaving much of the current understanding built from studying the geological aftermath left behind by past eruptions, alongside careful study of far smaller and more frequent ordinary volcanic eruptions instead. Why do continents drift? Earth's outer rocky shell isn't one single unbroken piece. It's cracked into several large plates that drift slowly across the more pliable layer underneath them, moving at a pace not unlike how fast a fingernail grows, a discovery that took decades of careful scientific debate before finally becoming widely accepted. A researcher studying old maps first noticed, long ago, that the continents looked almost like puzzle pieces that could once have fit neatly together, especially the way one continent's coastline seemed to match up remarkably well with another continent lying far across the ocean from it, further supported by matching fossils and matching rock layers found on continents now separated by a vast ocean, evidence that would otherwise require an oddly unlikely coincidence to explain any other way. Despite this compelling circumstantial evidence, The idea that continents had genuinely drifted apart over time was largely dismissed for decades, mainly because nobody could offer a believable explanation for how something as massive as an entire continent could possibly plow its way through solid ocean floor. The missing piece of the puzzle finally arrived once scientists discovered that fresh ocean floor is constantly being created along long underwater ridges and then spreading steadily outward in both directions over time. Evidence found preserved directly within the magnetic striping recorded in that same ocean floor rock, discussed in an earlier topic regarding Earth's flipping magnetic field, paired with the discovery that old, dense ocean floor eventually bends downward and sinks back into the depths at certain deep ocean trenches. This finally gave scientists a complete, workable mechanism explaining how continents really could shift position over the vast stretches of geological time involved. The underlying force driving all of this plate motion is now understood to involve hot rock slowly rising and cooler rock slowly sinking deep within the planet's interior, a large, slow-motion circulation pattern broadly similar in basic principle to currents swirling in a heated pot of water, only unfolding across solid, though still slowly shifting, rock instead of liquid, and playing out over an almost unimaginably long stretch of time. Why Earth, alone among the rocky planets in our solar system, ended up with this kind of cracked drifting shell, rather than one single unbroken shell the way its neighboring rocky planets have, remains an actively studied question, with current thinking pointing toward Earth's abundant surface water, believed to help lubricate and weaken rock enough to allow this kind of large-scale cracking and sliding to happen in the first place, as one of the most likely key ingredients setting Earth apart. What caused Snowball Earth? Long ago, deep in Earth's ancient past, geological evidence shows that thick sheets of ice once formed in places that, according to independent evidence pinpointing where those same rocks originally sat on the globe, were actually located right around the planet's equator at the time. A genuinely striking finding, since the equator normally receives far more direct sunlight than anywhere else, making equatorial ice formation almost impossible under conditions anything like today's. This evidence eventually led researchers to propose that Earth's entire surface, oceans included, may have become completely or very nearly completely covered in ice during this ancient stretch of time. An idea nicknamed Snowball Earth, driven by a runaway feedback loop involving how much sunlight Earth's own surface naturally reflects back into space. Here's how that runaway loop is thought to have worked. As ice sheets slowly crept outward from the poles toward the equator, that growing stretch of bright reflective ice bounced more and more incoming sunlight straight back out into space instead of soaking it up as warmth, driving further, cooling, which then let the ice creep out even farther still, bouncing away even more sunlight in turn, a self-feeding cycle that, once it passed a certain tipping point, could plausibly run all the way to nearly the entire planet becoming ice-covered, since there would be almost no dark, heat-absorbing ocean or land left anywhere to interrupt the runaway cooling. The spark believed to have set this whole runaway cycle in motion traces back to an ancient supercontinent breaking apart around this same general period, which would have exposed considerably more fresh rock to the weather, a process that naturally pulls a heat-trapping gas steadily out of the surrounding air over long stretches of time. With less of that heat-trapping gas left in the air, Earth's overall warmth would have gradually weakened, allowing global cooling to begin and potentially tip over into the runaway ice-reflecting cycle described above. A major remaining puzzle involves how Earth ever managed to escape from this deeply frozen state at all, since a fully ice-covered planet reflecting away so much sunlight would seem unlikely to simply warm back up on its own. The leading idea suggests that volcanic activity, continuing quietly beneath all that ice the whole time, slowly built up heat-trapping gas in the surrounding air over a very long stretch of time, since the usual weathering process that normally removes that gas would have been almost completely blocked by the thick ice cover, eventually building up enough heat-trapping gas to trigger a dramatic and rapid thaw. What triggered the ice ages? Earth has swung through repeated cycles of advancing and retreating ice sheets throughout its more recent geological past, with the most recent especially cold stretch giving way to the milder, warmer period we're living through today. The specific timing of these repeated cold and warm swings turns out to be substantially explained by regular, predictable wobbles and shifts in Earth's own orbit and tilt, worked out in careful mathematical detail by an engineer studying exactly this question nearly a century ago. 3 separate astronomical rhythms combine together to reshape how sunlight gets distributed across Earth's different regions over time, even while the total amount of sunlight reaching the whole planet barely changes at all. One rhythm involves Earth's orbital path slowly shifting between more perfectly round and more stretched out oval shapes over an extremely long cycle. A second involves Earth's tilt itself slowly rocking back and forth between a more upright and a more leaned-over angle, directly affecting how sharp the contrast between summer and winter feels. A third involves a slow wobble in the direction Earth's tilted axis itself points, similar to the wobble of a slowing spinning top, gradually shifting which season lines up with which part of Earth's orbital path over time. Together, these 3 rhythms combine and shift in and out of alignment with one another, altering how much summer sunlight reaches the far northern regions of the planet, a factor that turns out to matter enormously for whether existing ice sheets grow or shrink, since cool enough summers up north allow winter snow to survive without fully melting, gradually building up into an ever larger ice sheet, while warm enough summers melt everything back down each year regardless of how much snow piled up over the preceding winter. Careful study of ancient ocean floor mud, preserving a long, detailed record of past ice volume and ocean temperature, has confirmed that the timing of past ice ages lines up closely with the timing predicted by these same 3 orbital rhythms, offering strong direct support for this explanation roughly a lifetime after it was first proposed. Even so, these orbital rhythms don't fully explain everything on their own. At some point partway through the more recent stretch of repeated ice ages, the dominant rhythm pacing these cold and warm cycles shifted from one of the 3 rhythms to a different one entirely, a switch that still isn't completely understood, and that likely required some additional amplifying factor involving heat-trapping gas levels and the behavior of the ice sheets themselves, working alongside the orbital rhythms to fully explain the shift. Why does lightning form? Lightning is a sudden, powerful release of built-up electrical charge, occurring either within a storm cloud itself or between a storm cloud and the ground below, happening the instant that built-up charge grows strong enough to force its way straight through the surrounding air, which normally resists carrying any electrical charge at all. The resulting flash briefly heats the surrounding air to a temperature several times hotter than the surface of the sun, and that sudden, violent heating is exactly what produces the loud crack of thunder that follows right behind it. Exactly how a storm cloud builds up this much electrical charge in the first place remains, somewhat surprisingly, an area still being actively studied, though the leading explanation points to countless tiny collisions happening between different kinds of ice particles swirling around inside a storm cloud's turbulent updrafts and downdrafts. Small, light ice crystals bump into larger, softer clumps of icy slush, and each of these tiny collisions transfers a small bit of charge between them, generally leaving the smaller crystals positively charged and the larger, heavier clumps negatively charged. Because the smaller, positively charged crystals are light enough to get carried upward by the storm's own rising air currents, while the larger, negatively charged clumps are heavy enough to sink toward the lower part of the cloud, a storm cloud naturally ends up layered, carrying a positive charge up high and a negative charge lower down. This buildup, in turn, encourages a matching positive charge to gather on the ground directly underneath the storm, since the strong negative charge sitting low in the cloud pushes away negative charge in the ground below, while drawing positive charge upward toward the surface. Once the electrical difference built up this way, whether between different parts of the same cloud, between the cloud and the ground, or between 2 separate clouds entirely, grows strong enough to overpower the surrounding air's natural resistance, a lightning strike occurs, beginning with a mostly invisible branching feeler reaching downward or outward in short, stepwise bursts, followed by an extremely bright, fast return flash the instant that feeler connects with a rising response reaching up to meet it, producing the bright flash almost everyone recognizes as lightning itself. Even though the overall electrical structure of a storm cloud is fairly well understood, the exact detailed conditions needed to spark that very first flicker of a lightning strike remain only partly understood, with some researchers suspecting that high-energy particles arriving from space might occasionally help kick off that very first spark by briefly clearing a slightly easier path through the resisting air. Why are there giant crystal caves? Deep inside a mine tucked away in a remote desert region, miners once broke through into a hidden cavern containing some of the largest natural crystals ever found anywhere on Earth. Enormous glassy beams stretching many times taller than a person and weighing as much as a loaded truck, dwarfing anything found in virtually any other known natural setting anywhere in the world. The secret behind these crystals' extraordinary size traces back to the cave's remarkably steady underground temperature, sitting extremely close to the exact specific temperature at which a certain related mineral naturally transforms into the very crystal filling the cave, given enough time and the presence of mineral-rich water. Because the cave's temperature stayed locked in almost exactly at this precise transformation point for an extraordinarily long stretch of time, the crystals were able to grow with almost unimaginable patience and consistency, letting individual crystal structures grow to a far larger size than they ever could under the much faster, messier crystal growth typically found almost everywhere else. The cave sits deep underground, connected to a source of heat rising from below, and it remained completely flooded with mineral-rich water for almost the entire span of time it took these crystals to grow, meaning the growing crystals were essentially never disturbed by shifting temperatures, exposure to open air, or any physical jostling throughout that entire, extraordinarily long growth period. A rare and specific combination of stability researchers consider essential to why these particular crystals grew so much larger than crystals found almost anywhere else on the planet. The cave only became accessible to people at all after mining work pumped away the very water that had shaped and sustained the crystals throughout their entire growth history, and this creates an ongoing and delicate problem. Once removed from that original, stable, water-saturated environment and exposed instead to open air, researchers have found that the crystals slowly begin losing their original shine and gradually breaking down, meaning the very act of reaching and studying this remarkable cave has also quietly begun, hastening the slow decline of the very crystals being studied. Similar, though somewhat smaller, giant crystal formations have since turned up in other nearby passages sharing broadly similar underlying conditions, reinforcing the idea that this specific combination, a steady, geothermally warmed setting, held almost exactly at the right transformation temperature for an extremely long, undisturbed stretch of time, represents a genuine and repeatable natural formula, even though a location meeting every one of these conditions at once remains exceptionally rare to find anywhere on Earth. What causes ball lightning? Every so often, witnesses during or right after a thunderstorm report seeing a glowing, roughly ball-shaped light drifting silently through the air, ranging anywhere from about the size of a small ball to something considerably larger, lingering, and slowly moving, for anywhere from a few seconds up to several minutes, dramatically longer than an ordinary flash of lightning lasts, before eventually fading quietly away. Or, in some accounts, ending suddenly with a small pop and a faint burnt smell lingering in the air afterward. People have reported seeing something like this for centuries, yet it has remained genuinely difficult to study properly, given how rare, unpredictable, and fleeting each sighting tends to be, along with the practical difficulty of ever having proper scientific instruments pointed in exactly the right direction at exactly the right moment to catch one happening in real time. As a result, most of what's known about it still comes largely from eyewitness descriptions rather than direct instrument readings. One genuinely important breakthrough came when researchers, studying an unrelated ordinary lightning strike, happened to accidentally capture a detailed light reading from a naturally occurring instance of this glowing phenomenon at the very same time, revealing the presence of certain elements consistent with vaporized soil, lending real support to an idea proposing that an ordinary lightning strike hitting the ground can sometimes vaporize a small amount of soil. with the resulting vaporized material condensing back together into a glowing, slowly drifting cloud that keeps faintly burning and glowing for some time afterward as it settles and reacts with the surrounding air. Several other explanations remain seriously considered as well, including the idea that it might involve a self-contained pocket of trapped, glowing energy held together briefly by surrounding charged air, or some other brief chemical or electrical process playing out directly within humid air itself without needing any vaporized soil involved at all. Some researchers even suspect that reports of this glowing phenomenon might not all share one single cause at all, and could instead represent a handful of genuinely different, unrelated occurrences that simply happen to look broadly similar and have historically all been lumped together under the very same informal name, further complicating the already difficult task of ever pinning down one single, fully confirmed explanation. Part 10. Ancient Earth. What killed the dinosaurs? The event that wiped out every dinosaur except the ancestors of today's birds, along with a huge share of every other species alive at the time, is now backed by a solid pile of physical evidence pointing squarely at a massive rock falling from space. Researchers first noticed an unusual metal, rare on Earth's surface, but far more common in space rocks, showing up in a thin layer of clay marking that exact moment in the geological record, found at matching sites scattered clear around the entire globe, strongly suggesting a single planet-wide event had spread this same unusual layer everywhere all at once. That suspicion was confirmed once researchers finally identified a massive, buried impact scar hidden off the coast of a peninsula in the Gulf of Mexico, dated to almost exactly the same moment as the mass extinction, and calculated to have been carved out by a rock roughly the size of a small mountain range slamming into the planet. Later drilling straight into the heart of that buried scar helped clarify exactly how a single impact managed to cause a worldwide catastrophe rather than only local devastation. The impact generated intense heat, a colossal wave crashing across nearby coastlines, and most crucially for its worldwide reach, blasted an enormous quantity of vaporized rock and sulfur-rich material high into the sky, where it's believed to have blocked out a significant share of sunlight for a stretch of months to years, triggering a sudden global cold snap and severely disrupting the tiny plant life at the base of the food chain across both land and ocean, collapsing food webs from the very bottom up, all around the world at once. A long-running scientific debate has asked whether the impact alone was enough to cause the full scale of destruction, or whether a separate, massive stretch of ongoing volcanic eruptions occurring around roughly the same time, pouring out lava and toxic gas across a huge stretch of what is now India, may have already been weakening ecosystems worldwide before the impact delivered its final blow. Increasingly precise dating suggests the most intense phase of that volcanic activity began shortly before the impact itself, lending some support to a combined explanation, though most researchers still consider the impact the primary and dominant trigger, given how precisely its timing lines up with the extinction itself. Current research treats the impact as the well-established primary cause, with ongoing interest focused more on exactly how much the volcanic activity contributed alongside it, and on piecing together the detailed chain of environmental collapse, sudden cooling, wildfires, acid rain, and ocean souring that turned one catastrophic impact into the specific, selective wave of extinction actually recorded in the fossil layers. Why did giant insects exist? Fossils from a certain distant stretch of Earth's ancient past reveal insects and their crawling relatives growing to a genuinely startling size, including a dragonfly-like creature with wings stretching wider than a dinner plate, and a millipede-like creature stretching longer than a person is tall, dramatically larger than anything even remotely similar crawling or flying around today. The leading explanation for this ancient gigantism points to Earth's own air, holding noticeably more breathable oxygen back then than it does today, driven largely by the vast swampy forests covering much of the land at the time, whose abundant plant growth pumped out oxygen faster than the slow decay of the era's dead plant matter could use it back up, letting oxygen levels build up unusually high in the surrounding air. This connects directly to how insects actually breathe, since unlike people, Insects don't pump air through lungs at all, but instead rely on a simple network of branching tubes that carry oxygen passively straight to their tissues from small openings along their sides. This passive system becomes noticeably less effective the larger an insect's body grows, since oxygen has to passively travel farther and farther to reach tissue buried deep inside a larger body, placing a natural ceiling on how large an insect can grow under any given level of surrounding oxygen. Careful modern experiments raising ordinary insects in specially enriched, oxygen-rich air have found they do grow noticeably larger than the very same species raised in ordinary air, offering direct, hands-on support for this connection between available oxygen and maximum possible insect size. The pattern isn't a perfectly clean match everywhere throughout the fossil record, though, suggesting oxygen alone may not be the complete story. Other likely contributing factors include the near-total absence, at the time, of any flying vertebrate predators, since neither birds nor their flying reptile cousins had evolved yet, potentially leaving giant flying insects free to occupy the skies without any serious airborne competition or threat. A wide-open opportunity that would later close considerably once flying vertebrate predators finally evolved. Insect body sizes shrank noticeably in the stretch of time following this era, lining up closely with both a documented drop in atmospheric oxygen back toward levels closer to today's and the eventual rise of flying vertebrate predators, offering two mutually reinforcing pieces of evidence, rather than one clearly outweighing the other, with most researchers today treating ancient insect gigantism as most likely the product of both factors working together. Why did Megalodon disappear? An enormous extinct shark once patrolled oceans worldwide, estimated from fossil teeth to have grown several times longer than the largest great white shark alive today, making it among the largest hunting fish ever to have existed anywhere in the ocean's long history. The most well-supported explanation for its disappearance centers on a major cooling of the world's oceans and the resulting drop in sea level that unfolded around the same general period, tied to growing ice sheets forming at the poles. This giant shark is believed, based on where its fossils and likely nursery grounds have been found, to have depended heavily on warm, shallow coastal waters, especially for breeding and raising its young. As the oceans cooled and sea levels dropped, those same warm, shallow coastal habitats would have shrunk considerably and become far less reliably available, placing serious pressure on the species' ability to keep reproducing successfully. A second major contributing factor likely involved fresh competition for food, as early ancestors of today's killer whales and great white sharks began appearing and spreading out around this same general period. Careful reanalysis of the timing involved has suggested this giant shark's disappearance may have actually happened somewhat earlier than once thought, placing it in closer, more direct overlap with these newly emerging rival hunters, lending support to the idea that fresh competition played a real role alongside the shrinking warm water habitat. A related idea points to a shift in available prey. This giant shark is believed, based on bite marks preserved on fossil whale bones, to have hunted whales as a major part of its diet, and the overall mix of whales available as prey shifted noticeably during this same period, with many smaller, warmer water whale species declining, while some whale lineages grew larger and, in some cases, migrated toward the colder polar waters. This shark may have been poorly suited to hunt within, straining its ability to reliably find enough food to sustain its own enormous size. Most researchers today treat the giant shark's disappearance as the combined result of all these pressures working together at once: shrinking habitat, fresh competition, and a shifting prey base, rather than any single cause acting entirely alone, a pattern consistent with how many other major extinctions throughout Earth's history seem to unfold as well. What caused Earth's 5 mass extinctions? Across the long stretch of Earth's history, 5 particularly severe extinction events stand out clearly in the fossil record, each one wiping out a substantial share of everything alive on the planet at the time and each one traced to a somewhat different specific combination of underlying causes, even while certain themes, especially rapid climate change and disrupted ocean chemistry, keep showing up again and again across several of them. The earliest of the five is generally linked to a sudden, severe cold snap and the resulting drop in sea level, followed by an equally sudden warming and rise in sea level once that cold snap ended, a violent 1-2 punch of environmental whiplash that proved devastating to life at the time. The second is most strongly tied to a widespread loss of oxygen throughout the world's oceans, likely triggered as the first proper forests began spreading rapidly across land, dramatically increasing how much nutrient-rich runoff washed into the oceans and fueling algae blooms that, once they died and decomposed, drained huge stretches of ocean water of nearly all of their dissolved oxygen. The third, and by far the most severe of the five, is most strongly tied to an enormous, sustained stretch of volcanic eruptions pouring out immense quantities of heat-trapping and toxic gas over a comparatively short span of geological time, driving rapid warming, severe ocean souring, and widespread oxygen loss throughout the oceans, all happening together at once. The fourth is likewise tied to a massive stretch of volcanic activity, this time connected to an ancient supercontinent beginning to tear itself apart, again releasing enough heat-trapping gas to drive rapid climate change and ocean souring through a broadly similar mechanism to the third extinction, though somewhat less severe overall. The fifth and most recent, discussed in an earlier topic, stands apart from the other four by having a confirmed impact from space as its primary documented trigger, though a stretch of ongoing volcanic activity happening around the very same time may have added further stress on top of it. Looking at all five together, massive volcanic eruptions releasing enormous amounts of gas over a relatively short stretch of time show up as a recurring theme behind at least three, and arguably four, of the five, with rapid climate change, ocean souring, and oxygen loss representing the most common ways these underlying triggers actually translated into widespread extinction, a pattern that has shaped considerable modern concern about how quickly today's climate is currently changing. Could another extinction happen? Careful research over the past couple of decades has documented species disappearing and overall biodiversity declining at a pace many researchers consider comparable to, and in some specific ways possibly exceeding, the pace seen during Earth's past major extinction events, though scientists studying this question are careful to point out important differences in overall scale and stage between today's ongoing biodiversity crisis and the fully completed mass extinctions of the deep past. Careful analysis comparing today's documented rate of species loss among animals, with a backbone against the natural, background rate expected without any added human pressure, has found today's rate running many times higher than that natural baseline, leading a number of researchers to describe the current moment as the early stages of a sixth mass extinction, a description that has since been widely adopted, though always with careful qualification. The specific pressures driving today's biodiversity loss differ somewhat from the primary triggers behind the five historical extinctions discussed in the previous topic. Rather than one single dominant cause like a falling space rock or a massive stretch of volcanic eruptions, today's losses trace to several pressures happening together at once, including the loss and breaking up of natural habitat through farming and city growth, generally considered the single largest contributing factor today alongside overhunting and overfishing. The spread of species into places they don't naturally belong, pollution, and a changing climate, which many researchers expect to become an increasingly dominant factor as it continues intensifying in the years ahead. Unlike each of the five historical extinctions, which are identified and studied only after their complete effects were already fully recorded in the fossil layers, today's crisis is, by its very nature, still actively unfolding, meaning its ultimate final severity can't yet be confirmed with certainty, and remains a matter of informed projection rather than settled fact, depending heavily on how much and how quickly meaningful conservation action actually happens in the years ahead. An influential and widely discussed study examining this exact question found that while today's extinction rate is indeed significantly elevated, the total number of confirmed losses so far remains considerably smaller than the full losses tied to any of the 5 historical mass extinctions, meaning that if today's elevated rate continues unchecked or worsens further, the crisis could plausibly reach a scale comparable to the historical Big Five. But if the trend can be meaningfully slowed through serious conservation effort within a reasonably limited window of time, the final outcome could turn out considerably less severe than those completed events preserved in the ancient fossil record. What was the first animal? Pinning down exactly which kind of creature counts as the very first true animal to ever evolve remains a genuinely unsettled question, made especially tricky by the fact that the earliest animals were almost certainly small and soft-bodied, making them extremely unlikely to have left behind any clear fossil trace at all, leaving much of the relevant evidence resting instead on carefully comparing the genetic makeup of animals alive today. For a long time, simple, sponge-like creatures lacking any nervous system, distinct organs, or muscle tissue were widely considered the most likely candidate for the earliest branch on the animal family tree, since their basic body structure fit neatly with the idea of an early, transitional stepping stone between single-celled ancestors and more elaborate animal groups, an idea supported by a series of genetic comparison studies carried out over the years. This long-standing view was seriously challenged once a different set of genetic studies instead suggested that comb jellies, a group of gelatinous, jellyfish-like sea creatures belonging to an entirely separate branch of the animal family tree, might actually represent an even earlier branching lineage than the simple sponges, despite comb jellies having a working nervous system and muscle tissue that sponges completely lack. This came as a genuine surprise, since it would mean either that comb jellies independently evolved their own, fairly sophisticated nervous system after branching off on their own, or that sponges instead lost a nervous system that had already evolved earlier in some shared ancestor of both groups. This particular debate has continued for years since, with different research teams analyzing different sets of genetic data, sometimes reaching opposite conclusions about which particular branch, sponges or comb jellies, truly split off earlier, showing this remains a genuinely live and technically difficult scientific question, rather than one that's already been fully and conclusively settled. Setting the specific sponges versus comb jellies debate aside, careful estimates based on how quickly genetic differences naturally accumulate over time generally place the true origin of the very first animals well before the later dramatic burst of animal diversity discussed in an earlier topic regarding that sudden explosion of complex life, suggesting animal life got its start slowly and gradually, quietly diversifying for a considerable stretch of time before that later, much more dramatic and much better documented burst of complexity finally took off. Why did mammals suddenly dominate? Mammals actually got their start far earlier than most people assume, appearing well before the extinction that eventually wiped out the dinosaurs, and living alongside dinosaurs for an extraordinarily long stretch of time before that extinction finally happened. Throughout nearly all of that long stretch living alongside the dinosaurs, mammals stayed small, ecologically limited, and fairly modest in variety, generally understood to reflect how thoroughly dinosaurs dominated the vast majority of land habitats and ecological niches during that same long stretch of time. Once the dinosaurs were wiped out, mammals underwent a striking and comparatively rapid burst of diversification and growth in body size, generally credited to the sudden disappearance of dinosaurs as dominant competitors, which opened up a wide range of previously occupied ecological roles, including larger plant-eating and hunting roles, that surviving mammal lineages were then free to expand into without facing the same degree of competition and predation risk they had faced throughout the earlier era. Detailed fossil evidence has helped clarify just how quickly this post-extinction burst actually unfolded, with the major mammal lineages eventually leading to today's familiar groups beginning to rapidly diversify within a remarkably short window of time right after the extinction, a genuinely rapid pace of evolutionary change by ordinary geological standards, lending strong support to the idea that sudden ecological opportunity, rather than anything else, was the primary driver behind mammals' rapid diversification and growth after the extinction. An important further piece of this story asks why mammals, specifically rather than birds or reptiles, were so well positioned to seize this sudden opportunity. Researchers have pointed to several mammalian traits that likely offered a real advantage during the harsh, dark, food-scarce period immediately following the impact discussed in an earlier topic, including mammals' warm-blooded metabolism, letting them stay active even as the world darkened and cooled. Their generally small size and flexible generalist diets, letting many species survive on whatever limited food happened to be available when larger, more specialized feeders struggled, and their generally burrowing or nocturnal habits beforehand, which may have offered some built-in shelter from the very worst immediate effects of the impact itself. Taken together, mammalian dominance following the extinction of the dinosaurs appears to have resulted from the sudden removal of dominant competitors, opening up wide ecological opportunity, combined with several pre-existing mammalian traits that happen to confer a real survival edge during the immediate crisis, letting mammals both survive in greater numbers than many other groups and quickly expand afterward into the wide range of niches the dinosaurs left behind. Did ancient oceans hide unknown giants? The fossil record keeps revealing that Earth's ancient oceans once held marine animals considerably larger and sometimes structurally quite different from anything swimming in today's oceans, with new discoveries continuing to reshape how large and how early these ocean giants first appeared, suggesting current knowledge of these ancient giants is still far from complete. One especially striking example involves a group of dolphin-shaped marine reptiles that thrived for a long stretch of Earth's ancient past. A large jawbone fossil discovered washed up on an ordinary beach alongside a handful of other significant recent finds has suggested that certain species within this group may have reached a length rivaling or even exceeding the largest whale alive today, hinting that some of these ancient reptiles achieved a scale of ocean gigantism not fully appreciated until fairly recently, and raising a genuinely interesting and actively studied question about how a body plan so different from a modern whale's could have reached such an enormous size in the first place. Beyond that particular group, the fossil record has also turned up several other notably large ancient ocean predators whose full size and role continue to be refined through ongoing study, including an extinct relative of the sperm whale equipped with what may be the largest confirmed teeth of any known predator and a group of short-necked marine reptiles, one especially large and well-documented specimen suggesting a length and bite force among the strongest ever calculated for any known animal, living or extinct. This steady pattern of newly discovered fossils continuing to reveal previously unknown or underestimated ancient ocean giants, even quite recently, reflects both genuine ongoing discovery, since huge stretches of the fossil record, especially from ocean environments, remain only partly explored, and the simple fact that large animals are naturally much rarer to fossilize successfully in the first place. Since fossilization requires an uncommon and specific combination of favorable conditions, meaning the full range of sizes and species that once lived in ancient oceans is very likely still only partly represented in what's been found so far. It's worth drawing a clear line between this genuine, ongoing pattern of confirmed fossil discovery, revealing real, physically documented giant species from Earth's deep past, and unconfirmed popular speculation about undiscovered living giants persisting secretly in today's oceans, a separate topic addressed elsewhere in this series, since every ancient giant discussed here is understood, based on the fossil record and past extinction events, to have died out long ago rather than surviving quietly into the present. Could intelligent dinosaurs have evolved? A well-known thought experiment asks what might have happened to dinosaur intelligence if the extinction event that wiped them out had never occurred. Built originally around a small, unusually large-brained hunting dinosaur, used as a starting point for imagining what a distant future descendant might have eventually looked like had that lineage kept evolving uninterrupted for many more millions of years. This particular imagined future descendant, envisioned with a more upright, human-like body, has faced considerable pushback in the years since it was first proposed, mainly because evolution doesn't march toward any predetermined destination or fixed body shape at all, but instead responds opportunistically to whatever pressures and existing anatomy a given lineage happens to already have, meaning there's no solid reason to expect an intelligent dinosaur descendant would have specifically ended up looking anything like a person, rather than developing along an entirely different path better suited to its own particular starting point. The small hunting dinosaur. This idea was originally based on genuinely does stand out for having an unusually large brain relative to its body size, along with other features hinting at fairly sharp senses, including notably large eyes suited for good night vision. Even so, this brain-to-body ratio, while impressive for a dinosaur, still falls well short of today's smartest birds and mammals, let alone anything resembling human-level thinking, meaning any imagined future leap toward greater intelligence would still have required an enormous, entirely speculative amount of further evolutionary development. A further important point comes from birds themselves, now understood to be direct descendants of small feathered dinosaurs, technically making them a surviving branch of the dinosaur family tree and offering a genuinely useful real-world test case. Several modern bird groups have independently evolved remarkably sharp thinking abilities, including tool use and complex problem-solving, long after the extinction event, and despite not being closely related to that original hunting dinosaur at all, suggesting the broader dinosaur lineage carried real underlying potential for sharp intelligence, even though that potential ended up realized within surviving bird descendants rather than within any dinosaur alive before the extinction. Overall, whether non-bird dinosaurs would have eventually evolved anything resembling human-level intelligence remains fundamentally unanswerable with any real confidence, since evolution follows no single predictable path, though the real intelligence seen in today's birds offers some genuine support for the more modest idea that dinosaurs, broadly speaking, did carry real potential for developing considerable mental sophistication, given enough time. What species will come after humans? Wondering which creatures might eventually rise to fill dominant ecological roles following some future decline in human presence is a genuinely reasonable line of thinking, grounded in the well-documented historical pattern, discussed throughout this part of the series, in which major extinction events have repeatedly opened up fresh ecological opportunity for whichever creatures happen to survive them, exactly as mammals did after the dinosaurs disappeared. A well-known older book exploring exactly this question used solid, established evolutionary and ecological principles to imagine a detailed hypothetical future in which today's mammals, birds, and other creatures diversify to fill roles left behind by a hypothetical human decline. A work explicitly meant as thoughtful speculation rather than a firm scientific forecast, even while drawing on genuinely sound underlying principles about how new ecological opportunity tends to get filled. From a more careful scientific standpoint, researchers studying this kind of question generally stress that predicting exactly which specific creature might rise to dominance is inherently far too speculative to forecast with any real precision, given how unpredictable and dependent on chance events the whole process of evolution genuinely is. Even so, a few broad, well-supported principles offer some grounded basis for informed, if still fairly general, speculation. Creatures that are already flexible generalists, spread widely across many different environments and able to eat a wide range of different foods, tend, based on the historical pattern following past extinctions, to be more likely candidates for rapid future diversification than narrowly specialized creatures tied closely to just one particular habitat or food source, since generalists tend to survive a broader range of sudden disruption in greater numbers and carry more built-in flexibility to adapt afterward into newly available roles. Researchers have specifically pointed to certain highly adaptable and already widespread creatures, including generalist rodents, unusually sharp thinking and adaptable birds, and a handful of highly flexible mammals, as plausible, though entirely speculative, candidates for significant future diversification based on their current flexibility and wide distribution. This whole line of thinking depends heavily on exactly what kind of future decline actually happens, which other creatures happen to survive alongside or after it, and what conditions prevail afterward, none of which can be predicted with any real certainty. It's best understood not as an actual forecast of a specific future outcome, but as a way of applying well-established evolutionary and ecological principles drawn from Earth's own documented past to a deliberately hypothetical and genuinely unpredictable future scenario. Part 11. The Ocean's Mysteries. What lives in the Mariana Trench? Tucked into the western Pacific Ocean lies the deepest known point in any of Earth's oceans, a place so deep that if the tallest mountain on the planet were dropped straight down into it, its peak would still sit far below the surface. Conditions down there are extreme even by deep ocean standards, crushed under staggering pressure, chilled near freezing, and completely without a single ray of sunlight, ruling out anything resembling plant life as a food source. Despite all that, direct exploration has confirmed a genuinely surprising variety of life clinging on down there. The very first manned descent all the way to the bottom reported spotting what looked like a flatfish resting on the seafloor, and later trips using unmanned equipment have confirmed small shrimp-like creatures, sea cucumbers, and, at the very deepest points of all, giant, single-celled blobs large enough to see without a microscope, despite consisting of just one single cell. Confirming that actual fish live down at these crushing depths took considerable patience, eventually turning up a ghostly, pale, and remarkably deep-dwelling species of snailfish, currently the deepest living fish ever directly confirmed anywhere. Fish appear to hit a hard depth limit somewhere beyond that, past which no fish has ever actually been found, thought to be tied to how difficult it becomes, at such extreme pressure, for a fish's cells and proteins to keep functioning properly, while creatures without a rigid internal skeleton, including small shrimp-like animals and single-celled blobs, appear able to tolerate even greater pressure still. Creatures living at these crushing depths have picked up a clever chemical trick to survive, building up unusually high levels of a particular natural compound known to help stabilize proteins against the kind of pressure-driven distortion that would otherwise wreck normal cell function. The deeper a fish species is normally found living, the more of this compound its body reliably carries, offering a clear, direct explanation tied closely to why fish simply cannot survive much beyond a certain crushing depth. Even after decades of dedicated deep-sea research, scientists studying these deep trench ecosystems generally agree that only a small sliver of the total area down there has ever actually been directly explored and sampled, given how difficult, costly, and specialized the equipment needed to operate reliably at these extremes really is, meaning new creatures and previously unknown adaptations keep turning up with pretty much every fresh expedition specifically aimed at these deep trenches. Why is so little of the ocean explored? Most estimates from ocean scientists suggest that the large majority of the world's oceans remain completely unmapped and unexplored in any real, detailed sense, a genuinely striking fact given how thoroughly people have already mapped every stretch of dry land and even the surface of the Moon and other planets, and one that comes down to a handful of specific, well-understood practical obstacles rather than any lack of scientific interest. The most basic obstacle is simply that seawater blocks the very kind of light and radio signals normally relied upon for mapping from orbit, the same tools that work beautifully for mapping land and even distant planetary surfaces. Sunlight only penetrates the ocean's uppermost layer in any useful way, and radio signals get absorbed within just a short distance of hitting the water's surface, meaning mapping the deep ocean floor in any real detail requires a fundamentally different approach altogether than the light-based tools that work so well everywhere else. The main tool actually used to map the ocean floor relies on sound rather than light, since sound travels efficiently through water and can measure depth and terrain by carefully timing how long it takes an emitted pulse to bounce back off the seafloor below. The trouble is that this kind of detailed mapping generally requires a ship to physically travel slowly across the ocean's surface while continuously running its equipment, meaning fully mapping the entire ocean floor at high resolution. This way would take an enormous amount of ship time and funding sustained over many years, a global effort that, despite genuine dedicated international projects working toward exactly this goal, remains far from finished even now. Beyond simply mapping the physical seafloor terrain, actually sampling and studying whatever creatures live down there presents an even bigger practical challenge still, since that requires specialized deep-diving equipment built to withstand crushing pressure, a considerably more expensive and technically demanding task than mapping terrain alone, meaning even ocean regions already reasonably well mapped often remain far less thoroughly studied when it comes to what actually lives there. A meaningful part of the gap also simply comes down to funding priorities, since space exploration has historically received considerably more dedicated funding than ocean exploration, a disparity ocean scientists frequently point to, even while acknowledging that the ocean genuinely does present its own distinct set of technical hurdles, separate from anything involved in exploring space, that have likewise slowed down how much of it has been properly explored so far. What causes rogue waves? A rogue wave is an unusually massive ocean wave that towers dramatically above the surrounding waves around it, far larger than anything the surrounding sea conditions would normally suggest. And for a long time, most scientists dismissed persistent stories about waves this size as little more than exaggerated sailors' tales, until a wave exactly matching these old stories was finally caught directly on precise instruments out at sea. That instrument reading, recorded by sensors mounted on an oil platform out at sea, showed a single towering wave rising to more than double the height of every surrounding wave measured at the very same moment, offering the first unmistakable, precisely measured proof that waves of this extreme and unusual size really do occur in nature, sparking a genuine wave of serious scientific research afterwards, specifically trying to understand how. Several distinct explanations have since been confirmed as real, contributing causes, with their relative importance shifting depending on location and conditions. One straightforward explanation involves several separate wave systems traveling at different speeds or from different directions, happening to align and add their heights together at one particular moment and place, a fairly simple extension of ordinary wave behavior, though this kind of simple stacking alone doesn't appear to be enough on its own to explain the very largest rogue waves ever recorded. A second, more subtle explanation involves a group of waves traveling closely together somehow, funneling extra energy from their neighbors into a single, much larger wave, effectively stealing height from the waves around it in a way ordinary simpler wave models don't fully predict, a mechanism that has since been successfully recreated and confirmed inside a controlled laboratory wave tank. A third contributing factor, especially relevant in a handful of specific coastal regions long known among sailors for producing unusually frequent giant waves, involves a strong ocean current flowing directly against the usual direction waves are traveling, which compresses and steepens the approaching waves considerably, boosting their height well beyond what calmer current conditions would ever produce, helping explain why certain stretches of ocean earned a dangerous reputation among sailors long before the underlying physics was ever properly understood. Most researchers now treat rogue waves as arising from some mix of these confirmed mechanisms, working together under just the right combination of conditions, rather than any single explanation covering every documented case on its own, with current research increasingly focused on forecasting which conditions carry the highest risk. Valuable information for the safety of ships and offshore platforms working in affected waters. Why do whales sing? Male humpback whales produce long, elaborately structured sequences of sound, built from repeating patterns arranged into clear, consistent phrases, sometimes stretching on for hours at a time. And once researchers finally sat down and carefully analyzed these sounds in detail, they found a surprisingly organized, almost musical structure running through them, far more deliberate than simple random noise. The most well-supported explanation for why these whales sing points toward reproduction, since this singing is produced almost entirely by males, mostly during the breeding season, and its overall pattern closely resembles mating displays documented in plenty of other animals, where males use an elaborate show specifically to attract a mate or to signal their own status to rival males, though exactly which of these two specific purposes matters more has remained an active question researchers continue investigating. One especially striking feature of this whale song is that every male within a given group of whales tends to sing a broadly similar song at any given time. Yet that shared song keeps slowly shifting and evolving from one breeding season to the next. Researchers have even documented a completely new song pattern, one that first appeared among a group of whales on one side of an ocean, gradually spreading clear across an entire ocean basin over the course of just a few years, revealing a genuine form of shared cultural learning, passing between whale groups that's considered highly unusual among animals generally, since most animal sounds tend to stay fairly fixed and instinctive, rather than shifting and spreading this way over time. Beyond humpback whale song specifically, other whales make their own distinct sounds serving different purposes. Sperm whales produce patterned bursts of clicks that seem to function almost like distinct dialects, helping tell apart separate whale family groups from one another, and the largest whales of all produce extremely deep, low sounds capable of traveling vast distances underwater, likely helping widely scattered individuals stay in contact and coordinate across huge stretches of open ocean. While the broad reasons whales make these sounds, mating, social bonding, and long-distance contact, are reasonably well understood, exactly what specific meaning, if any, is carried within particular song patterns or click sequences, and just how much individual whales are capable of learning, sharing, and perhaps even having something like a real back-and-forth exchange, remains an active and rapidly developing area of ongoing research. What creates bioluminescence? Deep in the ocean's permanently dark middle layer, the overwhelming majority of creatures living there carry some ability to produce their own glowing light, making this one of the most widespread traits found anywhere in that particular stretch of ocean, in sharp contrast to how rare the very same trait is among land animals and creatures living in shallower, sunlit water. The chemistry behind this glow generally comes down to a light-producing substance reacting with a helper enzyme, releasing the resulting energy almost entirely as light rather than wasted heat, making it a remarkably efficient way to produce light compared to most artificial lighting built by people. Interestingly, this particular chemical combination isn't one single, universally shared recipe across every glowing creature. It has evolved independently from scratch multiple separate times across quite different, only distantly related branches of the animal family tree, suggesting that the advantage of producing light in a permanently dark ocean has been strong enough to push this same basic trick into existence again and again through several entirely separate underlying chemical pathways. Deep-sea creatures put this glow to work in several distinct and clearly documented ways. Many use it to hunt, including one especially well-known creature that dangles a glowing lure directly in front of its own mouth, specifically to draw curious smaller prey close enough to strike. Others use a sudden bright flash defensively, momentarily startling and confusing an approaching predator, and some squid even release a glowing cloud into the surrounding water as they flee, working much like an ordinary ink cloud does for creatures living in shallower, sunlit water. One particularly clever defensive trick involves certain creatures glowing softly along their undersides in a pattern carefully matched to the faint light still filtering down from the sunlit surface far above, effectively erasing their own silhouette from the perspective of a hungry predator glancing upward from below, where an ordinary, non-glowing body would otherwise stand out sharply against the brighter water overhead. Some of these creatures can even actively adjust exactly how bright their glow needs to be in real time, matching whatever faint light happens to be filtering down at that particular moment. Beyond hunting and hiding, many deep-sea creatures also use their own specific glowing patterns and flashing sequences to recognize and attract a potential mate in the vast, dark, and otherwise featureless open ocean, serving much the same basic evolutionary purpose that a colorful display or a mating call serves for creatures living somewhere brighter or quieter. Are there unknown giant sea creatures? An enormous tentacled sea creature, already known to science and confirmed through washed-up remains for a very long time, wasn't actually photographed alive in its own natural deep ocean home until remarkably recently, with proper video footage of one swimming freely in the deep sea not captured until years after that first photograph. This shows that even an already confirmed already scientifically named giant creature can remain completely unseen alive in its natural habitat for a very long stretch of time, simply because actually finding and filming a large roaming deep-sea animal in the wild is genuinely difficult. This well-documented difficulty offers useful context for thinking about whether other, still entirely undiscovered, giant sea creatures might exist somewhere out there. Given how remarkably hard it proved to directly film even an already confirmed and comparatively well-studied giant creature, it seems entirely plausible, and is taken seriously by many marine biologists, that other large deep-sea creatures, not yet formally identified at all, could still be swimming around undiscovered, especially given how much of the deep ocean remains completely unexplored. New large sea creatures continue to be formally confirmed fairly regularly, showing this remains an active, ongoing process. A previously unrecognized species of deep-diving whale, a group already notoriously hard to study given how deep they dive and how briefly they surface, was formally confirmed as genuinely distinct not too long ago, based on careful genetic study of animals found stranded on distant coastlines, showing that entirely new large sea mammals, not just small invertebrates, continue turning up even in fairly recent times. It's worth drawing a clear line between this genuine pattern of real discovery, which happens through legitimate methods, including genetic testing, deep-sea cameras, and study of stranded animals, and unconfirmed popular stories about specific legendary sea monsters, for which no verified physical evidence has ever turned up, despite considerable searching. Marine biologists generally stay open to undiscovered large sea creatures broadly similar to ones already known, while holding a far higher bar of evidence toward more dramatic, unprecedented claims that would overturn established biological understanding. Given the ocean's track record of hiding large creatures in plain sight, the honest, scientifically grounded answer is that more undiscovered giants very likely remain out there somewhere, quietly waiting to be found, particularly in the depths and distances farthest from regular human observation. Why are deep-sea animals so strange? Creatures living down in the ocean's deep, permanently dark layers have evolved a whole collection of genuinely bizarre features, including greatly oversized eyes, or in some especially deep-dwelling cases, no proper eyes at all, jelly-like see-through bodies, disproportionately huge mouths and stretchy stomachs, and, as discussed in an earlier topic, glowing light-producing patches, each one traceable to specific, well-understood pressures created by the deep ocean's genuinely extreme combination of conditions. The near-total absence of sunlight below a certain depth creates strong pressure either toward maximizing whatever faint light might still be detectable, including both the very last trace of filtered sunlight and any glow produced by nearby creatures, or, for creatures living somewhere, light never reaches at all, toward abandoning eyesight altogether. Since maintaining working eyes and the brain tissue needed to process what they see carries a real ongoing energy cost that provides no benefit whatsoever in a place with nothing at all to see. Scarce food represents a second defining condition shaping life down there, since the deep ocean depends almost entirely on a slow, thinning trickle of drifting organic material sinking down from the sunlit waters far above. This scarcity has driven oversized, hinged jaws and remarkably stretchy stomachs in several deep-sea creatures, letting them swallow and fully digest unusually large meals relative to their own size whenever a rare chance to eat comes along, since counting on a second decent meal, turning up soon, simply isn't a safe bet down there. Crushing water pressure, growing heavier the deeper you go, represents a third major pressure, generally favoring soft, water-rich, jelly-like bodies over the more rigid, mineralized bone and muscle favored in shallower water and on land, since maintaining rigid structures against crushing pressure demands far more energy than relying on soft, pressure-resistant, and far cheaper jelly-like tissue instead. The especially unusual mating habits seen in some deep-sea anglerfish, where a much smaller male permanently attaches to a much larger female's body, surviving as little more than a permanent source of sperm, reflects a direct adaptation to how thinly populated the deep ocean truly is, making a second-chance encounter with a mate extremely unlikely. Showing how this single shared set of pressures, darkness, scarcity, and isolation has repeatedly shaped the strange appearance deep-sea creatures are known for. What are underwater brine pools? Certain patches of the ocean floor host something genuinely strange. Pools of extremely salty, unusually dense water sitting directly on the seafloor, forming a clearly defined pool, complete with its own distinct surface and shoreline, almost like a small lake resting quietly beneath the surrounding ordinary seawater above it, made possible because the pool's much higher salt content makes it considerably denser than the ordinary seawater around it, keeping the two from mixing together the same way oil and water stay visibly separate. These pools generally form in one of two well-understood ways. In certain ocean basins, ancient buried salt deposits, laid down long ago when the region was once a shallow sea that later dried up, slowly dissolve as water seeps through cracks in the rock above them, with the resulting extremely salty, dense mixture eventually seeping back out onto the seafloor and pooling in low spots because it's so much denser than the ordinary water surrounding it. In other locations, underlying volcanic and geological activity generates strong, localized heat that drives water to dissolve minerals out of the surrounding rock instead, again producing an unusually dense, salty mixture that pools the very same way. The chemistry inside these pools can be extreme, even by the standards of the deep ocean, sometimes carrying substantial amounts of dissolved toxic gas, making the water directly inside these pools lethal to almost any ordinary sea creature that happens to wander in, an effect researchers have actually filmed happening in real time, with the pool's edges sometimes littered with the preserved remains of creatures that didn't manage to avoid it, leading some to informally describe certain of these pools as underwater lakes of death. Despite that toxicity right at the pool's center, the boundary ringing its edge often supports a surprisingly rich community of life, generally powered by specialized bacteria that draw usable energy directly from chemically breaking down the toxic compounds dissolved in the brine, rather than relying on sunlight at all. These bacteria, in turn, support nearby mussels, tube worms, and other creatures that have evolved a close partnership with them, generally by hosting the bacteria directly inside their own bodies and receiving nutrients in exchange for offering the bacteria a safe, sheltered home. These strange pools have drawn particular interest from scientists studying whether life might survive under similarly extreme conditions elsewhere in the solar system, since this same combination, extreme saltiness, total darkness, and chemistry-powered life, is considered a reasonably close match for the kind of hidden ocean believed to exist beneath the icy shells of certain distant moons discussed elsewhere in this series. Why do some fish glow? Fish make up one of the largest, most varied, and most thoroughly studied groups of glowing creatures anywhere in the deep ocean, giving researchers an unusually rich set of examples for studying exactly how and why this particular trick evolved so many separate times. Careful study comparing the family trees of glowing fish species has found that the ability to glow evolved independently, dozens of separate times across entirely different fish lineages, a striking sign that producing light is a strongly favored trick under deep ocean conditions, repeatedly rediscovered from scratch rather than passed down once through a single shared ancestor. The same research also found that fish lineages that evolved the ability to glow tend afterward to branch out into a noticeably larger number of separate species than their closest non-glowing relatives, suggesting that gaining the ability to produce light opens up meaningful new evolutionary opportunity, plausibly by enabling new ways to hunt, new ways to avoid being hunted, and new ways to signal a potential mate that non-glowing rivals simply don't have access to. One particularly well-studied glowing fish doesn't actually produce its own light through its own body chemistry at all, but instead hosts colonies of separate glowing bacteria living inside a special light-producing pouch just beneath each eye, with the fish itself able to actively control when that light shows by physically rotating the pouch or covering it with a small flap, giving it real behavioral control over its own glow, even though the bacteria themselves are simply glowing away continuously on their own the whole time. A well-known deep-sea anglerfish, instantly recognizable by its glowing lure, works the very same way, relying on its own hosted colony of glowing bacteria rather than producing the glow directly itself. And different anglerfish species turn out to host different specific bacteria within their lures, with the particular bacteria matching closely to the anglerfish's own family lineage, hinting at a long, closely paired evolutionary partnership between each specific anglerfish lineage and its own particular bacterial partner. By contrast, other deep-sea fish, including some of the most numerous fish anywhere in the deep ocean, produce their glow directly through their own internal chemistry without needing any bacterial partner at all. This shows that fish have arrived at glowing through at least two entirely different underlying methods, producing it directly themselves or hosting bacteria that do it for them. This offers a particularly clear example of how distantly related creatures can independently stumble onto a strikingly similar trick through genuinely different underlying paths, all in response to the same powerful pressure of living somewhere permanently dark. What lies beneath Antarctic ice shelves? Buried beneath Antarctica's thick ice sheet sit hundreds of hidden lakes of liquid water, trapped far below the surface and kept from freezing solid by a combination of heat rising up from deep within the planet and the sheer insulating weight of all that ice pressing down from above, keeping these lakes liquid even while the surface far above regularly plunges to brutally cold temperatures. The largest and most thoroughly studied of these hidden lakes was first confirmed to exist through careful radar surveying, and turns out to be one of the largest lakes on Earth by volume, believed, based on the surrounding geology, to have remained completely sealed off from the outside air and from sunlight for an extraordinarily long stretch of time, making it one of the most thoroughly isolated bodies of water found anywhere on Earth's surface. A dedicated research team eventually managed to drill carefully all the way down through the ice and reach this lake's water directly, taking great pains to avoid contaminating its pristine, long-isolated water with anything from the surface. Analysis of ice that refroze inside the borehole from the lake's own water has turned up signs of diverse microscopic life living down there, including some distantly related to microbes found in other extreme environments elsewhere on Earth, though these particular findings have required careful, ongoing double-checking, given legitimate concerns about whether surface microbes might have slipped in during the drilling process, despite every precaution taken. A separate hidden lake, sitting beneath a considerably thinner covering of ice and therefore easier to reach, was successfully sampled by a different research team using specially designed clean drilling equipment, confirming a genuinely diverse and actively living community of microbes drawing their energy directly from chemical reactions involving compounds present in the lake's own sediment and water, rather than relying on sunlight at all, offering solid, direct proof that a complete self-sustaining microbial community really can survive for a very long stretch of time in complete isolation beneath thick Antarctic ice without needing any outside energy at all from the sunlit world above. These confirmed discoveries of thriving microbial life surviving in complete isolation beneath thick ice have drawn considerable extra interest from scientists studying the chances of life existing elsewhere in the solar system, since these hidden Antarctic lakes are widely considered among the closest and most useful Earth-based comparisons available for studying the kind of hidden, icy ocean believed to exist on certain distant icy moons discussed elsewhere in this series. Part 12. Mathematical Mysteries. Why does mathematics describe reality? Mathematics grew up largely as its own separate, abstract pursuit, often explored purely for the sake of its own internal logical beauty, with no particular real-world use in mind. And yet, again and again, it has turned out to precisely describe physical phenomena discovered or even invented long after the relevant mathematics was originally worked out. A pattern one physicist famously described as a kind of miracle that is neither fully understood nor obviously deserved. Consider a branch of geometry describing oddly curved surfaces, worked out purely as an abstract logical curiosity by mathematicians exploring what would happen if a certain ancient geometric assumption were changed, with absolutely no anticipated physical use at the time. Decades later, this exact same abstract geometry turned out to be precisely the tool needed to describe how massive objects bend space itself. or consider a strange kind of number, involving the square root of a negative value, first developed purely to help solve certain awkward algebra problems and treated with real suspicion for a very long time regarding whether it meant anything physically real at all, only for it to later become an absolutely essential tool for describing the strange behavior of tiny particles. A few different explanations have been seriously proposed for why this pattern keeps happening. One explanation suggests it's less mysterious than it first seems, since mathematicians have already explored such an enormous range of possible abstract structures over history that it wouldn't be too surprising for some portion of that already existing toolkit to happen to match some later real-world discovery, purely as a matter of how much ground has already been covered. A second explanation suggests mathematics was never fully separate from physical reality to begin with, having originally grown directly out of very basic physical activities like counting objects and measuring space, meaning its usefulness for describing the physical world is less surprising once you realize it was drawn straight out of that same physical world from the very start. A third, more striking explanation suggests mathematics describes reality so well because reality, at the deepest level, might actually be identical to a mathematical structure, rather than merely being described by one, meaning the fit between the two isn't a coincidence at all, but a single underlying fact wearing two different names. No single explanation has earned full agreement, and this pattern remains an open and genuinely fascinating puzzle sitting quietly underneath the entire practice of physics, which relies completely on math being trustworthy without ever fully explaining why it should be. What is infinity? Infinity describes a quantity with no final limit or end, and for a very long stretch of mathematical history, it was treated with real caution and suspicion, with early thinkers drawing a sharp line between an endless, ongoing process, like counting upward forever without ever reaching a largest number, considered perfectly sensible, and a fully completed, actually finished infinite quantity, treated as one single object, considered deeply troubling or perhaps even meaningless. That old caution was completely overturned by one mathematician who developed a fully rigorous way of treating completed infinite collections as legitimate objects that could be precisely compared and worked with using clear, well-defined rules. His single most surprising discovery was that not every infinity is the same size. The endless collection of ordinary counting numbers and the endless collection of every possible point along a continuous line turn out to be different sizes of infinity, with the second being, in a precise and carefully proven sense, strictly larger than the first, despite both stretching on forever. He proved this using an elegant argument showing that no matter how you tried to build a complete list, pairing up every counting number with a matching point along that continuous line, it would always be possible to construct one further point that had been left off the list entirely, proving the two collections could never be fully matched up one-to-one, and therefore couldn't be the same size of infinity after all. He then went further still, proving that for any given infinite collection, you can always build an even larger one from it, meaning there's no single largest infinity anywhere at all, only an endless, ever-climbing staircase of increasingly larger infinities stretching upward without any final top step. This entire way of thinking faced serious resistance from other mathematicians at the time who considered treating completed infinity this way to be fundamentally illegitimate, though it was eventually embraced and now sits at the very foundation of modern mathematics. Even so, one very specific and basic question, whether any size of infinity exists strictly between the two sizes discussed above, has been formally proven to be permanently unanswerable using math's own standard foundational rules, a genuinely remarkable result showing that even some of the most basic questions about infinity's structure may simply never be settled at all. Do numbers exist independently? A long-running and genuinely unsettled debate asks whether numbers and other mathematical objects exist as real things out there in some sense, waiting to be discovered rather than invented, or whether they exist only as useful ideas inside human minds with no independent existence of their own beyond the people who think about them. Those who believe numbers are genuinely real point to how mathematical truths seem to hold with a kind of unshakable necessity, quite unlike ordinary facts about the physical world. A properly proven mathematical fact once established seems true not merely as a pattern observed so far, but as something that could never have turned out otherwise, holding the exact same way regardless of anything about our particular universe, suggesting to believers in this view that mathematical truths describe some separate, unchanging realm existing independently of and prior to any physical universe or any mind capable of thinking about it. Believers in this view also often point to how completely separate thinkers, working entirely independently and unaware of one another's work, have repeatedly stumbled onto the exact same mathematical discoveries throughout history, arguing this is best explained by both of them having genuinely discovered the very same pre-existing truth, much like two separate explorers independently finding the same hidden island, rather than each one simply inventing their own private fiction that happened, by sheer coincidence, to match perfectly. Skeptics of this view raise a serious counter-problem. If numbers really do exist as fully real things, they'd have to exist entirely outside ordinary space and time, since numbers have no physical location or mass at all, which raises an awkward question about how physical human minds, which learn about the world only through ordinary physical senses, could possibly gain reliable knowledge of something existing entirely outside of physical space, time, and any possible ordinary interaction with our physical brains. An alternative view suggests mathematical statements should instead be treated as useful, internally consistent fictions, similar in a sense to statements describing characters in a novel, judged by whether they're logically consistent and useful within their own framework, without requiring that the mathematical objects being discussed actually exist as real things at all. This entire debate remains genuinely unsettled, with thoughtful mathematicians and philosophers holding sincerely different views across the whole spectrum. Why is pi infinite? Pi, the precise ratio between a circle's distance around its edge and the distance straight across its middle, belongs to a special category of numbers that can never be written exactly as one whole number divided by another, meaning its decimal digits continue forever without ever settling into any repeating pattern, a property mathematicians finally proved with full certainty long after ancient civilizations had already begun studying and closely estimating pi's value. This becomes clearer by comparing pi to an ordinary fraction like 1/3, whose decimal form does repeat the very same digit over and over forever in a perfectly simple, predictable pattern. Pi's own digits, by contrast, show no such repeating pattern at all, no matter how many trillions of digits have been carefully calculated and checked, appearing instead to behave with genuine, structureless randomness, with every single digit from 0 through 9 turning up roughly equally often throughout. Beyond simply never repeating, pi carries an even deeper mathematical property. It can never be produced as the exact solution to any ordinary algebra equation built using only whole numbers and fractions, no matter how complicated that equation is allowed to be. Proving this carried a genuinely important historical consequence, since it finally and permanently settled an ancient geometric puzzle that had occupied mathematicians for well over 2,000 years, definitively proving that a particular classic geometric construction, attempting to build a square with exactly the same area as a given circle using only the simplest ancient drafting tools, is mathematically impossible to achieve. Because pi's digits never repeat, calculating an ever larger number of them has become a popular way to test and show off the raw power of the newest supercomputers, with the current record already stretching into many trillions of digits. It's worth noting, though, that actually using pi for any real practical purpose requires vastly, almost laughably fewer digits than that, since even a modest number of decimal digits is already more than precise enough to calculate the exact distance around the entire visible universe to an accuracy finer than the width of a single atom, meaning these extreme record-breaking calculations mostly serve to test computing technology itself rather than serving any genuine scientific necessity. Pi's specific properties aren't even especially unusual among numbers generally, since it turns out that the overwhelming majority of all possible numbers share this exact same kind of endless, non-repeating, unsolvable by simple equation behavior, with the simple, tidy fractions most people use in everyday life actually being the rare exception rather than the ordinary rule. Is there a largest prime number? A prime number is any whole number greater than 1 that can only be evenly divided by itself and by the number 1, with no other whole number fitting evenly into it at all. Primes matter enormously in mathematics, because every single whole number greater than 1 can be built by multiplying some specific combination of primes together, making primes function almost like the basic building blocks from which every other whole number is constructed. The question of whether primes eventually run out at some largest possible value was settled with complete certainty well over 2,000 years ago through a wonderfully elegant argument. It begins by imagining, purely for the sake of argument, that someone had managed to write down a complete and final list containing every single prime number that will ever exist. The argument then shows that multiplying every prime on that supposedly complete list together and adding just one more produces a brand new number that cannot possibly share any prime factor with anything already on the list, meaning this new number must either be a prime itself that was somehow left off the list, or it must be built from some other prime that was also left off, either way directly contradicting the original assumption that the list had ever been complete in the first place. This proves, with total and permanent certainty, that no finite complete list of primes could ever exist, even though mathematicians have known for over 2,000 years that primes never run out. Dedicated computing projects still actively search for specific, individually record-breaking prime numbers, generally focusing on a particular special category of prime built using a simple repeated doubling pattern, since a specially efficient mathematical test exists just for numbers of this particular shape, making it practical to test unusually enormous candidate numbers for primality using currently available computers in a way that would be far less practical for testing an arbitrary large number not built in this same special way. Beyond simply chasing record-breaking individual primes for their own sake, primes carry an enormously important practical role in everyday life today, since the security protecting most secure digital communication and financial transactions online depends directly on how extraordinarily difficult it is to take one giant number, built by secretly multiplying two large primes together, and figure out backward which two primes were originally multiplied to produce it, providing a genuinely direct and consequential real-world link between one of the oldest branches of pure mathematics and the security protecting modern digital life. What is the Riemann hypothesis? Among every unsolved problem in mathematics today, one particular puzzle is widely considered the single most significant of all, concerning the precise, detailed pattern behind how prime numbers are scattered among all the other whole numbers, and it remains, to this day, the one major unsolved problem, out of a famous handful once singled out for special attention, with a substantial prize offered for its solution that nobody has yet managed to solve. This puzzle concerns a particular mathematical function, whose input and output values can both be built from combinations of ordinary numbers together with an unusual imaginary quantity, discussed in an earlier topic. This function has certain very specific input values where its output happens to come out to exactly 0, and setting aside a small handful of simple, already well-understood cases, the puzzle claims that every single one of these countless remaining special 0 points, when carefully plotted out, should fall along one single, precisely defined straight line, without a single exception found anywhere among the infinitely many of them. This might initially sound like a narrow technical detail confined to one obscure function, but it carries enormous significance, since the exact pattern of these special 0 points turns out to be closely tied to the underlying pattern behind how prime numbers themselves are distributed. A full proof would sharpen mathematicians' current best understanding of exactly how primes are scattered throughout the number line, including the unavoidable margin of error in common ways of estimating how many primes exist below a given threshold. Extensive computer checking has confirmed this puzzle holds for an enormous number of these special 0 points, with no exception ever found. But mathematicians stress that computer verification, however extensive, can never substitute for a fully general logical proof. Since mathematical history includes real cases of patterns holding perfectly for an enormous number of small tested cases, only for a genuine exception to turn up much further along than anyone had thought to check. Countless mathematicians, including some of the most accomplished in the whole history of the field, have tried to fully prove this puzzle over the century and a half since it was first proposed, without success so far, and a substantial and growing body of other mathematical results has already been proven specifically conditional on this puzzle eventually turning out to be true, meaning an enormous amount of additional mathematical knowledge is currently resting on and would be immediately confirmed by a future successful proof, making it arguably the single most consequential open question in the whole of mathematics today. Can mathematics explain consciousness? Several serious modern efforts attempt to describe conscious experience, the subject of much of an earlier part of this series, using precise mathematical formulas rather than purely descriptive language. A genuinely bold departure from how philosophers have traditionally approached the mind, and this raises a genuinely interesting question. Can mathematics ever fully capture something as inherently subjective as felt, first-person experience? One of the most fully developed of these attempts proposes a specific mathematical quantity, meant to measure how thoroughly a physical system's individual parts are woven together into one single, unified whole. Calculated by carefully analyzing the full web of cause and effect relationships running between that system's own components, with the theory proposing that a system's calculated score under this formula corresponds directly to how much genuine, conscious experience it carries. This particular approach has faced sharp criticism from several computer scientists and philosophers, who argue that its own formula, taken literally, would assign a surprisingly high consciousness score to certain simple error-correcting systems and basic grid-shaped circuits. Systems hardly anyone would otherwise consider conscious at all, raising a broader worry about whether any current formula can really be trusted to track genuine experience rather than some different quantity that merely resembles it on paper. A separate and controversial proposal suggests consciousness arises from strange, tiny-scale physical effects occurring inside structural components found within individual brain cells, partly built on the argument that genuine human insight cannot be fully explained through ordinary step-by-step computation alone. This has drawn pushback from most brain researchers and physicists, who argue the brain's warm, constantly jostled, wet environment seems extremely unlikely to sustain such delicate tiny-scale effects long enough to matter. Given these serious ongoing technical and philosophical challenges facing every current mathematical approach to consciousness proposed so far, whether mathematics can ever, even in principle, fully capture subjective experience remains genuinely unsettled, with some researchers hopeful that a sufficiently refined future formula could eventually succeed, and others arguing that first-person experience may belong to a fundamentally different category. No purely mathematical outside-looking-in description could ever fully capture. Is reality a mathematical structure? One especially bold idea proposes that physical reality isn't merely well described by mathematics, as is generally and uncontroversially accepted throughout science, but is, at the very deepest level, actually identical to a mathematical structure, with no additional physical substance or stuff required on top of the mathematics itself for physical reality to genuinely exist. The reasoning behind this idea starts from the fairly modest and widely shared assumption that some kind of external reality genuinely exists, entirely independent of human minds. It then argues that any complete description of a reality that's truly independent of human minds in this way must, by its very nature, be entirely free of anything specifically tied to human language, culture, or particular perspective, since a description still tangled up in specifically human concepts wouldn't really count as fully independent after all. Mathematical structures are argued to be uniquely well-suited for this job, since they're defined purely through their own internal relationships and formal properties, without depending on any particular human language or culture to describe them. Under this idea, the long-standing puzzle discussed in an earlier topic of why mathematics describes physical reality so remarkably well simply dissolves away entirely, since physical reality, under this view, doesn't merely resemble a mathematical structure. It simply is one, meaning there's no leftover mystery requiring further explanation, since a mathematical structure will always, by definition, be most naturally and completely described using mathematics. This idea leads directly to an even bigger further claim, connecting to the multiverse discussion from an earlier part of this series, suggesting that every mathematically self-consistent structure that could possibly exist must, in some equally real sense, actually exist as its own separate reality, since there's no obvious principled way to single out just one particular structure, namely our own universes, as uniquely real while excluding every other logically consistent structure from existing in that very same sense. This bold idea faces serious pushback. One challenge asks how to draw a clear, non-arbitrary line around exactly which mathematical structures should properly count as sufficiently real under this framework, given how wildly mathematical structures vary in their own complexity and coherence. A second challenge asks whether the specifically felt qualities of conscious experience discussed in the previous topic could ever be fully derived from a structure's own abstract relationships alone, without needing some additional ingredient beyond pure mathematics. Despite these unresolved challenges, this idea remains seriously discussed today, illustrating just how far some of the most careful thinking about reality's deepest nature has been willing to travel. Why are fractals everywhere? A fractal is a pattern that keeps looking similar to itself no matter how closely you zoom in on it, with a small piece of the overall shape closely resembling the whole larger shape, often repeating this same self-similar structure across many different levels of magnification at once. A property first properly and fully formalized by a mathematician studying, among other things, exactly how a coastline's measured length keeps growing the more closely and finally you measure it. Since a coastline keeps revealing smaller inlets and jagged little details at every finer scale you look, without ever fully settling into one final, fixed length. Fractal-like patterns of this kind show up remarkably often throughout the natural world, appearing in the branching shape of trees and river networks, the branching structure of blood vessels and the airways inside lungs, the repeating bumps of certain unusual vegetables, and even the overall large-scale scattering of galaxies throughout the universe. This striking pattern showing up again and again across so many entirely unrelated systems is generally explained by the fact that this kind of repeatedly branching, self-similar growth represents a remarkably simple and efficient solution to a shared underlying problem many different natural systems each independently face, namely how to distribute something limited, like sunlight, nutrients, or oxygen, as thoroughly as possible throughout a confined space, using the least possible amount of material and effort. Careful study of the branching structure inside the human circulatory and respiratory systems has shown that this same kind of branching pattern can be mathematically shown to represent something close to a genuinely optimal solution for efficiently delivering a limited resource, like oxygen-carrying blood or breathed air, to an enormous number of individual cells spread throughout the body, using the smallest possible amount of biological material and energy to build and maintain the entire branching network, offering a clear, well-supported reason why this same kind of branching structure has evolved independently over and over across so many separate and only distantly related forms of life throughout history. Beyond these naturally evolved examples, mathematicians have separately developed an entirely different class of purely abstract fractal patterns, generated by repeatedly applying a fairly simple mathematical rule over and over again, producing endlessly rich and detailed self-similar patterns that never fully settle into any final, complete shape, no matter how far you zoom in, illustrating that fractal geometry represents both a widespread and genuinely useful natural structural pattern, repeatedly and independently arising across many separate living systems for clear underlying physical reasons, and entirely separately, a rich and still actively studied area of pure abstract mathematics all on its own. Could the universe be a simulation? The simulation hypothesis suggests that our entire observed universe, including every conscious being within it, might actually be an extremely detailed computer simulation, run by some far more technologically advanced civilization, rather than representing an original, non-simulated base reality, an idea given a careful, rigorous, and probability-based formulation by one philosopher in an influential essay directly asking whether we might be living inside a computer simulation right now. That philosopher's argument doesn't directly claim we definitely are living in a simulation, but lays out three possible statements, arguing at least one must be true. Either almost every civilization at roughly our current level goes extinct before developing the technology to run detailed simulations of their own history, or civilizations that do reach that level simply choose not to run many such simulations. Or, if neither is true, the overwhelming majority of all minds having an experience like ours must actually be simulated rather than original. Since a single advanced civilization could plausibly run enormous numbers of separate simulations at once, each containing enormous further numbers of simulated minds, some physicists doubt whether any physically possible computer could ever have enough raw power to simulate an entire universe down to the full level of tiny-scale detail ours displays, since simulating even a small region this thoroughly seems to require resources that grow explosively as the simulated region gets larger. Supporters respond that an advanced civilization might not need that level of detail everywhere at once, but could apply a shortcut, rendering full detail only where someone happens to be looking closely enough to notice, though this remains entirely speculative. A small number of physicists have proposed possible ways to actually test this idea, suggesting that if our universe really were built on some kind of underlying grid-like computational structure, that hidden structure might leave a faint, detectable trace in extremely high-energy particles arriving from deep space. No such trace has ever been found, though even a confirmed detection would only rule out one specific, particular version of the idea, rather than the whole broader hypothesis. The simulation hypothesis remains entirely unconfirmed today, without any direct evidence supporting it either way, and it's worth noting that even if it somehow turned out to be true, it wouldn't necessarily change anything about how our own everyday experience actually feels from the inside, since a sufficiently detailed simulation would, by its very design, be completely indistinguishable from a genuinely real, non-simulated existence to anyone experiencing it from within. Part 13. Technology and the Future. Will artificial intelligence become conscious? Modern artificial intelligence systems, especially the ones trained on enormous amounts of text, can now produce remarkably fluent, thoughtful-sounding responses to almost any question, which has stirred up a genuinely serious debate about whether these systems might possess, or could one day come to possess, real inner experience, rather than simply producing behavior that looks convincingly thoughtful from the outside without anything actually being felt on the inside. These systems work by learning statistical patterns from an enormous pile of text, essentially predicting which word is most likely to come next given everything that came before it. A fundamentally different underlying setup from how a living brain actually develops and works, even though both do rely on the same broad principle of information flowing through a huge, densely connected network of simple processing units. Most researchers currently working directly with these systems believe none of them have any genuine inner experience, though the exact reasoning behind that belief varies. Some point to how these systems lack any persistent, continuously updated memory of their own, and lack any genuinely embodied physical sense of the world the way a living creature does. Others point to specific theories of consciousness, discussed in an earlier part of this series, arguing that current AI designs simply don't have the particular kind of richly interconnected internal structure those theories consider necessary for genuine experience to arise at all. A major complicating factor is that consciousness itself still has no single, universally agreed upon scientific definition or reliable outside test capable of confirming whether it's present in any given system. meaning that even if a future AI system convincingly claimed to have real inner experience, researchers currently have no agreed-upon way to actually verify whether that claim is true, false, or perhaps not even a properly answerable question at all. Some philosophers argue there's no clear, principled reason why genuine experience couldn't eventually arise inside a sufficiently complex non-biological system, provided its underlying structure resembled whatever current theories consider relevant, while others argue that real experience may specifically require particular biological properties that no purely computational system, however behaviorally impressive, could ever truly replicate. Given both consciousness's unresolved definition and the real structural differences still separating today's AI systems from living brains, whether artificial intelligence could ever become genuinely conscious rather than merely appearing to be from the outside remains a wide-open and actively debated question. Can computers think? One of the earliest serious attempts to tackle whether a computer can genuinely think proposed sidestepping the difficult philosophical question of what thinking truly is in favor of a simpler, more practical test. If a human judge, talking through text with both a hidden computer and a hidden real person, can't reliably tell which one is the machine, then the machine should reasonably be credited with genuinely thinking, or at least with behaving in a way indistinguishable from real human thought. This test faced a famous and influential challenge built around a thought experiment, imagining someone locked inside a sealed room, handed an extremely detailed instruction manual written in their own language, telling them exactly how to respond to any incoming set of foreign symbols slipped under the door, without that manual ever requiring the person to actually understand what any of those symbols truly meant. This imagined person could, in principle, produce flawless, perfectly fluent-seeming responses well enough to fool anyone outside the room, despite genuinely understanding absolutely nothing about the language being used, which was meant to show that passing this kind of test doesn't prove real understanding is happening at all. Only that clever symbol shuffling according to fixed rules can convincingly imitate it. This thought experiment faced its own sharp pushback. One response argues that while the person alone doesn't understand the foreign language, the entire system, the person together with the manual and materials, considered as one whole, might reasonably be said to understand the language even if no single piece of it does alone. The original thinker pushed back by imagining the person simply memorizing the entire manual, effectively becoming the whole system, while still insisting they wouldn't gain any genuine understanding as a result. Today's advanced text-generating systems have dragged this decades-old argument back into sharp relevance, since these systems produce startlingly fluent, seemingly thoughtful text through what is, underneath, a large-scale statistical pattern-matching process rather than anything built to replicate genuine reasoning. Some researchers argue this makes these systems a real-world version of that same locked room, while others argue sufficiently large, complex pattern-matching systems might actually develop something functionally equivalent to genuine understanding, purely as a byproduct of their own scale. Whether computers can genuinely think in any sense truly comparable to human thought remains unresolved more than 7 decades after that first proposed test, with the exact same underlying disagreement whether passing a convincing behavioral test proves real understanding is happening underneath, still every bit as unsettled today as it was originally. Will humans merge with machines? Devices capable of directly reading, and in some cases even gently influencing, activity happening inside the brain, have progressed remarkably from early, rough research demonstrations into genuinely significant real-world medical tools over the past couple of decades, raising increasingly serious and grounded questions about just how far this kind of direct brain-machine connection might eventually go. One company recently succeeded in implanting this kind of device into a person living with paralysis, letting that person control a computer cursor directly using brain signals alone without needing to move at all, a genuinely meaningful milestone, though it builds directly on a much longer research foundation that had already years earlier allowed paralyzed patients to control robotic arms and computer interfaces using implanted sensors. Nearly every version of this technology currently in real medical use remains sharply focused on restoring lost ability to people with serious disability, letting a paralyzed person move or communicate again, rather than being anywhere near capable of genuinely boosting or enhancing the abilities of an otherwise healthy person beyond their own ordinary baseline. Since even the most advanced current sensors can only reliably pick up a small slice of the brain's total activity at any given time, placing a real practical ceiling on how much information can currently pass back and forth between a brain and a connected machine. Beyond these direct brain-reading devices specifically, a much older and broader category of human-machine partnership already exists and keeps expanding in ordinary medicine, including devices that have restored real, working hearing to a great many people with severe hearing loss by converting outside sound directly into signals capable of stimulating the relevant nerve, bypassing whatever part of the ear no longer works properly, and newer, more experimental devices aiming to partially restore some functional vision to certain kinds of blindness by directly stimulating either the remaining working parts of the eye or the vision processing part of the brain itself. Predictions about how far genuine brain-machine merging might eventually go, moving well beyond simply restoring lost function toward truly enhancing a healthy person's own abilities, vary considerably among people actually working in this field. Some voices in the industry remain publicly optimistic that far more capable connections are only a few decades away, while many neuroscientists and engineers working directly on the underlying technology urge considerably more caution, given the real remaining challenges around safely reading much more brain activity at once and keeping any implanted device safe over a person's entire lifetime. Can memories be uploaded? The popular idea of directly uploading a person's complete memories or their entire mind into a computer in a way that would genuinely preserve and continue that same person's specific thoughts and experience within a non-biological system remains, based on everything currently known about the brain and computing, considerably more speculative than the more incremental brain-machine devices discussed in the previous topic, given the very real remaining hurdles still standing in the way. As discussed in earlier parts of this series regarding memory, individual memories appear to be stored through specific patterns of connection strength spread across enormous numbers of interconnected brain cells, rather than sitting in any single, easily identifiable spot the way a file sits in an ordinary computer. Fully mapping out every single one of these connections across an entire living human brain would require an extraordinarily detailed brain mapping technology that simply doesn't exist yet at anywhere near the needed scale for a full human brain, though smaller-scale versions of this same mapping effort have already succeeded for much simpler creatures, including a tiny worm and, more recently, an entire fruit fly brain. Beyond the sheer technical challenge of ever fully reading out this level of detail from a living human brain, a further and deeply difficult question remains. Even if that same detailed structure were perfectly copied onto some entirely different non-biological system, would that copy genuinely continue the original person's own specific experience? Or would it instead simply create a brand new, separate conscious being that merely happens to share the very same memories and personality, without that new being actually being a real continuation of the original person at all? This question connects directly to a long-running set of puzzles in philosophy concerning what it truly means for a person to remain the same individual over time. Some researchers have proposed a slower, gradual approach instead, imagining individual brain cells being replaced one at a time over an extended period, with artificial equivalents built to behave exactly like the originals, with supporters arguing this gradual method might preserve a real, continuous thread of identity throughout the whole process, in a way that one sudden, instant copy might not, though this remains entirely theoretical, and the deeper philosophical question of whether it would truly preserve identity, even if it somehow became possible, remains just as unresolved either way. Given both the massive remaining technical gap in mapping a full living brain and the deeper unresolved philosophical question of what a copy would actually mean for the original person, mind uploading remains a subject of serious speculation and genuine philosophical interest, but not something that exists today or that mainstream researchers expect anytime soon. Could we live forever digitally? The idea of achieving some genuine form of lasting digital immortality, building directly on the idea of mind uploading discussed in the previous topic, raises its own separate set of tricky questions beyond simply managing the initial technical feat of copying a mind into a machine in the first place, especially concerning what it would actually take to keep that same digital mind running properly across an indefinitely long stretch of time. Any digital mind, no matter how it's built, would need some kind of continuously running, carefully maintained physical hardware and an uninterrupted supply of power in order to keep operating at all, meaning true digital immortality would additionally require some long-term, reliable system for maintaining, repairing, and eventually moving that same digital mind onto newer hardware across many centuries or longer, as whatever hardware it originally ran on inevitably ages and eventually fails completely. A genuinely different and more open-ended kind of ongoing upkeep challenge than anything an ordinary human lifetime, however long, ever actually requires. A separate and genuinely tricky question asks whether a digital mind that's been moved across many completely different pieces of hardware over a very long stretch of time, and perhaps had bits of its own underlying structure gradually adjusted and updated along the way, would still genuinely count as the very same original person the whole way through, or whether it might instead gradually turn, through the build-up of many small individual changes, into something different enough that calling it still the same person would no longer really hold up. Some people who think seriously about this question argue that this kind of gradual change should really be thought of as no different from the completely ordinary way a living human body already continuously replaces its own individual cells and molecules throughout an entire lifetime, without that ordinary process ever being thought to threaten someone's basic sense of remaining the same person the whole way through. Others push back, arguing that ordinary cellular replacement happens within a continuously stable and never fully interrupted underlying system, whereas jumping between totally different kinds of hardware might represent a much more fundamental kind of interruption, one not obviously comparable to gradual biological turnover at all. Beyond these deep philosophical questions, digital immortality would also raise a long list of entirely practical, social, and legal questions that no current system is remotely built to handle, including how a society might need to adapt its own laws and institutions to accommodate people whose existence could, in principle, continue indefinitely, considerably longer than any legal or social system has ever had to operate continuously across. Can nanobots repair the human body? The general idea of tiny medical machines built at a scale far smaller than anything visible to the naked eye, specifically designed to travel through the human body and diagnose or repair damage at the level of individual cells, was first seriously and thoroughly proposed decades ago in a detailed engineering book exploring the broader idea of building precise, functional structures at the scale of individual atoms and molecules. What actually exists in real medicine today falls considerably short of that original, more ambitious vision of fully independent tiny robots freely diagnosing and repairing problems on their own, but real medicine has still achieved genuinely important successes using much simpler small-scale engineering. Tiny fatty bubbles, for instance, were used as the essential delivery method for a major class of vaccine, safely carrying fragile genetic material directly into human cells, even though these bubbles aren't independently acting robots in any mechanical sense, but simple passive delivery containers. More advanced experimental delivery systems, some built with surface markers designed to selectively latch onto target cells such as cancer cells, letting treatment concentrate precisely where needed while sparing surrounding healthy tissue, have already made it into regular medical use, representing real progress toward that ambitious vision, even though these systems still mostly rely on passive chemistry rather than any independent, self-directed navigation. More sophisticated experimental devices with at least some limited specific ability to move or act on their own have already been successfully demonstrated in research labs, including tiny structures built directly from genetic material, carefully folded into specific working shapes capable of simple, useful actions such as staying closed until they detect one very specific target signal, then opening precisely at that moment to release a treatment exactly where it's needed. Achieving the fuller original vision of truly independent medical machines, freely patrolling the bloodstream, diagnosing a wide range of problems on their own, and carrying out sophisticated repairs entirely without outside guidance, remains considerably beyond what's currently possible, with real remaining challenges including how to reliably power such tiny devices for a useful length of time, how to give them genuinely reliable independent navigation and judgment at such a small scale, and how to keep the body's own immune system from rejecting them, meaning today's real nanomedicine, while genuinely significant, remains far more modest than the popular picture of fully independent nanobots roaming freely and repairing the body on their own. Will we ever build warp drives? A warp drive, as commonly imagined, would let a spacecraft effectively travel faster than light by reshaping the space around the ship itself, rather than by the ship directly breaking light's own local speed limit, a distinction that fits neatly within the accepted rules of gravity, which strictly forbid any object from locally outracing light through its own immediate surroundings, while still allowing space itself to stretch, shrink, or shift shape at rates not bound by that same limit. One physicist proposed the first serious, mathematically valid version of this idea, describing a way of reshaping space so it contracts directly ahead of a ship and expands directly behind it, creating a traveling bubble that would carry the ship along at an effective faster-than-light speed relative to a distant observer, without the ship itself ever locally breaking light's speed limit within its own small bubble of ordinary space. Despite fitting the math cleanly, this proposed drive runs into extremely serious practical obstacles. It requires large amounts of an unusual kind of matter that pushes space apart rather than pulling it together. The same material discussed in an earlier topic regarding negative mass, and the tiny scale rules of physics place a strict limit on how much of it can exist and for how long, making it genuinely unclear whether nearly enough could ever be gathered or sustained. Later, more careful calculations found that the amount of this unusual material the original proposal would actually require vastly exceeds the entire mass and energy contained within the whole observable universe, an extremely severe requirement. More recent refined proposals have managed to calculate significantly reduced energy requirements using cleverer geometric shapes, though even these still call for energy quantities far beyond anything any realistic future power source could plausibly supply. A further serious concern involves whether any real physical process could safely start, precisely steer, and eventually stop a bubble like this once it was already moving, since detailed theoretical work has suggested that ordinary particles and radiation encountered along the way could get trapped and dangerously concentrated right at the bubble's leading edge, posing a serious safety risk the moment the bubble's motion was ever brought to a halt. Given both the extreme unresolved energy requirement and these further serious safety concerns, warp drives remain a mathematically valid but entirely theoretical consequence of gravity's own equations, with most physicists working in this area believing genuinely new breakthroughs, especially concerning this unusual matter's true nature, would be needed before a real working warp drive could ever become a serious engineering possibility. Can we terraform Mars? Transforming Mars on a large scale into a genuinely Earth-like, directly habitable world, one where people could walk around without a pressurized suit, would require overcoming a handful of deep, connected planetary-scale challenges, the biggest of which involves Mars's remarkably thin surrounding air, far thinner than Earth's own, and made mostly of a heavy, heat-trapping gas. One widely discussed proposed approach involves deliberately releasing the same heat-trapping gas currently frozen solid within Mars's polar ice caps and locked away in various pockets underground, in order to thicken the surrounding air and strengthen its natural warming effect, directly heating the planet's surface and, in principle, becoming somewhat self-reinforcing as the resulting warmth triggers even more frozen gas to release from remaining hidden pockets. A detailed and influential study directly analyzing spacecraft data gathered while orbiting Mars concluded that the total amount of this gas realistically available anywhere on the planet, even if every last bit of it could somehow be fully released into the air, would only thicken Mars's atmosphere to a small fraction of Earth's own, an amount the study's own researchers concluded would fall well short of what's needed to keep liquid water stable on the surface or make Mars genuinely livable without a pressurized suit, a finding that has considerably dampened earlier optimism about this particular proposed approach. Beyond this basic shortage of available gas, Mars also lacks anything like Earth's own protective magnetic shield, discussed in an earlier part of this series, having lost its own version of that shield very early in its history, once its smaller core cooled and solidified considerably faster than Earth's larger core has. Without that shield, any newly thickened atmosphere would remain directly exposed to the Sun's constant outward stream of energetic particles, the very same process already confirmed to have stripped away most of Mars's original, thicker early atmosphere over billions of years, meaning a newly created atmosphere would likely need constant, ongoing replenishment to keep up against this same slow but steady erosion, unless some further and currently speculative solution, such as an artificial planet-wide magnetic shield, were also somehow built and deployed. Given both this shortage of available gas and the lack of any natural protective shield, most planetary scientists working in this area now consider fully terraforming Mars to be considerably more difficult using any currently known technology than earlier. More optimistic discussions once assumed, though more modest partial changes to the environment, along with simply building fully enclosed, pressurized living habitats rather than reshaping the whole planet's open surface and air, remain a far more realistic near-term path toward a lasting human presence there. Could time travel ever exist? The accepted rules of gravity allow certain unusual situations that would let someone travel into the future, relative to a distant observer, a genuine effect already confirmed through real-world measurement, including the fact that clocks aboard orbiting satellites tick at a very slightly different pace than identical clocks on the ground. And, more strikingly, through astronauts who have spent long stretches in orbit, who have, as a measured consequence, technically traveled a tiny sliver of time into their own personal future compared to everyone who stayed behind on Earth. Forward time travel on a much more dramatic scale remains fully allowed under these same rules, requiring either travel at a speed extremely close to light's own, or spending an extended stretch deep within an unusually strong gravitational pull, both of which reliably slow the passage of time for the traveler relative to someone watching from farther away, though achieving either condition to any dramatic degree would require propulsion or gravitational proximity far beyond anything currently achievable. Backward time travel, by contrast, runs into far more serious theoretical trouble. While certain unusual mathematical solutions to gravity's own equations do technically allow for looping paths through time that could let someone return to their own earlier moment, these solutions generally require exotic conditions that either don't appear to exist in our real, observed universe, or would require substantial amounts of that same theoretical negative energy matter discussed in earlier topics regarding wormholes and warp drives. One physicist proposed a chronology protection idea, suggesting the fundamental laws of physics likely act to actively prevent this kind of backward time travel loop from forming on any large, meaningful scale, specifically to preserve the basic rule that a cause must come before its effect and to avoid the severe paradoxes unrestricted backward. Time travel would otherwise create, such as a traveler acting to prevent their own birth, a scenario leading directly to a flat contradiction if truly unrestricted time travel were possible. While this particular idea hasn't been formally proven as an absolute general rule covering every conceivable case, it remains reasonably well supported by the consistent pattern that every specific proposed mechanism for backward time travel examined so far has required some exotic ingredient that either doesn't seem to exist or appears impossible to produce in the needed amount, leading most physicists to consider genuine backward time travel extremely unlikely, even while forward time travel, understood more modestly, is already a confirmed and measured physical reality. Will humanity colonize the galaxy? Serious thinking about humanity's long-term prospects for eventually spreading out into the wider galaxy has to start by confronting the sheer, almost incomprehensible scale of distance involved. Since even our very nearest neighboring star system sits so far away that reaching it with the fastest spacecraft propulsion technology ever actually built and tested would take many thousands of years. Meaning any realistic future effort to spread beyond our own solar system would first require developing dramatically faster propulsion than anything demonstrated so far. Several propulsion ideas well beyond ordinary chemical rockets have been seriously studied as ways to meaningfully shrink these enormous travel times, including one concept genuinely studied as a real engineering project decades ago, generating thrust through a rapid sequence of small, controlled nuclear explosions set off just behind the ship, and separately, proposed engines tapping the enormous energy released when matter meets its exact opposite counterpart, though producing and storing that opposite matter in any meaningful quantity remains far too limited and costly today for real spacecraft use. Beyond propulsion, any realistic, multi-generational journey to another star would also need to sustain a fully self-contained, stable living environment for centuries or longer, endlessly recycling air, water, and food, while maintaining real social and psychological stability across many successive generations born, living, and dying entirely aboard the ship, never once setting foot on any planet's surface. A very different and considerably more modest proposed approach skips large-scale direct human travel altogether, instead imagining small, self-replicating robotic probes sent to a nearby star system, which would then use whatever raw material is locally available there to build fresh copies of themselves, which would in turn continue onward to further star systems to repeat the same process indefinitely. Calculations suggest a coordinated fleet of probes working this way could, in principle, visit every single star system in the entire galaxy within a stretch of time that, while genuinely enormous by any ordinary human measure, is still remarkably short compared to the galaxy's own overall age. Given how far current propulsion, life support, and robotic technology still sit from what any of these approaches would actually require, most researchers who have seriously studied this question generally conclude that meaningful galaxy-wide colonization, in whatever specific form it might eventually take, likely remains many centuries away at the very least, representing one of the most distant and ambitious possible outcomes for humanity's long-term future. Part 14. Unsolved Signals and Phenomena, the WOW signal. A researcher combing through printouts from a radio telescope scanning the sky one summer night noticed something jump off the page, an unusually strong, narrow burst of radio energy, lasting less than a minute, far stronger than the ordinary background noise around it. He was so startled by it that he circled the reading on the printout and scrawled a single excited word in the margin beside it, giving the signal its lasting nickname ever since. What made the signal especially interesting was the specific radio frequency it arrived on, sitting extremely close to a frequency naturally given off by plain hydrogen gas, the most common material in the entire universe. Scientists had long suspected this particular frequency would make a logical, almost obvious meeting point for any civilization deliberately trying to signal across the stars, since any sufficiently advanced civilization studying basic physics would likely recognize this same frequency as an easy, universal choice. Despite how strong and how promising it looked, the signal has never once been detected again, despite repeated follow-up searches over the following decades, using the same telescope and various others, pointed at the very same patch of sky. The original telescope's particular design also meant the exact source could only be narrowed down to one of two possible small regions of sky, rather than one single precise spot, making any future search even trickier. A few ordinary, down-to-earth explanations have been proposed over the years. One suggested the signal might have come from a passing comet's own cloud of gas, though this idea faced serious pushback from other researchers, including members of the original team, who pointed out that comets aren't known to produce this kind of narrow, focused radio burst. and that the specific comet suggested wouldn't have actually been positioned correctly to match what was recorded. Another suggestion pointed to a stray signal bouncing off a passing satellite, though the burst's specific characteristics don't fit that explanation especially well either. With no repeat detection and no fully satisfying ordinary explanation, the signal remains formally listed as unexplained, neither confirmed as a deliberate message from elsewhere nor definitively traced to any known natural cause, a status that has now lasted for decades, making it one of the most long-discussed unresolved signals in the entire history of the search for other civilizations out among the stars. Tabby's star. An ordinary-looking distant star drew sudden, intense scientific attention once volunteers combing through data from a planet-hunting space telescope noticed something strange. Its brightness kept dipping in large, oddly irregular ways, unlike anything a normal orbiting planet would ever produce. The pattern was unusual in more than one way. Some individual dimming events blocked out a huge share of the star's total light, far more than even a planet much larger than Jupiter could ever block on its own, and the dips didn't repeat on any steady, predictable rhythm the way an orbiting planet's shadow reliably would. The astronomer who led the formal study of the star considered several natural explanations, including the possibility of a broken-up swarm of comet fragments drifting past. Around the same time, a separate astronomer publicly proposed as one serious idea worth actually investigating rather than a confirmed conclusion, that the pattern was also consistent with what you might expect from an enormous, partly built artificial structure, the kind an extremely advanced civilization might construct to capture more of its own star's energy. This idea prompted a dedicated radio search specifically listening for any accompanying signal that might hint at real technology at work, and that search came back completely empty. The strongest current explanation came from a later, more detailed study that measured exactly how the star's light dimmed across different colors at once, finding that the dimming was noticeably stronger in bluer light than in redder light. A solid, opaque object, whether a planet or an artificial structure, would be expected to block every color equally. But a fine cloud of drifting dust naturally scatters blue light more strongly than red, matching the observed pattern far better and pointing toward a natural explanation involving orbiting dust rather than anything solid or artificial. Even with this stronger, more natural explanation now favored, exactly where this dust came from and why it settled into such an unusual and irregular pattern in the first place still isn't fully worked out, leaving the star's full story only partly resolved even today. Oumuamua. A telescope scanning the sky one night picked up a small, fast-moving object, cutting through our solar system on a path that made clear it wasn't gravitationally bound to our sun at all, meaning it had arrived from somewhere else entirely, drifting in from beyond our solar system and destined to leave again just as quickly, marking the first confirmed visitor of its kind ever directly observed. Researchers only had a short window to study it before it grew too faint and distant to observe any further. But in that brief time, its changing brightness as it tumbled through space hinted at a strikingly elongated, unusual shape, considerably more stretched out than any ordinary comet or asteroid ever seen before. Though the exact details of just how extreme that shape truly was have faced some further debate and reanalysis since. The most puzzling detail involved its path through space, which showed a small but very real extra nudge of speed beyond what the sun's gravity alone could explain. Comets often show a similar small nudge, caused by frozen material inside them slowly turning to gas as they warm near the sun, acting like a tiny natural rocket thruster. But that kind of gassing off is normally accompanied by a visible cloud and tail trailing behind, and despite careful searching, no such visible cloud or tail was ever spotted around this particular object, creating a real tension between its measured path and its plain visible appearance. A leading natural explanation suggests it may have been quietly releasing an unusually large amount of a particular gas that's much harder to spot with ordinary observation methods than the more easily seen material typical comets release, consistent with the object having originally broken off from a distant icy world rich in frozen gases of exactly this kind. One astrophysicist notably proposed a far more speculative alternative, suggesting the object's odd shape and unexplained nudge in speed without any visible gas cloud might be explained by it being an artificial object, perhaps an extremely thin, lightweight sail built by some other civilization. This idea drew plenty of public attention, but hasn't been widely accepted among researchers, most of whom consider the natural gas explanations more likely, though the debate remains unsettled since the object is now long gone, far beyond the reach of any further direct study. Fast radio bursts. While an earlier part of this series covered the general mechanisms proposed to explain sudden, powerful flashes of radio energy arriving from deep space, several individual discoveries within this category stand out as their own particularly puzzling stories, showing just how much genuine mystery remains even as the broader category has become steadily better understood. The very first source ever confirmed to repeat, rather than flashing only once and going silent, turned out to follow an intriguing and only partly understood rhythm of its own, cycling through active stretches of frequent bursting, followed by quiet stretches with no activity at all. A pattern some researchers suspect might be tied to this source being part of a paired system with a companion object, with the rhythm reflecting their orbit around one another, though this remains unconfirmed. A separate puzzle involves where these bursts tend to come from. Some sources trace back to small distant galaxies busily forming new stars, the same general kind of environment linked to certain rare and unusually powerful stellar explosions. Other confirmed sources instead trace back to entirely different kinds of galaxies, older and calmer with far less active star formation, closely resembling our own galaxy. This split has led researchers to conclude that these bursts likely don't all share one single underlying cause, but instead arise from at least two, and quite possibly several, genuinely different kinds of sources, even as one particular kind of extremely magnetic collapsed star remains the strongest single suspect identified so far. A further notable puzzle involves a small number of bursts showing highly unusual internal structure, along with at least one especially striking detection traced back to an extraordinarily distant and ancient source, corresponding to a time when the universe itself was still remarkably young, raising interesting questions about how whatever mechanism produces these bursts could already have been fully in place that early in cosmic history. A dedicated telescope built specifically to catch these bursts in large numbers continues steadily growing the total catalog of confirmed detections, revealing a genuinely varied and only partly understood family of signals, with researchers still actively working to sort out exactly how many different underlying causes are truly responsible for the whole range of bursts observed so far. The Pioneer Anomaly. Two early spacecraft, launched decades ago on paths that carried them past the outer planets before continuing on toward the very edge of the solar system, were later found, through careful analysis of their tracked radio signals, to be slowing down very slightly more than the Sun's gravity and every other known influence could fully account for, a small but consistent and puzzling extra drag that came to be called the Pioneer Anomaly. The mismatch itself was tiny, but it showed up consistently across both spacecraft and held steady across more than a decade of careful tracking, making it a genuinely serious puzzle rather than simple noise or error, and it sparked real scientific excitement about whether it might point to some entirely new and previously unknown behavior of gravity itself operating way out at the far edges of the solar system. More down-to-earth explanations were also seriously considered from early on, including the idea that the spacecraft themselves might be unevenly radiating away their own leftover heat. Both spacecraft were powered by a steady source of heat produced from radioactive decay, and if that heat happened to radiate away from the spacecraft's structure slightly unevenly in one particular direction rather than perfectly symmetrically in every direction, the resulting gentle recoil, working exactly like the kick of a fired gun, could plausibly produce a small, steady push in one specific direction, fully explaining the observed slowdown without requiring any new physics at all. This heat-based explanation was eventually confirmed as correct through a later, more thorough study that combined much more complete historical engineering records with detailed modern heat modeling, precisely calculating the expected push created by the spacecraft's own particular design and finding that it closely matched the originally observed anomaly in both size and direction, providing a full and widely accepted explanation requiring nothing exotic or unknown whatsoever. This resolved anomaly is now frequently cited as a valuable lesson in how careful, patient scientific work should proceed, showing that an unexplained puzzle, however statistically solid and genuinely strange at first appears, doesn't automatically mean new physics is at play and can sometimes be fully explained through careful, ordinary engineering analysis once enough data and refined modeling finally become available to solve it properly. The flyby anomaly. Starting with one early spacecraft mission and later noticed in several others, engineers guiding spacecraft past Earth on their way toward more distant destinations using our planet's own gravity to gain a speed boost began noticing small, inconsistent mismatches between a spacecraft's carefully predicted speed after this kind of maneuver and its actual measured speed afterward. A puzzling pattern that came to be called the flyby anomaly. The same researcher who had earlier identified the Pioneer anomaly discussed in the previous topic, also led a detailed study of this separate puzzle, examining several spacecraft flybys of Earth conducted over roughly a 15-year span, and finding that a few, though notably not all, of these flybys showed a small but statistically real, unexplained shift in speed, an extremely tiny mismatch, but one considered meaningful, given how precisely spacecraft tracking and orbital calculations can normally be trusted. Unlike the earlier Pioneer anomaly, which showed up consistently and predictably, this particular anomaly proved considerably harder to pin down with any single unifying explanation, since some flybys showed the unexplained shift while other, seemingly quite similar flybys, conducted under broadly comparable conditions, showed nothing unusual at all, making it much harder to settle on one clear underlying cause the way the Pioneer anomaly eventually was. Researchers have proposed and carefully investigated several possible explanations over the years, including small overlooked errors in the standard corrections normally applied to spacecraft tracking, atmospheric effects not fully accounted for, and more exotic possible tweaks to the basic rules of gravity itself at these particular speeds and distances. Unlike the Pioneer anomaly, though, no single explanation proposed so far has managed to fully and consistently account for every individual case that's been recorded. More recent, more careful reanalysis of the original tracking data and equipment used at the time has suggested that at least some of the originally reported cases may trace back to overlooked, fairly mundane technical errors in how those early measurements were actually taken, rather than reflecting any genuinely new physical effect at all, though this explanation hasn't yet been confirmed as accounting for every single reported case. Given this more mixed and still not fully settled picture, the flyby anomaly remains a legitimately open topic of ongoing investigation, illustrating that not every spacecraft trajectory puzzle resolves as neatly as the earlier Pioneer anomaly eventually did. The Tunguska event. Early one summer morning, a massive explosion tore through a remote stretch of Siberian forest, flattening trees across an enormous area and releasing energy on a scale comparable to a large nuclear weapon, making it, by a wide margin, the most powerful impact-related explosion recorded anywhere in human history. Because the location was so remote, the first serious scientific expedition to investigate didn't arrive until nearly 2 decades later, led by a researcher who had specifically expected to find a large crater and recoverable chunks of space rock waiting for him at the site. Despite the sheer scale of destruction still clearly visible across the landscape, that expedition, and everyone that followed it, failed to turn up any confirmed crater or any confirmed fragments of the object responsible. The explanation now most widely accepted points to a relatively small space rock, or possibly an icy fragment, that entered the atmosphere at tremendous speed and exploded violently several miles above the ground rather than actually striking the surface directly. an event called an airburst. This would neatly explain both the enormous scale of tree destruction caused by the shockwave radiating outward and downward from high above, and the complete absence of any crater or recoverable fragments, since the object itself would have been largely vaporized and scattered as fine dust high in the atmosphere during the blast, rather than surviving intact all the way down to the ground. This general kind of atmospheric airburst explanation gained considerable further real-world support more recently, when a much smaller space rock exploded in a very similar kind of airburst over a Russian city, an event captured on countless dashcam and security cameras and studied in great detail immediately afterward, offering direct, modern, thoroughly documented proof that airbursts of exactly this kind really do happen, really can cause significant damage on the ground below, and really can occur without leaving behind any crater or easily recoverable debris, lending strong additional real-world credibility to the similar, though vastly more powerful explanation already proposed for the original historical event. Even with this explanation now broadly accepted, some genuine uncertainty remains about the exact size and makeup of the original object, given that no confirmed physical fragment from it has ever actually been recovered, keeping a small handful of more speculative alternative explanations alive in occasional discussion, even though the broader airburst explanation itself faces little serious doubt today. The Hessdalen Lights. For many decades, and especially during one particularly active stretch, people living in or visiting a quiet valley in Norway have reported seeing strange, unexplained, glowing lights hovering, drifting slowly, or occasionally moving quickly through the sky and near the ground, sometimes appearing frequently enough during especially active periods to draw serious, dedicated scientific attention. Researchers eventually set up permanent, automated monitoring equipment directly in the valley, including cameras, radar, and instruments capable of analyzing the exact colors of light given off by the phenomenon, specifically to gather more reliable, objective data than eyewitness accounts alone could ever provide. This same monitoring station, steadily upgraded over the years, has continued gathering data more or less continuously ever since, making this valley one of the most thoroughly and continuously monitored sites of unexplained lights found anywhere in the world. The leading scientific explanation points to the valley's unusual local geology, which places two very different types of mineral-rich rock unusually close together on either side of the valley. Researchers suspect this specific arrangement might create the conditions for a large, naturally occurring, slow-acting electrical effect, not unlike an enormous natural battery, with certain gases or charged dust particles released from the surrounding rock becoming charged and glowing as a result through a process broadly related to, though considerably more complex and less fully worked out than other naturally glowing electrical phenomena. Careful analysis of the light itself has, notably, detected the presence of a fairly rare metallic element in some recorded instances, a detail researchers suspect may be tied to the valley's own particular local mineral makeup, lending some further support to this geological explanation, even though the complete underlying mechanism capable of explaining every observed detail, including occasional rapid movement, hasn't been fully nailed down yet. While a few more speculative and far less scientifically supported explanations occasionally circulate in informal discussion, the dedicated ongoing scientific research effort has consistently focused on these natural geological and electrical explanations as the most plausible, treating the lights as a genuine, real, and repeatedly measured natural phenomenon whose complete underlying mechanism remains an active and ongoing area of study rather than something already fully solved and explained in exhaustive detail. The bloop sound. Underwater microphones maintained across a wide stretch of the Pacific Ocean, originally set up to monitor seismic and volcanic rumbling beneath the sea, once picked up an extremely powerful, distinctive, and completely unfamiliar low sound, detected simultaneously by multiple separate listening stations spread thousands of miles apart, quickly earning an informal nickname from the researchers who first noticed it. What made the sound so intriguing at the time was simply how powerful it was, measured as considerably louder than any known individual animal sound, including the loudest calls made by the largest whales on Earth, a genuine mismatch that fueled plenty of informal public speculation at the time about whether some enormous and entirely unknown sea creature, far larger than anything already confirmed to exist, might have been responsible. The research team that first identified and studied the sound eventually compared its exact acoustic pattern against various known categories of natural ocean sound, concluding that it closely and consistently matched the well-documented pattern produced by large-scale ice fracturing, the kind of sound produced when massive icebergs crack apart from a parent ice shelf, or when large icebergs further break apart as they drift into somewhat warmer water. This icy explanation was further supported by the sound's own carefully traced point of origin, pinpointed to a stretch of ocean near Antarctica known to contain a substantial concentration of large icebergs, a location entirely consistent with large-scale ice fracturing rather than any living creature or anything else. Researchers also noted that this same general kind of sound has, in fact, been picked up on numerous other separate occasions by the very same listening network, both before and after the original recording that first drew public attention, showing that sounds of this general type and cause are a fairly common and now well understood part of the ordinary background noise of the Southern Ocean. While the original mystery has therefore been considered fully and satisfactorily resolved as very likely representing a large natural ice-cracking event rather than any unknown creature, the story is still frequently retold in popular discussion as a memorable example of how an initially strange and powerful, unexplained sound can spark considerable public excitement and speculation, before patient, careful scientific investigation eventually settles on a more ordinary, though still genuinely interesting, natural explanation. The Green Children of Woolpit: Scientific Perspectives. According to two separate medieval chronicles, written not too long after the events they describe, two children, a young boy and a slightly older girl, both said to have distinctly green-tinted skin and clothing made from unfamiliar material, mysteriously appeared near a small English village, speaking a language nobody there could understand, and reportedly refusing to eat anything except raw beans until they gradually adjusted to ordinary local food over time. According to these same old accounts, the boy soon fell ill and died, while the girl survived, gradually lost her unusual green coloring as she adjusted to a normal diet, eventually learned the local language, and went on to live an otherwise ordinary life in the village, reportedly explaining, once she could finally communicate clearly, that she and her brother had come from a distant, dim, twilight land where everyone shared the same green skin, though this particular detail, filtered through medieval writers working somewhat removed from the actual events, is treated with real caution by modern historians studying the story. Historians generally treat this old legend as most likely reflecting a genuine real event that actually happened, since the story shows up consistently in two separate, independent written accounts, mixed together with the kind of embellishment and reinterpretation typical of medieval storytelling more broadly, rather than treating it as either a perfectly accurate historical record or a complete invention with nothing real behind it at all. From a medical standpoint, historians and some researchers have proposed that the reported green skin could plausibly be explained by a real, well-documented condition caused by severe iron deficiency, known historically for producing a distinctive pale, greenish tone in affected patients, especially in malnourished children, an explanation that would also help account for the poor health and the boy's early death, and for the girl's gradual return to a normal skin tone as her diet and health improved over time. The detail about their unfamiliar language and unfamiliarity with local food has led some historians to propose the children may have been immigrants from a nearby region on the European mainland, possibly orphaned survivors of a documented local conflict from around that same period, having become lost and disoriented in unfamiliar woodland while fleeing that violence, which would neatly explain both their unfamiliar language and their evident distress upon arrival. Given how little historical evidence survives, and how impossible any physical confirmation would now be, the story can't be definitively resolved but is generally treated as a real, if considerably embellished, historical event, rather than a literal account of children from a hidden or otherworldly place. Part 15. The Biggest Questions. Why is there something instead of nothing? An earlier part of this series explored this question through the lens of old philosophy and basic physics. A different and increasingly popular approach reframes the whole question around information itself, treating information, rather than matter or energy, as possibly the more fundamental underlying ingredient from which everything else in physical existence might ultimately arise. One physicist proposed this general reframing, suggesting that every physical thing, every particle, every field, and even space and time themselves might ultimately derive their existence from simple, discrete yes or no answers to specific physical questions, meaning information itself might be a more basic starting point than matter, energy, or geometry. A closely related and considerably more mathematically developed idea rests on a striking discovery showing that the maximum possible amount of information that can ever be packed into any bounded region of space depends only on that region's outer surface area, not on how much space it actually encloses inside, a genuinely counterintuitive result first worked out in the context of studying collapsed stars. This has grown into a broader idea suggesting that the complete description of any three-dimensional space could, in principle, always be fully captured on that same space's own flatter, lower dimensional boundary, hinting that the extra dimension we experience as depth might itself be a kind of construction, built from more basic information encoded elsewhere. If reality really is built from information in something like this sense, then the old question of why anything exists takes on a slightly different shape. Rather than asking why matter or energy exists at all, the more basic question becomes why any distinctions or information should exist at all, since a truly complete absence of any distinction whatsoever might represent a cleaner, more precise definition of true nothingness than even the emptiest patch of ordinary space, which, as discussed earlier in this series, still quietly carries physical fields, laws, and structure of its own. This reframing doesn't fully settle the underlying question any more completely than earlier philosophical approaches did, since it's still fair to ask why any information should exist at all rather than none. But it offers a genuinely different and more precise vocabulary for approaching the very same deep question, showing that even humanity's oldest philosophical puzzles keep getting reshaped and reconsidered as science keeps developing fresh new tools and fresh new ways of thinking. What is reality? The question of what reality is ultimately built from has come up from several different angles throughout this series, including whether mathematics itself forms the deepest layer of everything, whether space and time are truly fundamental, and whether inner experience plays any special, built-in role within reality's basic structure. Pulling these threads together reveals several genuinely different, competing answers still taken seriously today. The view most scientists work from day to day holds that reality is ultimately built from ordinary physical matter and energy, with everything else, including thought and feeling, fully emerging from that same underlying physical foundation, without needing anything extra layered on top. This view has proven enormously successful as a working approach to doing science, but as discussed in an earlier part of this series regarding consciousness, it still struggles to fully explain why physical activity should be accompanied by any felt experience at all, rather than simply happening quietly with nothing on the inside. An older opposing view holds instead that mind or experience is the truly fundamental ingredient, with the physical world we observe being some kind of expression or construction built from that more basic mental foundation rather than the other way around. A third, in-between view suggests both mind and matter might spring from some deeper, more neutral foundation that is, by itself, neither fully mental nor fully physical, only becoming one or the other depending on how it's viewed. A fourth and increasingly discussed view suggests that some extremely basic, minimal flicker of experience might be a built-in property of matter at every scale, not something that only switches on suddenly once matter organizes itself into something as complicated as a brain, a position that has drawn fresh, serious attention partly because of the same unresolved difficulty ordinary physical explanations run into when trying to fully account for experience. Given this genuine and lasting diversity of seriously considered positions, each tackling a different piece of the puzzle while facing its own real difficulties, the basic question of what reality most fundamentally consists of remains one of the most enduringly open questions in the whole history of both philosophy and science, with science's remarkable success at describing and predicting the observable world not, on its own, having fully settled the deeper question of reality's own truest underlying nature. Does the universe have a purpose? Whether the universe carries any built-in purpose, some specific goal it's quietly working toward rather than simply unfolding according to impersonal physical rule with no direction at all, sits right at the boundary between physics, philosophy, and personal belief, and ordinary scientific method isn't especially well equipped to settle it directly. Since science generally aims to describe how events happen, rather than whether those events serve some deeper intended purpose beyond their own immediate physical causes. Some thinkers point to the remarkably delicate balance of the universe's own basic rules, discussed in an earlier part of this series, as at least suggestive of a universe specifically arranged to eventually produce complexity and conscious life, an argument some have pushed even further, proposing the universe must, in some stronger sense, possess exactly the properties needed for life to eventually appear within it, a proposal others consider straying beyond what ordinary testable reasoning can support, since it's genuinely hard to tell that stronger claim apart from simply observing that our universe happens to permit our own existence, without any deeper requirement necessarily being involved. A contrasting view, closely tied to an ordinary scientific outlook, holds that the more thoroughly physics comes to understand how the universe actually works, the more genuinely purposeless and impersonal it appears to be at its most basic level, a view memorably summed up by one physicist's observation that the more comprehensible the universe becomes, the more pointless it also seems to become, a specifically striking phrase that has itself been widely discussed and debated ever since. A further useful distinction separates purpose in the sense of some deliberately intended goal set in place before anything even began, which would require some kind of outside guiding intelligence to have set that goal, from purpose in the far more modest sense of meaning and value that conscious beings, once they eventually appear through ordinary natural processes, are capable of finding and creating for themselves from within the universe itself. A more modest sense of purpose that some philosophers argue is both more defensible and, in practical terms, ultimately more meaningful than the grander, more demanding kind of purpose traditional teleological views usually require. Since this question reaches well beyond what any current or realistically foreseeable scientific method could directly test, whether the universe truly holds intrinsic purpose remains fundamentally a matter of philosophical reasoning and personal belief, rather than something science is currently equipped to settle either way. Is intelligence inevitable? Whether complex, human-like intelligence is a highly likely outcome of evolution given enough time on a suitable planet, or whether it's instead a rare, accidental outcome that could easily have failed to happen even under otherwise similar conditions, remains a genuinely open and actively debated question with real relevance to how common intelligent life might be throughout the universe. One well-known paleontologist has argued, based on the widely documented pattern of evolution repeatedly and independently arriving at broadly similar solutions to shared problems across entirely separate lineages, that intelligence, or at least some comparably sophisticated form of thinking, likely represents a similarly expected outcome, likely to eventually show up on any sufficiently habitable planet, given enough time, pointing to how sharp thinking abilities have already evolved independently, more than once here on Earth, in separate branches of intelligent sea creatures, clever birds, and various primates alike. A different and equally well-known paleontologist argued the opposite, examining the strange and remarkably varied early animal body types preserved in one especially well-known ancient fossil site, and proposing that if you could somehow rewind Earth's history and let evolution play out again from some early starting point, it would very likely produce an entirely different and quite possibly far less complex or intelligent final outcome. Given how many individual chance events, including the specific asteroid impact that wiped out the dinosaurs, discussed in an earlier part of this series, ended up shaping which particular lineages happened to survive and thrive at each major turning point in Earth's long history. This disagreement between seeing intelligence as a broadly expected outcome versus a largely accidental one remains genuinely unresolved, complicated by the simple fact that we currently only have exactly one confirmed example of a planet where any life, let alone intelligent life, is known to have evolved at all, making it genuinely difficult to draw any confident general conclusion from such a limited single example. The ongoing search for both simple and intelligent life beyond Earth, discussed at various points throughout this series, may eventually help provide further evidence bearing directly on this same basic question, though no confirmed evidence of life beyond Earth currently exists to help settle this particular scientific debate one way or the other. Is consciousness fundamental? Whether conscious experience is a basic, built-in feature of reality itself, present in some form at the very deepest level of physical existence, or whether it's instead a later arising phenomenon that only appears once physical matter gets organized into something sufficiently complex like a living brain, is one of the deepest questions raised throughout this series, tying directly back to earlier discussions of the hard problem of consciousness and the possibility of some basic form of experience being built into matter itself. The standard scientific working assumption holds that consciousness only arises once matter is organized into a sufficiently complex system, such as a nervous system past a certain threshold of complexity, with simpler things like individual atoms or plain rocks carrying no experience whatsoever. This view fits naturally alongside the broader idea that reality is fundamentally physical, but it still runs into the same persistent difficulty of fully explaining why or how experience actually switches on once that threshold gets crossed, rather than complex activity simply continuing to happen with nothing being felt at all, no matter how complex it becomes. An alternative view proposes instead that some extremely basic, minimal form of experience is already a fundamental property of matter at every scale, with the rich, complex experience creatures like us have, arising through some kind of combination of these more basic underlying elements, rather than experience switching on suddenly only once a certain threshold of complexity is reached. This avoids needing to explain how experience could ever arise from something with no experience in it at all, though it faces its own serious difficulty in explaining exactly how countless tiny, separate flickers of basic experience could ever combine into the single unified experience each of us seems to have. A third, more radical view flips the usual order entirely, treating consciousness itself as the single most fundamental starting ingredient of reality, with the physical world we ordinarily observe instead being some kind of expression of that more basic underlying awareness, a view sharing real similarities with older philosophical positions discussed elsewhere in this series, and one that has drawn renewed serious academic attention in recent years. Because consciousness still lacks any single, universally agreed scientific definition or reliable outside test capable of confirming its presence anywhere, settling whether it's fundamental or merely emergent remains genuinely difficult using any current scientific method, leaving this question to be addressed mainly through careful reasoning rather than direct experiment. Are we alone? Whether intelligent life exists anywhere else in the universe remains completely unresolved, with no confirmed detection of life beyond Earth of any kind, simple or complex, ever having been made, despite several decades of dedicated searching. A persistent silence that sits in genuine tension with just how vast the universe actually is, filled with an almost uncountable number of galaxies, each one containing an enormous number of individual stars, a good many of which are now confirmed to host their own orbiting planets. This tension is sometimes summed up by a simple, pointed question one physicist reportedly raised during an informal conversation decades ago, essentially asking why, given how many stars and planets exist, we haven't heard from anybody else yet. One well-known way of organizing this question breaks the overall likelihood of detectable intelligent civilizations down into a series of separate factors multiplied together, including how many stars form, how many host planets, how many of those planets are habitable, how many of those actually develop life, how many of those develop intelligence, how many of those develop detectable technology, and how long such a civilization would keep broadcasting anything detectable before falling silent. Because several of these individual factors remain deeply uncertain, this framework doesn't produce one single confident final answer on its own, but it does offer a genuinely useful way of structuring the whole question clearly. Several distinct ideas have been proposed to help explain the current silence. One idea suggests the specific combination of conditions needed for complex life, including a stable host star and a large, steadying moon, discussed in an earlier part of this series, might simply be rarer throughout the universe than more optimistic assumptions suggest. Another idea proposes that some particular evolutionary or technological stage is extremely difficult to get past, acting as a kind of filter that most developing civilizations never manage to survive, with a genuinely unsettling open question being whether humanity has already safely passed that filter in its own past, or whether it still lies somewhere ahead of us. Other ideas suggest civilizations might typically destroy themselves before ever reaching the point of broadcasting clearly detectable signals, or might simply choose, for their own reasons, not to announce their presence at all. Given how limited our searching has been so far compared to the sheer scale of the universe, the current silence can't yet be treated as solid proof that intelligent life is rare or absent, leaving the basic question of whether we're truly alone among the most significant, genuinely open questions in all of science today. Can science explain everything? Whether the scientific method, the careful, repeatable process of forming testable ideas and checking them against real observation, is capable, even in principle, of eventually explaining every meaningful aspect of reality, or whether some parts of existence simply lie permanently beyond its reach, connects directly to many separate threads already raised throughout this series. A few specific candidate limits to science's reach have already come up along the way. The hard problem of consciousness, discussed in an earlier part of this series, questions whether any complete outside description of the brain, however detailed, could ever fully explain the actual felt quality of experience itself. The deep question of why any physical laws exist at all, and why they take the particular form they do, discussed regarding the universe's own beginning, sits at least partly outside science's usual method, since science generally explains events by appealing to deeper existing laws, but doesn't typically explain why those deeper laws themselves hold in the specific way that they do. A useful standard for judging whether an idea properly counts as scientific holds that it must make specific predictions that could, at least in principle, be shown false by some possible future observation, a standard that has led some to question whether certain highly speculative theoretical proposals, including some far-reaching multiverse and string theory ideas discussed elsewhere in this series, fully qualify as strictly scientific in this demanding sense, since most of their specific predictions concern other regions or universes that lie permanently beyond any possible direct observation, no matter how advanced our instruments eventually become. A further important distinction separates questions about observable physical fact, which science handles remarkably well given enough time and technology, from questions about values, ethics, and meaning, which many philosophers argue require an entirely different kind of reasoning that can't simply be reduced to observation and measurement alone, a long-standing distinction sometimes summarized as the difficulty of deriving any statement about what ought to be from statements only describing what simply is. Given these several identified candidate limits, many philosophers of science conclude that while science has proven an extraordinarily powerful method for understanding a great deal about the physical world, there likely remain at least some meaningful categories of question lying permanently, or at least very persistently, beyond its particular reach, though this conclusion itself remains a genuinely contested position rather than a fully settled matter. Is the universe alive? Whether the universe as a whole might reasonably be considered alive in some genuine sense rather than simply consisting of ordinary matter and energy following fixed impersonal rules, first requires carefully clarifying exactly what standard criteria are normally used to define biological life, before then trying to see whether the universe might actually meet them. Biologists generally look for a handful of specific features when defining life, including organized cellular structure, the ability to reproduce, the ability to grow, the ability to respond to its surroundings, and the ability to maintain stable internal conditions despite a changing outside environment, alongside the ability to take in and use outside energy for all of this. Measured directly against this standard checklist, the universe as a whole doesn't appear to satisfy the large majority of these features in any straightforward, literal sense, lacking any confirmed way of reproducing itself, growing toward any specific goal, or genuinely regulating its own internal state the way living things do. Even so, some physicists have seriously proposed looser, more structural comparisons between certain cosmic processes and biological ones. One well-known physicist proposed a genuinely serious hypothesis, suggesting that new universes might form through a specific process occurring inside collapsed stars, with each resulting universe inheriting slightly randomly varied physical rules from its own parent universe, and universes whose particular rules happen to favor producing more of these collapsed stars, naturally producing more offspring universes in turn, creating a process broadly resembling biological natural selection playing out at the grandest possible cosmic scale. This idea remains a seriously considered, though clearly minority position, among physicists studying the universe's deepest structure. A separate and more casual line of thinking points to a loose visual resemblance between the universe's own large-scale web of galaxies and filaments and the branching, self-organizing patterns found in biological nervous systems, a comparison that has genuinely been studied and discussed, though most researchers involved in that comparison stress that the resemblance likely reflects shared underlying principles of efficient network formation under similar physical constraints, rather than pointing to any deeper, literal biological connection between cosmic structure and actual life or awareness. Given the universe's clear failure to meet most standard biological criteria in any literal sense, most scientists don't consider the universe alive in any literal, scientifically meaningful way, though certain specific, seriously developed proposals do genuinely explore whether something resembling evolution might operate at the very largest cosmic scales, representing a fascinating, if still highly speculative, minority position within physics today. Will humanity ever know every scientific answer? Whether human scientific inquiry could ever reach a genuine, complete finish line, having successfully answered every meaningful and answerable question there is to ask, or whether it instead necessarily keeps going forever without any final stopping point, touches directly on several themes raised throughout this series, including the specific limits already identified regarding gravity, consciousness, and the deepest questions about existence itself. One especially significant piece of relevant mathematics proves that within any sufficiently powerful logical system capable of ordinary arithmetic, there will always exist true statements that cannot be proven true using only that same system's own internal rules, a landmark result in mathematical logic whose broader implications for physics remain genuinely debated, since this result technically applies directly to formal logical systems rather than automatically to scientific inquiry as a whole, though some physicists have suggested it may hint at similar fundamental limits on ever building one single, complete theory covering absolutely everything in physics, a suggestion others have pushed back against as reading too much into a more narrowly specific mathematical result. Beyond this formal consideration, several of the deepest questions already raised throughout this series, including why any physical laws exist at all and the hard problem of subjective experience, may simply not be fully answerable using science's own standard method at all, suggesting that even a hypothetically complete physical theory, fully explaining every physical process in exhaustive mechanical detail, still might not fully settle these deeper underlying philosophical questions on its own. A further, more practical consideration comes from simply looking at the history of science itself, which shows a consistent pattern of major discoveries, opening up entirely new and previously unimagined questions, rather than steadily narrowing everything down toward one final, complete answer. A pattern this very series has illustrated repeatedly, with breakthroughs in understanding the tiny-scale world, gravity, and life itself, each resolving old mysteries while simultaneously generating a whole new set of deeper open questions in turn, with nothing in this pattern suggesting it's likely to simply stop anytime soon. Given these formal, philosophical, and historical considerations taken together, most scientists and philosophers of science consider it unlikely that humanity will ever reach a true final endpoint where every meaningful scientific question has been completely answered, though this ongoing, unfinished state of inquiry is generally seen as a genuinely exciting and productive feature of science, rather than any kind of disappointing failure on its part. What is the greatest mystery of all? Having traveled across the stars, the deep past, the human body and mind, the strange tiny-scale world, mathematics, and the biggest questions of all throughout this entire series, it's worth asking, gently, whether any single one of these many open mysteries might reasonably be considered the very deepest of them all. The question of why anything exists at all, rather than nothing whatsoever raised early in this series, arguably sits at the very deepest possible level, since every other mystery discussed throughout the rest of this series, from hidden gravitational matter to human consciousness itself, already assumes that a universe capable of containing these mysteries exists in the first place, making this particular question logically prior to every other question raised throughout the entire series. The hard problem of consciousness holds an equally strong claim to this same title, since it's the one singular mystery through which every other mystery discussed throughout this series must itself be experienced and understood in the first place. A universe containing hidden gravitational matter, collapsed stars, and independent mathematical truths, but no conscious experience anywhere within it, would have no one present to ever notice, appreciate, or properly formulate any of these mysteries as mysteries to begin with. The question of why mathematics describes physical reality so well, raised earlier in this series, offers a third and genuinely different foundational candidate, sitting right at the crossing point between pure abstract logic and concrete physical fact, two categories ordinary intuition treats as separate, yet which this mystery reveals to be connected in some deep and still not fully understood way. Rather than crowning any single one of these the greatest, it may be more useful to notice that these deepest mysteries are closely woven together, exactly as this series has repeatedly traced. Existence connects to why physical law takes its particular form. Consciousness connects to what reality itself ultimately consists of. And mathematics' effectiveness connects back to whether the universe is, at bottom, a mathematical structure. Rather than being scattered puzzles, they appear to be different facets of one deeply unified, still unresolved question about existence, mind, and truth. What can be said with real confidence is that careful human inquiry has made genuine, substantial progress on very many fronts, even while several of the very deepest underlying questions remain genuinely open and still under active investigation. That combination, real progress alongside real remaining mystery, is not a disappointing place to arrive after this whole long journey. It's simply an honest description of exactly where careful human understanding stands today, poised at the edge of an enormous amount of discovery still waiting to be made. As our journey through the greatest scientific mysteries comes to an end, it's worth remembering that every answer humanity has ever discovered began as a mystery someone refused to ignore. For thousands of years, people looked up at the stars, wondered why lightning split the sky, questioned where life came from, and asked what consciousness truly is. Many of those questions found answers, but countless others remain, waiting for the next curious mind to uncover them. Science isn't just a collection of facts. It's a never-ending story of curiosity. Every new discovery opens the door to even deeper questions, reminding us that the universe is always far more mysterious than it first appears. Perhaps one day we'll understand dark matter. Perhaps we'll discover life beyond Earth. Perhaps we'll finally explain consciousness, solve the mysteries of quantum physics, or even learn what happened before the beginning of time. Or perhaps some mysteries will remain forever beyond our reach, inviting generation after generation to keep searching. And maybe that's the most beautiful part of science. Not that it has all the answers, but that it never stops asking questions. If you've made it this far, thank you for letting this journey accompany you into the night. I hope these mysteries sparked your imagination, filled you with a sense of wonder, and maybe even helped you drift into a peaceful sleep beneath the same universe we've been exploring together. Rest well, and remember, the greatest mystery isn't how much we know, it's how much there still is to discover. Good night.